Our universe is brimming with mysteries, from the tiniest quantum particles to the vast, sprawling structures of the cosmos. These enigmas challenge our understanding, teasing the minds of scientists who, despite remarkable progress, are continuously confronted with new questions. Each discovery seems to spark even more curiosity, compelling us to ask, what lies beyond the limits of our current knowledge? Join us as we embark on a journey to explore the uncharted territories of our extraordinary universe, where the boundaries of science and imagination blur. One of the most captivating and elusive mysteries is dark matter. Comprising roughly 27% of the universe, this invisible substance remains one of the greatest scientific puzzles. Dark matter doesn't emit light or any form of electromagnetic radiation, rendering it undetectable by our most advanced instruments. Despite its invisibility, we are certain of its existence, largely due to its gravitational influence on visible matter, radiation, and even the very structure of the universe. Galaxies, for example, rotate in a way that suggests they contain much more mass than what can be observed through telescopes, hinting at an unseen force at play. This unseen mass, which we call dark matter, is thought to be far more abundant than ordinary matter, but its exact nature remains a mystery. The reason dark matter continues to elude detection is its lack of interaction with electromagnetic forces, the very forces that allow us to see objects through light. Without this interaction, dark matter cannot reflect or emit light, which makes it impossible to observe directly. Scientists have proposed a variety of theories about what dark matter might be. Some suggest it could consist of exotic particles, such as weakly interacting massive particles, WIMPs, or axions. Yet, despite these compelling theories, the true identity of dark matter remains unknown, leaving scientists to speculate and search for answers. Dark matter's role in the cosmos is profound. It plays a critical part in shaping the large-scale structure of the universe, forming a vast, invisible web that extends far beyond galaxies. This web influences the formation, movement, and clustering of galaxies, effectively acting as a scaffold for ordinary matter to coalesce into the complex structures we observe today. Evidence for this cosmic framework comes from a variety of sources, including the cosmic microwave background radiation and the way galaxies cluster together. These observations suggest that dark matter serves as the invisible framework that guides the formation and evolution of galaxies and galaxy clusters. Understanding dark matter is crucial for building a complete picture of the universe's composition and its evolution over time. As scientists develop more sophisticated instruments and search for ways to create dark matter particles in laboratory settings, the quest to unlock the secrets of this enigmatic substance continues. With each step forward, we inch closer to understanding not only what dark matter is, but also how it shapes the universe we live in. Detecting dark matter is an incredibly challenging endeavor. Because it doesn't emit light and interacts only weakly with ordinary matter, scientists cannot observe it directly. Instead, they rely on indirect methods to infer its presence. One of the primary techniques used to detect dark matter is the study of its gravitational effects on galaxies and galaxy clusters. By examining the rotation curves of galaxies, researchers have observed that the outer regions of galaxies rotate faster than expected based on the visible matter alone. This discrepancy suggests the presence of a substantial amount of unseen mass, dark matter, that is influencing the galaxy's rotation. Another powerful tool used in the search for dark matter is gravitational lensing. When light from distant objects passes near a massive galaxy cluster, the gravity of the cluster bends the light, creating distorted images or even multiple images of the same object. By analyzing these distortions, scientists can map out the distribution of mass within the galaxy cluster. The amount of visible matter alone does not account for the observed bending of light, reinforcing the idea that dark matter must be present, providing the additional gravitational pull needed to explain these effects. As we continue to probe the mysteries of dark matter, we are reminded of the vast unknowns that still lie beyond our reach. The search for this invisible substance is not just about understanding what it is, it's about understanding the very nature of the universe itself. And as technology advances and new discoveries are made, the answers to these profound questions may soon be within our grasp, unveiling a deeper, more intricate cosmos than we ever imagined. Scientists are actively exploring new methods to detect dark matter directly by using highly sensitive detectors buried deep underground, shielded from the cosmic radiation that constantly bathes the Earth's surface. These detectors are designed to catch the rare interactions between dark matter particles and ordinary matter. Numerous experiments are underway, each striving to identify potential candidates for dark matter, such as weakly interacting massive particles, WIMPs. While a definitive detection has yet to occur, the continuous advancements in technology and detection methods are fueling optimism within the scientific community. In parallel to these underground efforts, astrophysical observations are also playing a key role in unraveling the mystery of dark matter. One of the most valuable tools is the cosmic microwave background radiation, CMB, which serves as a snapshot of the early universe. By studying the CMB, scientists gain insights into the distribution of dark matter shortly after the Big Bang, providing crucial data to refine our models of cosmic structure formation. This helps researchers understand how dark matter has influenced the development of the universe we observe today. Together, these varied approaches form a multi-layered strategy aimed at unveiling the true nature of dark matter. A number of compelling theories have emerged, each offering a different perspective on what dark matter could be. One of the leading candidates in this search is WIMPs, hypothetical particles that are predicted to have mass but interact only through weak nuclear forces, making them extremely difficult to detect. WIMPs are particularly attractive because they arise naturally from extensions of the standard model of particle physics, especially within supersymmetric theories, which predict a stable, massive particle that could serve as the building block of dark matter. Another fascinating candidate is the axion, an extremely light particle linked to the strong nuclear force. Initially proposed to address an issue in quantum chromodynamics, axions may also provide an explanation for dark matter. These particles, if they exist, could be so abundant throughout the universe that they remain undetectable by current methods. However, scientists are developing experiments designed to detect axions by studying their potential interactions with photons in strong magnetic fields. Some theories propose that dark matter could be composed of primordial black holes, tiny black holes that might have formed in the universe's earliest moments. If these black holes were created shortly after the Big Bang, they could explain certain observed behaviors that we currently attribute to dark matter. However, confirming their existence and determining their abundance is a challenge that remains unsolved. Lastly, alternative theories suggest modifications to gravity itself, proposing frameworks like modified Newtonian dynamics, MOND, to explain cosmic phenomena. Rather than postulating unseen matter, these models attempt to explain galactic behaviors by altering the laws of gravity. Though these theories have garnered interest, they have not achieved widespread acceptance when compared to particle-based explanations. These diverse theories, whether involving exotic particles or radical changes to our understanding of gravity, illustrate the ongoing pursuit of understanding dark matter. Each theory, in its own way, sheds light on the role this enigmatic substance plays in shaping the universe we live in. While dark matter remains elusive, researchers have also been grappling with the question of dark energy, another mysterious force that is just as important to our understanding of the cosmos. Dark energy is responsible for the accelerated expansion of the universe and makes up roughly 73% of its total energy density. Unlike dark matter, which clusters around galaxies and contributes to their gravitational pull, dark energy appears to be evenly distributed throughout space. Its primary role is to counteract the attractive force of gravity, pushing galaxies apart and causing the universe to expand at an ever-increasing rate. The discovery of dark energy in the late 20th century came as a surprise. Observations of distant supernovae revealed that galaxies were moving away from us faster than expected, hinting at an acceleration in the universe's expansion. This led scientists to propose the existence of a repulsive force, which they named dark energy. Unlike ordinary matter or dark matter, both of which clump together under gravity, dark energy seems to resist gravitational attraction. This results in the accelerated expansion we observe today. The behavior of dark energy, with its negative pressure and uniform presence throughout the cosmos, contrasts sharply with that of dark matter. Dark matter interacts through gravity, helping to form the structures we see in the universe, whereas dark energy's effect is felt primarily on cosmological scales, where it drives the universe's expansion. This dichotomy between dark matter and dark energy underscores their very different roles in shaping the cosmos. As researchers continue to study both dark matter and dark energy, it becomes clear that understanding these two components is critical to painting a full picture of the universe. There is even the possibility that the two are interconnected in ways we have yet to understand. Such discoveries could lead to groundbreaking insights into the fundamental nature of the universe itself. The accelerated expansion of the universe, driven by dark energy, represents one of the most profound discoveries of modern cosmology. Observations at the close of the 20th century, particularly those examining distant supernovae, revealed that rather than slowing down due to gravitational forces, the universe's expansion was speeding up. This unexpected finding prompted scientists to investigate the nature of a force that could counteract gravity on a cosmic scale: dark energy. Dark energy is believed to permeate the universe, exerting a negative pressure that causes space itself to expand. Unlike the matter and dark matter that clump together under gravity, dark energy seems to work in the opposite direction, pushing galaxies apart and accelerating the universe's expansion. The study of dark energy, along with dark matter, continues to be one of the most exciting frontiers in physics, as researchers strive to understand how these two forces shape the future of the universe. The true nature of dark energy continues to be one of the most profound and elusive challenges in cosmology. Despite decades of research, scientists remain uncertain about whether dark energy is a fundamental property of space itself, a completely unknown field, or perhaps the result of modifications to our current understanding of gravity. One of the most prominent theories is the concept of the cosmological constant, a term first introduced by Albert Einstein in his general theory of relativity. This constant represents a fixed energy density that uniformly fills space. When incorporated into the equations of cosmology, the cosmological constant suggests that as the universe expands, dark energy becomes more dominant. This causes the expansion to accelerate, pushing galaxies away from one another at increasing speeds. While this theory aligns with many observations, other hypotheses propose different forms of dark energy, each with its own potential implications for the universe's future. The consequences of an accelerating universe are profound. As time progresses, galaxies will continue to recede from one another, leading to a future characterized by vast, cold stretches of space, with fewer stars and galaxies visible to the eye. Such a future paints a picture of an increasingly desolate cosmos. Understanding dark energy is thus not only vital for explaining the current dynamics of the universe, but also for grasping its ultimate fate. As scientists continue to investigate this mysterious force, it remains a central focus of modern cosmological research. If dark energy did not exist, the future of the universe would look drastically different. Currently, dark energy is the driving force behind the accelerated expansion of the cosmos, causing galaxies to move away from each other faster and faster. Without this enigmatic influence, the universe's expansion would slow down. The gravitational pull of both visible and dark matter would take over, altering the universe's expansion. In this alternative scenario, the universe would gradually decelerate as gravity tugged on galaxies and other celestial bodies. Depending on the total density of matter in the universe, this slowing expansion could lead to various outcomes. If the matter density were high enough, gravitational forces could eventually overcome the expansion, leading to a dramatic reversal in the form of a big crunch. In this case, the universe would cease expanding and start contracting, ultimately collapsing back into a singularity. On the other hand, if the density of matter were precisely at a critical threshold, the universe might expand forever, but at a constantly decelerating rate. This scenario would create a flat universe, one that keeps growing, but with the expansion slowing down over time. Such a universe, however, would become increasingly isolated. Galaxies would drift farther apart, and eventually, cosmic expansion would lead to a universe full of dark, isolated galaxies. an increasingly static and lifeless environment. The existence of dark energy helps explain the observed acceleration of the universe's expansion. Without dark energy, measurements from distant supernovae and large-scale cosmic structures would yield different interpretations of how the universe has evolved. The absence of dark energy would radically change our understanding of cosmology and the universe's ultimate destiny, reducing it to a cosmic dance solely dictated by gravitational forces and the matter within. Astronomers have developed several sophisticated methods to measure the effects of dark energy, each leveraging the vastness of the cosmos and the light it emits. One of the most influential techniques involves studying distant supernovae, particularly type Ia supernovae. These stellar explosions exhibit a remarkable consistency in their brightness, allowing astronomers to use them as standard candles to measure cosmic distances. By observing how bright or dim these supernovae appear from Earth, scientists can determine their distance and track the rate at which they are receding. The surprising dimness of these supernovae suggests that the universe's expansion is accelerating, a phenomenon attributed to dark energy. Another powerful method is gravitational lensing. This technique examines how the light from distant galaxies is bent by massive objects like galaxy clusters in the foreground. The extent of this bending provides crucial insights into the distribution of both visible and dark matter in the universe. By studying how these gravitational lensing effects change over distance, astronomers can gain a deeper understanding of how dark energy influences the expansion rate and structure of the cosmos. Perhaps the most fundamental tool for measuring dark energy is the cosmic microwave background radiation, CMB, the faint afterglow of the Big Bang. This radiation fills the entire universe and carries with it valuable information about the early conditions of the cosmos. By analyzing the temperature fluctuations in the CMB and how these variations are distributed across the sky, scientists can derive key parameters related to dark energy, such as its density and constant. CMB measurements serve as a crucial cross-check against findings from supernovae observations and the study of large-scale cosmic structures, providing a comprehensive picture of the universe's past, present, and future. In conclusion, dark energy remains one of the most profound and enigmatic forces shaping the universe's fate. Despite the many questions still surrounding it, ongoing research continues to unlock more details about its role in the cosmos. As we uncover more, we get closer to understanding not only the mysteries of dark energy itself, but also the ultimate trajectory of the universe we call home. The study of galaxy distributions and their clustering over time provides scientists with an extraordinary window into the universe's evolution. By mapping the arrangement and grouping of galaxies, astronomers can detect subtle patterns that reveal the influence of dark energy on cosmic expansion. These clusters, how galaxies form, spread, and interact, offer vital clues, helping researchers trace the hidden footprints of dark energy as it shapes the structure of the universe. Combining these observations with other methods, such as the study of cosmic background radiation and galaxy redshifts, crafts a fuller picture of how dark energy is molding the cosmos we see today. While dark energy and dark matter are the leading explanations for many astronomical phenomena, alternative theories continue to emerge in an attempt to unravel these cosmic mysteries. One of the most prominent challengers to the dark matter theory is the concept of modified gravity. This hypothesis, rooted in modified Newtonian dynamics, MON, proposes that the laws of gravity might behave differently at very low iterations, conditions that prevail in the outer regions of galaxies. MON-D suggests that Newton's laws break down in these low acceleration zones, thereby explaining the observed rotational speeds of galaxies without requiring unseen mass. However, while MON does provide a compelling explanation for certain galactic behaviors, it struggles when it comes to large-scale structure formation and other cosmological observations. This limitation has made it a less favored explanation among the scientific community. Another alternative seeks to introduce additional fundamental forces to the mix. These fifth forces are theorized to influence the behavior of matter on cosmic scales. The idea is that beyond the familiar gravitational forces, there may be additional interactions at play that could help explain galactic rotation curves without invoking dark matter. Yet, these theories remain speculative and have failed to gather significant empirical support, making them unlikely contenders in the ongoing search for explanations of the universe's mysterious behavior. When it comes to dark energy, one of the main alternatives is the idea of quintessence. Unlike the standard cosmological constant, which assumes that dark energy is a fixed, unchanging force, quintessence posits that dark energy is a dynamic, fluid-like field that can evolve over time and space. This model could potentially account for the observed variations in the rate of cosmic expansion. However, quintessence faces its own challenges. One of the main hurdles is distinguishing its behavior from that of a simple, static cosmological constant. Still, quintessence offers a fascinating way to think about dark energy as something more than a fixed property of the universe. In another line of thought, some researchers argue that the effects typically attributed to dark energy might not be the result of an unknown force at all. Instead, they propose that irregularities in the distribution of matter throughout the cosmos could create the illusion of accelerated expansion. According to this theory, the apparent acceleration is merely a byproduct of how galaxies and other matter are arranged in the universe. While this approach presents an intriguing new lens through which to view cosmic expansion, it requires solid evidence to challenge the robustness of the dark energy framework, which has already provided such a successful explanation for many observed phenomena. These alternative theories continue to spark debate, keeping the scientific community in a constant state of inquiry. While dark matter and dark energy remain the dominant explanations, exploring these alternatives is essential in pushing the boundaries of our understanding of the universe. Each theory, no matter how unconventional, adds a new dimension to the ongoing conversation about the cosmos, encouraging researchers to probe deeper into the very fabric of reality. Beyond the mysteries of dark matter and energy lies one of the most puzzling features of the universe: black holes. At the core of a black hole is the event horizon, a boundary beyond which not even light can escape. As an object crosses this threshold, it is inexorably drawn toward the singularity, the point at which gravitational forces become infinite and space-time itself breaks down. Within this realm, classical laws of physics cease to function in the ways we understand them. In the presence of a black hole, gravity warps space and time to such an extent that the very notion of inside and outside loses its meaning. The journey towards the event horizon is a harrowing one. As an object gets closer, the gravitational pull grows stronger, leading to what is known as a tidal effect. This effect is so intense that it creates a massive disparity in the forces acting on different parts of the object, causing it to stretch and compress, an effect so extreme that it is often described as spaghettification. The process varies depending on the size of the black hole. For smaller black holes, tidal forces increase sharply, making the stretching more violent. In contrast, larger black holes create a gentler gradient in gravitational pull, allowing objects to approach the event horizon in a less catastrophic manner. Once inside the event horizon, the usual concepts of time and space no longer apply in a conventional sense. According to Einstein's theory of general relativity, time behaves in peculiar ways near a black hole. To an observer falling into a black hole, time would seem to pass normally. However, from the perspective of someone watching from afar, the object would appear to slow down as it approaches the event horizon. It would seem to freeze at the threshold, never quite crossing it. This time dilation effect creates a sharp contrast between the perception of an object falling into a black hole and the view from outside. In the strange and mysterious environment of a black hole, the very nature of space-time is stretched to its limits, and the laws of physics must be rewritten. Understanding these extremes not only challenges our fundamental concepts, but also offers a glimpse into the mind-boggling forces that govern the universe on its most extreme scales. The singularity at the heart of a black hole is a realm of intense mystery and complexity, one that defies the very framework of modern physics. Here, gravity reaches infinite strength, and space-time itself becomes so contorted that classical physics ceases to function. It is at this point that quantum effects begin to take precedence, creating a chaotic environment where the very nature of reality is questioned. In this boundary-pushing domain, physicists continue to grapple with an unresolved paradox. How can we reconcile the principles of general relativity, which governs the large-scale structure of the universe, with quantum mechanics, the laws that rule the microscopic realm? These extreme conditions have led to an ongoing quest for a unified theory that can accurately describe the events unfolding within the black hole. This quest for understanding stretches the limits of human knowledge, driving us to explore some of the deepest questions about the universe itself. The mysteries surrounding black holes not only challenge our understanding of physics, but also inspire an insatiable curiosity, pushing the boundaries of science and uncovering new layers of the cosmos's fundamental nature. At the centers of most galaxies, including our own Milky Way, lie supermassive black holes, each one containing millions to billions of times the mass of our Sun. The formation of these colossal objects is still a subject of much debate, as it involves an intricate dance of several cosmic processes over vast periods of time. One leading theory proposes that supermassive black holes are born from the merging of smaller black holes and massive clouds of gas, a process that likely took place in the early universe. In the early stages of the universe, vast regions of dense gas filled the space. As these gas clouds collapsed under their own gravitational pull, they formed the first generation of stars. The most massive of these stars, which lived short but intense lives, ended in supernovae, some of which could have given birth to stellar black holes. Over time, these stellar black holes may have collided and merged, forming progressively larger black holes. Simultaneously, the surrounding gas plays a crucial role in this process. As gas spirals into the black hole, it heats up and emits radiation, causing the gas to collapse even more rapidly than it otherwise would. This process of accretion, where gas and stars are devoured by the black hole, creates the necessary conditions for a black hole to grow larger, sometimes at an astonishing rate. Given the right conditions, such a process could rapidly lead to the formation of a supermassive black hole. Another potential formation mechanism involves the direct collapse of a massive gas cloud. In this scenario, a sufficiently dense gas cloud may collapse under its own weight without forming stars, directly creating a massive black hole. This process could have been particularly prevalent in the early universe, where dense regions of gas allowed for the quick formation of these enormous objects. As these supermassive black holes continue to grow, they can do so by absorbing nearby gas, stars, and even other black holes. In fact, the merging of black holes during galaxy collisions is thought to have been a common occurrence throughout cosmic history, especially during significant epochs of galactic interactions. The prevalence of supermassive black holes at the centers of galaxies is a direct result of this complex interplay of gravitational dynamics, stellar evolution, and cosmic evolution. These forces have shaped the cosmos as we know it, creating the monstrous black holes that continue to captivate and perplex us. One of the most intriguing theories about black holes is the concept of Hawking radiation, proposed by physicist Stephen Hawking in 1974. This theory suggests that black holes can actually emit radiation and, over time, lose mass. According to the principles of quantum mechanics, pairs of virtual particles are constantly appearing and disappearing in the vacuum of space. Near the event horizon of a black hole, one of these particles can fall into the black hole while the other escapes into space. If the escaping particle has positive energy, it can manifest as radiation emitted by the black hole. This phenomenon leads to a fascinating implication. As the black hole emits Hawking radiation, it gradually loses mass and energy, shrinking over time. If the rate of radiation emission exceeds the rate at which material is falling into the black hole could eventually evaporate entirely. However, this process would take an incredibly long time, billions of years for a large black hole. But for smaller black holes, the effects of Hawking radiation would be much more pronounced, leading to faster evaporation. The theoretical existence of Hawking radiation raises profound questions about the ultimate fate of black holes. Perhaps the most challenging of these is the question of what happens to the information about the matter that falls into a black hole. According to quantum mechanics, information cannot be destroyed, but general relativity seems to imply that once something crosses the event horizon, it is lost forever. This creates the so-called information paradox, a conflict that has sparked much debate and research in theoretical physics. To resolve this, some scientists have proposed new frameworks, such as the holographic principle, that might offer a way to reconcile these two contradictory ideas. Although Hawking radiation has not yet been directly detected, it remains a cornerstone of theoretical research into black holes and their fundamental properties. The implications of this theory extend far beyond black hole thermodynamics, influencing our overall understanding of the universe's laws and how gravity interacts with quantum mechanics. As researchers continue to explore the mysteries of black holes, the concept of Hawking radiation will undoubtedly play a crucial role in advancing our understanding of the universe and the very nature of reality. The question of whether information can escape from a black hole is one of the most profound and perplexing challenges in modern theoretical physics. It arises from the implications of Hawking radiation and the information paradox that lies at the intersection of quantum mechanics and general relativity. According to general relativity, once an object crosses the event horizon of a black hole, it is thought to be lost forever. Yet, quantum mechanics suggests that information is never truly lost, creating a fundamental conflict that could change our understanding of the cosmos itself. However, the concept of information preservation in quantum mechanics implies that information cannot simply vanish. When Stephen Hawking proposed his theory of radiation emitted by black holes, he suggested that this radiation did not carry any information about the matter that had fallen into the black hole. This created a paradox. If a black hole could evaporate entirely due to Hawking radiation, what would happen to the information locked inside the objects and matter that crossed its event horizon? The apparent disappearance of this information would directly contradict a fundamental principle of quantum mechanics, the law of information conservation. In quantum mechanics, it's established that information must always be preserved, no matter the circumstances. Over the years, various researchers have grappled with this dilemma, exploring a range of potential solutions to this paradox. One compelling possibility is that the information might not be lost after all, but rather encoded within the Hawking radiation itself. While it may not be immediately accessible, it is theorized that over time, the radiation could carry subtle traces that reveal the states of the matter that fell into the black hole. These features, though hidden at first, might eventually be deciphered as the black hole continues to evaporate. This theory raises intriguing questions about the very nature of the radiation and whether it can hold the key to understanding the ultimate fate of the information that once existed inside the black hole. Another proposed resolution to the information paradox comes from the holographic principle, a groundbreaking idea in theoretical physics. According to this principle, all the information contained within a volume of space could be encoded in a lower dimensional theory on the boundary of that space. In this context, the event horizon of a black hole could act as a kind of boundary, storing information in two-dimensional form. This would mean that even though the matter is trapped inside the black hole, the information could still, in theory, be retrieved from the event horizon itself, offering a potential solution to the puzzle of how information escapes a black hole. As physicists continue to explore these and other possibilities, the debate surrounding information and black holes remains far from settled. Despite the emergence of promising theories, no conclusive answers have been found yet. The intersection of black hole physics and the mystery of information conservation holds the potential for groundbreaking insights into the very fabric of the universe itself. Primordial black holes, a fascinating class of cosmic objects, may play a pivotal role in answering some of the most profound questions in cosmology. These black holes are thought to have formed in the earliest moments after the Big Bang, unlike stellar black holes that emerge from the collapse of massive stars. Instead, primordial black holes could have resulted from density fluctuations during the universe's rapid expansion, causing regions of intense gravitational pull where matter collapsed into black holes of various sizes. What makes primordial black holes especially intriguing is their potential to span a vast range of masses. Some may be as small as an atom, while others could be as massive as the sun, or even far greater. The mere existence of these objects could offer valuable insights into the origins of the universe, including the elusive nature of dark matter. If primordial black holes exist, they could account for at least some of the missing mass in the universe, potentially solving one of cosmology's greatest mysteries. To detect primordial black holes, scientists rely on indirect methods, as these objects do not emit light in a way that makes them easily observable. Instead, researchers focus on the gravitational effects they might have on nearby matter. For example, if primordial black holes exist in sufficient numbers, they could contribute to phenomena like gravitational lensing, where their immense gravitational fields bend light from more distant objects. Additionally, their gravitational influence could alter the orbits of stars within galaxies, providing further clues about their presence. Some theories even propose that primordial black holes could produce detectable signals, such as gravitational waves, if they were to collide or interact with other celestial bodies. Despite ongoing efforts, the existence of primordial black holes remains unconfirmed. Their elusive nature continues to challenge scientists, yet their potential significance for understanding the early universe and the mysteries of dark matter keeps researchers searching for evidence. As the search continues, the mystery of primordial black holes remains a tantalizing possibility in the quest to unlock the secrets of the cosmos. However, they remain a subject of considerable theoretical interest and active research. Observations from gravitational wave detectors, cosmic microwave background studies, and analyses of galaxy formation may one day provide the concrete evidence needed to confirm whether these fascinating cosmic objects are truly woven into the intricate fabric of our universe. Binary black hole systems evolve through a series of complex interactions leading to their eventual merger. These systems consist of two black holes locked in a mutual gravitational orbit. Their evolution is influenced by several factors, including their initial separation, mass, and the environment surrounding them. The black holes can be formed from the remnants of massive stars in a binary star system, or can originate from the gravitational collapse of dense regions in the early universe. As the black holes orbit one another, they gradually lose energy through the emission of gravitational waves. According to the principles of general relativity, whenever massive objects like black holes accelerate, they create ripples in the fabric of space-time. These gravitational waves carry energy away from the system, causing the black holes to spiral closer together over time. The orbital period decreases, and the black holes accelerate toward one another. As the black holes draw nearer, approaching the event horizon of each, they undergo a complex process known as the final merger. This stage is marked by a rapid increase in the emission of gravitational waves, which can be detected by observatories like LIGO and Virgo. The merger itself occurs extremely quickly on cosmic timescales, resulting in a single, larger black hole, typically less massive than the combined mass of the two original black holes. This mass difference arises from the release of energy in the form of gravitational waves during the merger. After the merger, the newly formed black hole may go through a phase called ringdown. During this phase, the black hole settles into a stable state, emitting gravitational waves as it vibrates and sheds any remaining irregularities from the merger. Eventually, it reaches a stable configuration, becoming a single, more massive black hole. The study of binary black hole systems and their mergers has opened up an entirely new field of astrophysics, allowing scientists to probe fundamental aspects of gravity and space-time. The detection of gravitational waves from these events has provided direct evidence of black hole mergers, offering profound insights into the nature of black holes and their growth within the universe. When two galaxies, each hosting a supermassive black hole, approach one another, a captivating and complex series of events begins to unfold. Initially, the gravitational forces exerted by each galaxy strongly influence the other. As the galaxies draw closer, their stars, gas, and dust begin to interact. This interaction can trigger rampant star formation, igniting new stars as gas clouds collapse under the immense pressures created by these encounters. As the galaxies merge, their supermassive black holes also migrate toward one another, drawn by the gravitational pull of their respective fields. Over time, these black holes can exchange energy with their surrounding stars and gas, gradually losing energy and spiraling inward. This process can lead to the creation of a binary black hole system, where the two supermassive black holes orbit one another closely. Eventually, these black holes may reach a point where they can no longer resist the pull of gravity. As they close in, they merge into a single, even more massive black hole, releasing colossal amounts of energy in the process. This final merger generates gravitational waves, ripples in the very fabric of space-time that can be detected by observatories here on Earth. These waves provide valuable information about the properties of the black holes and the dynamics of their merger. The aftermath of such a colossal collision can reshape the galaxies involved. The newly merged black hole will influence the orbits of stars and gas in the resulting galaxy, leading to further interactions and possibly triggering new periods of star formation. This entire process exemplifies the intricate dance of gravity at work in the universe, showcasing how even the most massive structures can come together and dramatically transform. Quasars, or quasi-stellar objects, are among the brightest and most energetic phenomena in the universe, intimately connected to supermassive black holes. When a supermassive black hole is surrounded by a significant amount of gas and dust, it can create a massive accretion disk where material spirals inward due to the black hole's powerful gravitational pull. As this material accelerates and heats up, it emits an intense amount of energy, producing the luminosity characteristic of quasars. The energy emitted by a quasar can outshine entire galaxies, making them observable even at great distances. Quasars are often found in the early universe, offering a glimpse into the conditions billions of years ago. These extraordinary objects serve as important cosmic beacons, helping scientists understand the growth and evolution of supermassive black holes and their host galaxies over cosmic time. Quasars, some of the most captivating and extreme phenomena in the universe, exhibit behaviors that can vary dramatically. Some are highly variable in brightness, signaling dynamic changes in the accretion processes occurring around supermassive black holes at their centers. Others display powerful jets shooting out into the vastness of space, propelled by the intense magnetic fields and rotational forces surrounding these black holes. These jets can extend across light years, influencing their environments in profound ways. They can impact star formation rates in nearby galaxies, and even alter the intergalactic medium, which is the sparse material filling the vast stretches of space between galaxies. Research into quasars is pivotal, not just for mapping the distribution of supermassive black holes throughout the cosmos, but also for offering profound insights into the processes governing galaxy formation and evolution. By studying these enigmatic objects, scientists unlock the mechanisms behind the growth of black holes and how they interact with their surrounding environments. This knowledge, in turn, gives us a deeper understanding of the universe's history, revealing the intricate web of cosmic events that have shaped the cosmos as we know it today. The story of the universe's birth takes us back to a time immediately following the Big Bang, during what is known as the inflationary epoch. In this brief yet crucial moment, the universe expanded at an incomprehensible rate, growing exponentially in less than a fraction of a second. This rapid inflationary period, theorized to be driven by the inflaton field, stretched the very fabric of space-time itself, causing the universe to balloon by a staggering number of orders of magnitude. This extraordinary expansion smoothed out any irregularities that existed in the universe's early stages, laying the foundation for the large-scale structures that we observe today. One of the most significant consequences of this inflationary phase was the creation of quantum fluctuations, tiny variations in the density of matter and energy. These minuscule fluctuations would eventually serve as the seeds for all the galaxies, stars, and other cosmic structures that would populate the universe. As the universe continued to expand and cool, these fluctuations grew under the influence of gravity, gradually forming the intricate cosmic web that makes up the observable universe. The concept of inflation not only helps to explain the large-scale uniformity of the universe, but also provides a framework for understanding its ultimate fate. It raises profound questions about the nature of the universe's energy content, as well as the dynamics of its expansion. While many aspects of this theory are still under investigation, inflation remains one of the central pillars in the quest to understand our origins. One of the most perplexing and enduring mysteries in modern physics is the asymmetry between matter and antimatter in the observable universe. According to the standard models of cosmology, the Big Bang should have produced equal amounts of both matter and antimatter. However, observations suggest a stark contrast. The universe appears to consist almost entirely of matter, with very little antimatter detectable anywhere nearby. This imbalance presents one of the biggest puzzles in understanding the cosmos. One leading theory to explain this discrepancy is a phenomenon known as baryogenesis. According to this hypothesis, specific conditions in the early universe favored the production of matter over antimatter. More precisely, tiny differences in how particles and their corresponding antiparticles interacted may have led to a slight excess of baryons, particles like protons and neutrons that form the building blocks of atomic nuclei. A key aspect of this theory revolves around the violation of charge parity symmetry, or CP violation. This principle asserts that the laws of physics should be identical when particles are swapped with their antiparticles and when spatial coordinates are inverted. However, experiments have shown that certain weak force interactions behave differently when involving particles as opposed to their antiparticles. This subtle asymmetry might have been enough to tip the scales in favor of matter in the early universe, leading to the creation of the material that makes up everything we observe today. Another factor that may have contributed to this imbalance is the high-energy environment of the Big Bang itself. As the universe expanded and cooled, any antimatter produced during this time would have quickly annihilated with matter, leaving behind only a small surplus of matter. This leftover matter eventually coalesced to form the stars, galaxies, and other structures that populate our universe, offering the visible cosmos we see today. Together, these theories, the rapid inflationary expansion of the universe, the generation of quantum fluctuations, and the baryogenesis process, offer a glimpse into the dynamic, complex processes that have shaped the cosmos over billions of years. As scientists continue to probe these mysteries, they edge closer to unlocking the fundamental principles that govern the nature of the universe itself. Studies continue to delve into the fascinating question of matter-antimatter asymmetry, with experimental physics and observational data offering crucial insights into this fundamental mystery of our universe. This question has implications not just for our understanding of matter, but for the very essence of existence itself. One of the deepest questions explored by scientists and philosophers alike concerns the nature of time in the cosmos. Unlike the predictable linear flow of time that we experience daily, time in the universe behaves in ways that challenge our very perceptions of it. In the realm of astrophysics, time is not an independent, unchanging backdrop, but something that is intricately woven into the fabric of the cosmos. According to Albert Einstein's groundbreaking theory of general relativity, time is not an absolute and immutable entity. Instead, it is tightly intertwined with space, forming a dynamic, four-dimensional continuum that we call space-time. This interconnection of space and time has profound consequences, one of the most fascinating being the way time behaves in the presence of massive objects. In regions with intense gravitational fields, such as near a black hole, time doesn't simply march forward at a steady pace. Instead, time slows down significantly in comparison to areas far removed from such gravitational influences. This effect, known as time dilation, has been experimentally confirmed by comparing the ticking of atomic clocks at different altitudes, where higher altitudes, further from the Earth's gravitational field, register faster time than clocks positioned closer to the planet's surface. This discovery isn't just a theoretical concept, but a real-world phenomenon that has been observed and measured. For an observer close to a massive object, like a black hole, time would appear to pass much more slowly compared to someone situated far away. This realization fundamentally alters our perception of time, suggesting that it is far more malleable than we ever imagined. It stretches and contracts in response to the physical forces and conditions around it, creating a dynamic flow that can differ drastically from one location to another. Beyond the way time behaves, another compelling feature of its nature is the direction in which it flows. Often referred to as the arrow of time, this concept is tightly linked to the second law of thermodynamics. This law tells us that entropy, or the degree of disorder in a system, tends to increase over time in isolated systems. It is this increase in entropy that gives time its apparent directionality, allowing events to unfold in a sequence that moves forward and never backward. This one-way progression from a state of order to a state of disorder provides the arrow that we feel as time moving forward. Yet, on a grander scale, this concept becomes murky. Some cosmological theories propose that the universe could undergo cycles of expansion and contraction, challenging the idea of time having a definitive beginning or end. In such models, the flow of time might not follow the familiar linear path we associate with our day-to-day lives. This raises profound questions. Does time itself have an origin? Will it eventually come to an end, or does it stretch on forever in a cyclical pattern that we cannot yet comprehend? As our understanding of the universe deepens, time remains one of the most profound and elusive mysteries. Our scientific exploration continues, revealing more layers of complexity and paradox that defy our most basic intuitions. Whether it's through the durations of cosmic events or the puzzling properties explored by theoretical physicists, the nature of time is a frontier of knowledge, offering glimpses into the fundamental workings of the cosmos. Its study may ultimately reveal insights into the universe's structure and the laws that govern everything, from the tiniest particles to the largest galaxies. At the heart of our current understanding of the physical world lies the interplay of four fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. These forces govern everything from the motion of planets to the interactions of subatomic particles. Yet, even with our detailed understanding of these four forces, there remains the tantalizing possibility that other undiscovered forces exist beyond these known entities. Many scientists have speculated about the existence of additional forces, and several theories and experiments are pushing the boundaries of what we know. One prominent line of inquiry arises from efforts to unify the fundamental forces, particularly within the frameworks of string theory and quantum gravity. These theories suggest that at deeper levels of reality, the four known forces and all particles might be interconnected in ways we have yet to uncover. As our ability to probe higher energy scales and more extreme conditions increases, it is possible that we may eventually detect these hidden forces, expanding our understanding of the universe even further. This quest for knowledge has sparked the imaginations of physicists around the world, who are driven by the possibility that we are only scratching the surface of what could be a much richer and more complex physical reality. As experiments push the limits of current technologies, we may soon discover that the laws of nature are even more mysterious and profound than we can currently imagine. The search for these unknown forces will likely be a key area of research in the years to come, with the potential to reshape our understanding of everything from the tiniest particles to the grand structure of the cosmos. Moreover, recent research into dark matter and dark energy has sparked widespread speculation about potential interactions that could involve forces yet to be discovered. Dark matter, which accounts for a significant portion of the universe's total mass, continues to elude detection because it does not interact with electromagnetic forces in any detectable way. Unraveling the properties of dark matter could point toward new types of interactions or forces that may not align with the ones we currently understand. Similarly, dark energy, which is believed to be driving the accelerated expansion of the universe, remains an enigma. Despite its profound effect on the cosmos, our grasp of dark energy's origins and nature is still in its infancy, fueling theories that it might be related to entirely new kinds of forces that we have yet to encounter. Beyond theoretical pursuits, experimental physics continues its quest to identify anomalies that might suggest the existence of new forces or particles. High-energy particle collisions, such as those conducted at the Large Hadron Collider, hold the potential to reveal deviations from what we expect, which could indicate the presence of previously unknown forces or particles, thus expanding our fundamental framework of physics. While the confirmation of additional forces remains elusive, the landscape of physics is in a state of constant evolution. Ongoing research and exploration may, in the future, uncover new fundamental forces that could reshape our understanding of the universe in surprising and profound ways. These findings could fundamentally alter the trajectory of scientific thought and open up entirely new realms of possibility. The ultimate fate of the universe is another captivating topic, one shaped by the laws of physics and the universe's present conditions. Current cosmological models propose various potential outcomes, each determined by factors such as dark energy, cosmic expansion, and the overall density of the universe. One of the leading scenarios is known as the Big Freeze. In this model, the universe continues to expand indefinitely, driven by the influence of dark energy, a mysterious force that accelerates the cosmic expansion. As galaxies drift farther apart, they will eventually move beyond the observable horizon, rendering them inaccessible to any future interactions. Stars, too, will exhaust their fuel, leading to a gradual dimming of galaxies over vast timescales. Eventually, even black holes, the last remnants of stellar objects, will slowly evaporate through a process known as Hawking radiation. The end result will be a universe that is cold, dark, and sparsely populated, a place where matter and radiation are scattered thinly across a vast, uninhabited expanse. Another possibility is the Big Crunch. In this scenario, if the density of matter in the universe is sufficiently high, gravitational forces could eventually reverse the expansion, causing the universe to contract. This would lead to a collapse back into a singularity, where all matter and energy would be compressed into an infinitely dense point, much like the conditions that existed at the birth of the universe in the Big Bang. While current observations suggest that this scenario is unlikely, given the accelerated expansion, it remains a theoretical consideration. A more speculative idea involves the Big Rip, a scenario in which dark energy's repulsive effects intensify over time. If this happens, it could eventually tear apart galaxies, stars, planets, and even atomic structures. In this extreme outcome, all matter would be pulled apart, leading to a universe that ends in utter destruction just before the very fabric of space-time itself is disrupted. While such a fate seems improbable, it remains an intriguing area of theoretical investigation. Despite these diverse scenarios, the ultimate fate of the universe remains uncertain. Ongoing observations and theoretical research continue to refine our understanding, potentially revealing unexpected insights into the cosmos' distant future. Each possibility challenges our existing understanding of physics and evokes awe at the complexity and vastness of the universe. The concept of the heat death of the universe presents another chilling outcome. This scenario describes a state of maximum entropy, where the universe reaches a condition of uniform temperature and energy distribution. According to the second law of thermodynamics, entropy, or disorder, naturally increases over time in a closed system. As the universe ages, processes like star formation, nuclear fusion, and the gradual cooling of celestial bodies all contribute to rising entropy. Initially, the universe will continue to expand, driven by dark energy. Stars will burn through their nuclear fuel over trillions of years, and as they die, they will transform into red dwarfs, neutron stars, or black holes. While some new stars may form from leftover gas and dust, this process will become increasingly rare as the available material for star formation becomes depleted. Over incredibly long timescales, even black holes will evaporate due to Hawking radiation, a quantum process predicted by physicist Stephen Hawking. This radiation allows black holes to emit particles and lose mass, eventually leading to their demise. As the universe cools, it will be populated primarily by weakly interacting particles, radiation, and the remnants of dead stars. This dark environment will become colder and colder, approaching absolute zero. All available energy will become evenly distributed, and with no thermal gradients to enable work or energy transfer, no thermodynamic processes will occur. Matter and energy will be spread thinly across an unimaginably vast cosmos, resulting in a lifeless and stagnant universe, thus epitomizing the heat death scenario. Though this outcome lies trillions of years in the future, it highlights the inevitable decline of cosmic dynamics, emphasizing the profound relationship between time and entropy. The universe's eventual fate will be one of stillness, where complexity fades away and any order that once existed is lost in an eternal expanse of uniformity. Finally, the question of what came before the Big Bang is one of the most profound and enduring mysteries in cosmology. According to the Big Bang theory, the universe began as a singularity, a point of infinite density and temperature. However, what existed prior to this event, or whether the concept of before even makes sense in the context of time as we know it, remains a deeply debated topic. As we continue to explore the cosmos and push the boundaries of our understanding, the quest to answer these questions remains one of the most exciting and fundamental endeavors in modern science. However, because general relativity breaks down at the singularity, our current understanding of the universe struggles to describe conditions that existed before it. As a result, scientists have proposed various hypotheses to explore what might have existed prior to the Big Bang. One of the most fascinating ideas comes from the concept of a multiverse, which suggests that our universe is just one among many, potentially an infinite number, each governed by its own set of physical laws and constants. In this view, the Big Bang could be seen as a pivotal moment in the life cycle of one universe among many, a transition from the collapse or interaction of other structures within a broader cosmic landscape. Another compelling theory comes from the cyclic model of the universe. According to this idea, the cosmos undergoes an infinite series of expansions and contractions. Before our current universe emerged, there could have been a previous one that collapsed in on itself in a big crunch, only to explode once again, leading to another expansion into the universe we observe today. Each cycle would wipe away the specifics of the preceding universe, but preserve certain universal physical laws, creating an eternal cycle of rebirth. This theory paints a picture of a universe in constant flux, born and reborn over and over. Then there are the quantum gravity theories that suggest our traditional understanding of time may not even apply to the state of the cosmos before the Big Bang. According to certain interpretations of loop quantum gravity, the universe could have experienced a bounce rather than an explosion from a singularity. This would mean that what came before the Big Bang existed in a phase beyond our current understanding of time and space, a realm where time itself may have been irrelevant. The question of what came before the Big Bang remains an area of deep speculation, pushing the limits of our theoretical frameworks and calling for further exploration, both theoretical and observational. As scientists probe these profound mysteries, they are forced to confront the very nature of reality, existence, and time itself, all while uncovering secrets that might forever alter our understanding of the cosmos. The seemingly perfect conditions that allow life to exist in the universe have led to the concept of fine-tuning. This idea suggests that various physical constants and laws are set within an extraordinarily narrow range, allowing for the formation of stars, galaxies, planets, and ultimately, life itself. Several factors contribute to this remarkable arrangement, which has sparked both scientific inquiry and philosophical debate. A prime example of fine-tuning can be found in fundamental constants, such as the strength of gravity, the electromagnetic force, and the weak and strong nuclear forces. Each of these constants plays a crucial role in shaping the structure and behavior of matter. For instance, if the strength of gravity were even slightly weaker, galaxies, stars, and planets might never have formed. On the other hand, if gravity were stronger, stars would burn out too quickly, leaving no time for life to develop. Such delicate balances suggest that life as we know it depends on a precise set of conditions, a coincidence so remarkable that it raises profound questions about the very nature of existence. Several explanations have been proposed to address this fine-tuning. One such explanation is the anthropic principle, which argues that we are able to observe and question the universe's characteristics because we exist within it. According to this view, the universe must accommodate observers like us, thus leading to the conditions we observe today. However, this principle does not fully explain why those conditions exist in the first place. Another intriguing perspective comes from the multiverse theory, which suggests that our universe is just one of many, each with different physical constants and laws. In this view, if a vast number of universes exist, Each with a unique set of properties, it is not surprising that at least one would possess the right conditions for life. From this standpoint, we find ourselves in a universe that supports life simply because it is one of the lucky few that meets those conditions. The fine-tuning of the universe continues to raise essential questions about the nature of existence and the underlying principles that govern reality. As research into the cosmos's fundamental laws deepens, our understanding of why the universe appears so perfectly calibrated for life will undoubtedly remain both a scientific pursuit and a source of wonder. Meanwhile, astronomers have discovered thousands of exoplanets through a variety of detection methods, yet many remain elusive due to the limitations of our current technology. One significant category of undetected exoplanets includes those that are smaller and less massive than Earth. Common detection techniques, such as the transit method and radial velocity measurements, are biased toward larger planets. These methods detect the gravitational effects of a planet on its parent star, and larger planets, due to their stronger gravitational pull, create more noticeable signals. As a result, Earth-sized or smaller exoplanets are harder to detect, meaning that they may be rarer in our current datasets. Another class of exoplanets that has yet to be conclusively identified is the true Earth-like exoplanet situated within the habitable zone, often referred to as the Goldilocks zone. Although we've found candidates that may be rocky and temperate, many of these planets are still awaiting further observations to confirm their atmospheric compositions and surface conditions. The detection of transiting Earth-sized exoplanets in habitable zones is a rare event due to the precise alignment needed for transits to occur, combined with the vast distances separating us from potential candidates. As our technology advances, however, the number of exoplanets we discover, especially those that resemble Earth, will continue to grow, further expanding our understanding of the universe and the possibilities for life beyond our planet. Exoplanets, an elusive and captivating field of study, present an array of cosmic wonders, many of which stretch the very limits of our understanding of planetary systems. Among these strange and fascinating worlds are those that defy the conventional norms of planetary existence: rogue planets. These free-floating wanderers do not orbit any star and drift through the cosmos in isolation. Lacking the guiding light of a host star, they remain largely invisible to traditional detection methods. Their faintness presents a considerable challenge to astronomers, who must develop ever more sophisticated techniques to uncover their hidden paths across the universe. Some exoplanets fall into equally puzzling categories, such as gas giants residing in narrow, extreme orbits dangerously close to their stars. These planets could also elude detection, not only because of their size, but because their signatures are faint, camouflaged by the intense radiation and heat of their stellar companions. As these planets often lie in regions where observational data is hard to interpret, detecting them requires refining our tools and methodologies to unveil them from the cosmos. Perhaps the most enigmatic environments are dense star clusters, cosmic cities packed with stars whose gravitational forces interact in complex ways. In such crowded spaces, exoplanetary systems face a unique fate. They are more prone to planetary ejection. This high rate of planet displacement makes traditional detection methods less effective, presenting another challenge to researchers. However, with the rapid advancement of observational technology such as the future capabilities of the James Webb Space Telescope, we are on the cusp of discovering a broader array of exoplanets, unveiling previously hidden worlds that could offer a deeper understanding of planetary formation and, perhaps, the very essence of life beyond Earth. The quest to determine how common Earth-like planets are within the habitable zone of their stars remains one of the most thrilling frontiers of exoplanet science. Recent data, particularly from NASA's Kepler mission, has illuminated the vast potential of the cosmos. The habitable zone, the region around a star where conditions might allow liquid water to exist on a planet's surface, is a key parameter in determining whether a planet could potentially harbor life. Current estimates suggest that a significant portion of stars in our galaxy may host planets within their habitable zones. In fact, studies have shown that around 1 in 4 stars could have at least one planet situated in this life-friendly zone. With billions of stars in the Milky Way alone, this could mean the existence of hundreds of millions of potentially habitable planets scattered across the galaxy. However, the question of how many of these planets are truly Earth-like is more complex. While many of these planets may sit within the habitable zone, not all would offer conditions suitable for life as we know it. A planet's atmosphere, its geological activity, and the type of radiation it receives from its star are all crucial factors in determining whether it could support life. For instance, a planet may lie within the habitable zone, yet its atmosphere might be thick and toxic, making it uninhabitable. As we develop new observational technologies, the James Webb Space Telescope among them, we will gain unprecedented insight into the atmospheres and potential habitability of these distant worlds. With this data, researchers will be able to refine their models, providing a clearer picture of how common Earth-like planets truly are and whether they might one day host life. As we continue to look further into the stars, the possibility of discovering new life-sustaining environments becomes increasingly tantalizing. The search for Earth-like worlds continues to capture the imagination of scientists, pushing them toward what could one day be a profound discovery, the answer to the age-old question of whether humanity is alone in the universe. But not all exoplanets are friendly to life. Some are extreme, pushing the boundaries of what we consider possible. A striking example is WASP-17b, a gas giant situated about 400 light-years from Earth. This planet is renowned for its blistering close orbit around its star, completing a full revolution in under a single day. The intense heat from its proximity to its star causes its surface to reach unbearable temperatures, creating an atmosphere where gases are vaporized into the void. This world, as inhospitable as it is fascinating, offers an incredible laboratory for understanding the extreme conditions that exist on other planets. Another extreme example is HD 1088b, known as a lava planet. So close to its star that its surface remains perpetually molten, this planet is a hostile inferno with rivers of lava flowing across its landscape. The sheer temperature extremes on HD 1088b make it an uninhabitable world, but a valuable study in planetary formation. Understanding such worlds can offer vital clues about how planets are born, evolve, and perhaps even what makes them able or unable to support life. Then there is PHL 2483b, a world unlike any we know, with an atmosphere dominated by titanium oxide. This unusual chemical composition leads to temperature fluctuations that cause extreme weather patterns on the planet. The presence of titanium oxide plays a role in shaping the planet's weather, driving temperatures to stifling highs and making its climate a truly alien environment. The study of such extreme exoplanets challenges scientists to expand the boundaries of their imagination, offering them a rare chance to witness the spectacular range of planetary possibilities in the universe. Each of these extraordinary worlds adds to the vast growing tapestry of exoplanetary discovery, presenting both extraordinary challenges and opportunities for researchers striving to understand the full breadth of planetary diversity across the cosmos. In the vast expanse of the cosmos, TOI 2071b stands out as a striking example of an exotic super-Earth. This planet exhibits characteristics unlike anything we find in our own solar system. With its immense atmospheric pressure and potential volcanic activity, TOI 2071b presents a remarkable example of planetary extremes. Super-Earths like this one open a window into the diverse geologies and atmospheres that could exist across the universe. These planets challenge our understanding of what is possible, highlighting the tremendous diversity of planetary types beyond our familiar solar system. As astronomers continue to explore these worlds, they reveal much more than just strange landscapes. They provide valuable insights into the complex processes that lead to the formation and evolution of planetary systems. By studying planets like TOI 2071b, we can better understand how planets come into being, how they change over time, and how their environments might evolve under different conditions. This exploration deepens our knowledge of the universe and expands the horizons of what we think is possible in the cosmos. The search for biosignatures, the potential indicators of life, on exoplanets is an ongoing, multifaceted endeavor that combines advanced technology, innovative observational techniques, and theoretical modeling. Biosignatures are essentially markers of biological activity, and detecting them requires a deep understanding of the atmospheric and surface conditions of distant worlds. With an array of sophisticated methodologies at their disposal, scientists are exploring new ways to find life in the farthest reaches of space. One of the most promising techniques in the search for biosignatures is spectroscopy. This method involves analyzing the light that is emitted or absorbed by a planet's atmosphere. As an exoplanet passes in front of its host star, some of the star's light filters through the planet's atmosphere. This light is altered by the gases present in the atmosphere, and by examining the resulting spectral signatures, scientists can identify molecules commonly associated with life, such as oxygen, methane, carbon dioxide, and water vapor. The presence of these gases, especially when found in specific ratios, may indicate biological processes at work. If these gases exist in disequilibrium, meaning their concentrations are not balanced, it could suggest that biological activity is actively producing and consuming them, a key sign of life. Another method for detecting biosignatures is direct imaging, which allows astronomers to capture the light from the exoplanets themselves, instead of relying solely on the light from their parent stars. Using advanced telescopes equipped with sophisticated coronagraphs or star shades, scientists can block out the overwhelming light from the star, enabling them to observe the faint light from the exoplanet. This technique provides critical details about the planet's atmosphere and surface conditions, offering more clues about the presence of life. The potential for detecting biosignatures is poised to grow even further with missions such as the James Webb Space Telescope, which will employ its infrared capabilities to explore the atmospheres of Earth-like planets in unprecedented detail. By analyzing the chemical compositions and temperature profiles of these distant worlds, scientists hope to uncover patterns that point to biological activity. In addition to observational techniques, theoretical modeling and simulations play a crucial role in the search for life. These models help scientists predict what types of biosignatures might emerge under various environmental conditions, providing a framework for interpreting observational data. The more we understand about how biosignatures form and what factors influence their production, the better equipped we will be to detect them in the future. As technology advances, so too does our capacity to explore and understand the complex ecosystems that may exist on exoplanets. However, searching for microbial life on other worlds comes with significant challenges. Perhaps the greatest obstacle is the immense distances involved. Many potentially habitable exoplanets are located light years away, making direct observation a complex and difficult task. Even with advanced technology, detecting signs of life on planets that lie so far beyond our reach is not an easy feat. Closer targets, such as Mars or the icy moons of Jupiter and Saturn, present their own set of difficulties, with the remoteness of these worlds complicating the collection and analysis of samples. Another significant hurdle is the vast range of environments where life might exist. On Earth, extremophiles, organisms that thrive in extreme conditions, have been found in places like deep-sea hydrothermal vents, polar ice caps, and acidic hot springs. These organisms suggest that life might be able to adapt to similarly harsh environments elsewhere. But the challenge lies in knowing what types of life could exist under conditions we have not yet fully understood, making it difficult to design effective instruments and experiments to search for life on alien worlds. This uncertainty complicates the task of determining which biosignatures to look for. Moreover, distinguishing between biological and non-biological sources of certain gases is an intricate process. For example, methane and oxygen can be produced both biologically and through non-biological abiotic processes. To confirm that a biosignature is truly indicative of life, scientists must analyze the context in which these gases are found. A biosignature must not only be detectable, but also clearly attributed to biological activity. This makes the process of validating potential biosignatures far more complex, requiring careful scrutiny and a deep understanding of the environments in which they are found. Despite these challenges, the search for life beyond Earth remains one of the most exciting frontiers of modern astronomy. As our technology advances and our understanding of exoplanetary systems deepens, we are inching closer to uncovering the secrets of distant worlds. Each discovery brings us one step closer to answering one of humanity's oldest questions: are we alone in the universe? The journey to find life on other planets may be long and filled with obstacles, but it is a journey that continues to inspire and push the boundaries of what we know about the cosmos. Exploring the question of microbial life beyond Earth comes with a series of immense challenges, particularly in sample collection and in situ testing. Missions like the Mars rovers have encountered significant logistical hurdles when trying to obtain samples from beneath the surface of planets and moons. Collecting samples from subsurface oceans on moons like Europa and Enceladus presents its own set of obstacles. The depth and harsh conditions of these regions make sample extraction a complicated and delicate operation. Adding another layer of complexity is the need to ensure that instruments are capable of detecting potential alien life forms while avoiding contamination from Earth-based microbes. This dual challenge, gathering samples and preventing cross-contamination, underscores the difficulties that researchers must overcome in the search for extraterrestrial life. As our technology advances, these hurdles may eventually be overcome. With every mission we send beyond Earth, we come closer to answering the age-old question: are we alone in the universe? If alien life does exist, it might appear vastly different from what we understand as life on Earth. For example, the biochemistry of extraterrestrial organisms might deviate significantly from what we consider normal. While all known life forms on Earth are carbon-based, alien life might rely on entirely different elements like silicon, or even combinations of elements that are unknown to us. Such a fundamental shift could give rise to organisms with completely new forms, structures, and functions, challenging our very definitions of what constitutes life. The environments in which these life forms evolve will also play a critical role in shaping them. Life on Earth thrives in a relatively narrow band of temperature and pressure. However, extraterrestrial organisms might exist in conditions far more extreme than we can imagine. For instance, they could be living on planets with high radiation, extremely low temperatures, or in atmospheres rich in gases like methane or ammonia. Their adaptations to these environments might be extraordinary: protective outer shells, unique metabolic processes, or ways to harness the local chemical resources for energy. Such adaptations could make extraterrestrial life seem utterly alien to us, from their appearance to their behavior. Even the methods by which these organisms reproduce and communicate could challenge our terrestrial expectations. On Earth, many organisms rely on DNA to pass on genetic information. But extraterrestrial life might use entirely different mechanisms of reproduction, potentially even ones that don't involve cellular division. Similarly, alien species could communicate in ways that don't rely on sound or light. Instead, they might exchange information using chemical signals, electromagnetic fields, or other methods that we have yet to conceive of. Such discoveries would force us to rethink our entire understanding of biology, social structures, and ecosystems, offering a broader view of life's potential forms. The search for alien life also leads us to examine exoplanets, worlds beyond our solar system that might harbor environments conducive to life. As we explore these distant planets, we uncover the possibility of unique ecosystems and life forms that push the boundaries of our biological understanding. These investigations not only spark our curiosity, but also prompt us to consider the infinite possibilities of life in the universe, challenging the limitations of Earth-based biology. Within our own solar system, several intriguing locations have captured the interest of scientists in the hunt for life. Europa, one of Jupiter's moons, is a prime candidate. Beneath its thick icy crust, Europa is believed to harbor a vast ocean of liquid water, kept warm by tidal heating from gravitational interactions with Jupiter. This subsurface ocean could provide an environment where microbial life might exist, supported by chemical nutrients from the moon's rocky seafloor, similar to the extremophiles that thrive in Earth's deep ocean vents. Another moon that holds promise is Enceladus, one of Saturn's smaller moons. Enceladus is home to geysers that spew water vapor and organic compounds into space, hinting at the presence of a subsurface ocean. These plumes, along with the molecules detected within them, make Enceladus a key target in the search for life. The interaction between the moon's ocean and its rocky core could create conditions ideal for life to flourish, further fueling scientific interest. Yet, the search for microbial life continues to center on Mars, which remains one of the most promising sites for discovery. Evidence suggests that liquid water once flowed abundantly across the Martian surface, and there are still places where subsurface water might exist today. Recent findings, such as the discovery of recurring slope lineae, features that could indicate briny water activity, have renewed interest in the potential for life on the red planet. Ongoing missions are focused on analyzing Martian soil and ice samples for biosignatures, which could provide critical insights into the possibility of past or present life on Mars. As our exploration of these moons, planets, and distant exoplanets continues, it is clear that the search for microbial life is just beginning. Each mission, each discovery, brings us closer to understanding the broader question of life's existence beyond Earth, and the universe may be far more diverse than we ever imagined. Titan, Saturn's largest moon, offers a fascinating and distinct possibility for the existence of life. Though its surface conditions starkly contrast those of Earth, Titan's dense atmosphere and its lakes of liquid methane and ethane present a chemical complexity unlike any other in our solar system. Scientists believe that beneath its icy crust, Titan might harbor a subsurface ocean, a potential sanctuary for forms of life that are entirely alien to our current understanding. This possibility pushes the boundaries of what we consider habitable and highlights the essential need for ongoing exploration. Each unique environment across our solar system presents new opportunities to broaden our search for life beyond Earth. In the search for extraterrestrial intelligence, distinguishing between natural phenomena and potential technosignatures requires an advanced blend of observational techniques, theoretical frameworks, and meticulous data analysis. A technosignature is essentially any signal or structure that points to the presence of intelligent life. This could manifest as unusual emissions of electromagnetic radiation, intricate light patterns, or artifacts in space that appear engineered rather than naturally occurring. One of the primary tools for identifying technosignatures is spectroscopy. This technique involves analyzing the light emitted or absorbed by celestial bodies. Natural phenomena usually exhibit a predictable spectrum that corresponds with known atomic and molecular processes. However, when the observed spectrum deviates from this expected pattern, especially by displaying specific frequencies not attributable to natural sources, it may signal technological activity. For instance, a persistent, regular signal that breaks away from the background noise could suggest a technological origin, much like radio transmissions on Earth. Moreover, astronomers now employ machine learning algorithms and statistical techniques to process vast amounts of astronomical data. These sophisticated computational methods help identify anomalies that stand out from the usual noise of cosmic signals. By comparing these anomalies with a database of known natural phenomena, researchers can isolate the more unusual signals, focusing on those that might point to extraterrestrial technology. The context in which these signals are detected is just as important. If a strong signal emerges from a region of space with no natural sources, it increases the likelihood that the signal is, in fact, a technosignature. The search for signs of intelligent life in the universe is a collaborative effort that unites astronomers, astrophysicists, and other scientists from various disciplines. Together, they create sophisticated models to differentiate between natural cosmic processes and possible indicators of extraterrestrial life. This ongoing pursuit represents humanity's profound curiosity about our place in the cosmos and the tantalizing prospect of discovering other civilizations. In contrast to these focused searches, the vast cosmic voids provide a different kind of wonder. These enormous, largely empty regions of space contain far fewer galaxies compared to other areas of the universe. They can span tens of millions, even hundreds of millions of light years and take on irregular shapes. Cosmic voids are a defining feature of the large-scale structure of the universe, where galaxies form interconnected filaments and clusters, resembling a massive cosmic web. The emptiness of these voids becomes even more striking when contrasted with the densely packed, galaxy-rich regions surrounding them. The formation of these voids is a key aspect of the universe's evolution and the role gravity has played in shaping its structure. In the early universe, matter was unevenly distributed, with slight fluctuations in density. These density variations caused gravity to pull matter together, eventually forming galaxies and clusters. As these dense regions of matter coalesced, they created areas of lower gravitational attraction in the surrounding spaces, leading to the formation of the vast voids that we observe today. These empty expanses continued to expand as the universe itself grew, further accentuating the contrast between the dense and sparse regions. The interaction between dark matter and ordinary, baryonic matter has played a critical role in the creation of cosmic voids. Dark matter, though invisible, forms the framework of the cosmic web, while baryonic matter, which makes up stars and galaxies, tends to clump in these denser regions. This separation deepens the gap seen in voids, further distinguishing them from the crowded cosmic filaments and clusters. Understanding cosmic voids is crucial to gaining insights into the fundamental nature of the universe. They offer a unique perspective on the influence of dark energy and the gravitational forces that govern the cosmos. Far from being empty spaces, these voids reveal a delicate interplay of cosmic forces that has shaped the universe into the intricate and complex structure we observe today. Exploring these vast and seemingly empty expanses of the cosmos allows astronomers and physicists to piece together the intricate narrative of the universe's formation and evolution. At the heart of this vast canvas lie the galaxy filaments and walls, key components of the large-scale structure of the universe. These elements form a complex three-dimensional web that traces the distribution of galaxies and dark matter across unimaginable distances. This cosmic web is not a random scattering of objects, but a delicate arrangement defined by vast, elongated structures called filaments, which stretch across hundreds of millions of light years, connecting clusters and superclusters of galaxies. Yet, interspersed between these interconnected filaments are vast voids, regions of near-total emptiness that contribute to the universe's intricate pattern. It is in these voids that the universe's quiet beauty is often found. The distribution and organization of these structures owe much to the gravitational forces at play throughout the cosmos. In the early universe, matter was not evenly distributed. Quantum fluctuations during the inflationary period led to subtle irregularities in density, which would go on to shape the universe's grand structure. Over billions of years, these slight variations in density became more pronounced, causing certain areas to attract more matter via gravitational pull. As gas and dark matter amassed in these regions, they formed the dense pockets we now recognize as galaxy clusters. These clusters often appear at the intersections of filaments, marking the gravitational collapse of matter within an expanding universe. The result is a hierarchical structure where larger cosmic features form first, followed by the creation of smaller ones. One of the most fascinating aspects of this process is the formation of galaxy walls, or sheets. These are large, thin slices of space containing a significant concentration of galaxies. Typically, they surround the denser regions of filaments, where galaxies congregate in dense, organized structures. The interactions among these galaxies within the walls can lead to the creation of new cosmic structures, such as galaxy groups and clusters, which further shape the layout of the cosmic web. Large-scale observational surveys, like the Sloan Digital Sky Survey, have been instrumental in revealing the continuity of these filaments and walls, while also showing their relationship with dark matter. Computer simulations have been able to model the growth of these structures over time, illustrating how the universe will continue to expand and how filaments will become more pronounced as galaxies move toward them under the influence of gravitational attraction. Understanding how these cosmic structures are organized does more than just clarify the current layout of matter in the universe. It offers insight into the future trajectory of our cosmos. The interactions between galaxies, the pulling force of gravity, and the continued expansion of the universe will continue to mold the cosmic web in ways we are only beginning to grasp. Turning our focus to individual galaxies, the rotation of these massive cosmic entities is one of the most striking features of their evolution. This rotation is primarily driven by the gravitational interactions between visible matter, such as stars and gas, and the elusive dark matter that permeates every galaxy. When galaxies form, the gravitational pull of the accumulating mass causes surrounding material to collapse into a rotating disk-like structure. This motion is an example of the conservation of angular momentum, a principle stating that an object in motion will maintain its angular velocity unless acted upon by an external force. As gas and dust collapse to form stars, they spiral inward, rotating around the galaxy's center. This leads to the distinctive spiral shape of many galaxies, where stars on the outer edges often rotate at incredibly high speeds. However, this rotation is not uniform. The speed at which different parts of a galaxy rotate varies, depending on the distribution of mass within the galaxy. Gravitational forces ensure that stars farther from the galactic center do not simply drift away, but rather remain bound in orbit around the galaxy's core. One of the most remarkable aspects of galactic rotation is the impact of dark matter. Observations have revealed that the outer regions of galaxies rotate much faster than expected, based on the visible matter alone. This discrepancy suggests that there is unseen mass, dark matter, contributing to the galaxy's gravitational field. Though it cannot be directly observed because it does not emit light, dark matter is believed to exist in a vast halo around galaxies. This halo extends far beyond the visible structures of galaxies, and its gravitational influence plays a crucial role in shaping the galaxy's rotation curve. The presence of dark matter has fundamentally altered our understanding of galactic dynamics. It explains why galaxies rotate faster than the visible mass would suggest, leading to the discovery of dark matter as a pivotal force in the universe's structure. This unseen force also affects the long-term evolution of galaxies. When galaxies interact, whether through collisions or mergers, their rotational dynamics can change, leading to the formation of new structures and the reshaping of existing ones. Studying these rotational movements gives astronomers invaluable insight into the distribution of mass within galaxies, the presence of dark matter, and the gravitational forces that drive galaxy evolution. As galaxies continue to evolve throughout cosmic history, they undergo a remarkable transformation. These processes are driven by various factors, including gravitational interactions, star formation, and the pervasive influence of dark matter. In the earliest stages of the universe, shortly after the Big Bang, small fluctuations in density marked the beginning of cosmic structure formation. The first galaxies were relatively small, composed mostly of gas. Over time, gravitational forces caused these gas clouds to collapse, forming the first stars, which ignited the universe and set in motion the process of galaxy evolution. During the period known as cosmic noon, roughly a few billion years after the Big Bang, galaxies were particularly active, giving rise to a burst of star formation. This period saw galaxies creating massive numbers of stars, leading to a significant increase in their size and complexity. As galaxies continued to evolve, this rapid star formation helped to shape the galaxies we observe today, setting the stage for the diverse array of structures and features that define the universe. The ongoing study of galaxy formation and evolution remains one of the most exciting frontiers in our understanding of the cosmos. However, this vibrant era of star formation eventually slowed as the essential gas and dust for creating new stars began to deplete. As a result, the rate at which stars formed in these galaxies dropped, signaling a shift from an active to a more passive phase of evolution. Gravitational interactions between galaxies also significantly shape their development. Galaxies can collide and merge, triggering profound transformations in their structure and star formation activities. These cosmic encounters can reignite bursts of star formation, giving birth to larger galaxies. The aftermath of these mergers produces a vast array of galaxy shapes and sizes, from elliptical galaxies formed by the collision of spiral galaxies to more irregular configurations. The influence of dark matter deepens the complexity of this evolutionary tale, acting as the invisible scaffold that governs the gravitational behavior of cosmic structures. Dark matter weaves a hidden thread through the universe's ongoing evolution. In the more recent chapters of this cosmic drama, the evolution of galaxies has been increasingly influenced by environmental factors. Galaxies nestled within dense clusters often undergo interactions that strip away their gas, further stalling their star formation. This process stands in stark contrast to galaxies in more isolated regions where they continue to evolve at a slower pace, preserving their gas and maintaining star formation for extended periods. Today, many galaxies have matured into states dominated by older stars, having transitioned from their chaotic star-forming youth to a quieter, more stable phase. Yet, even in this calmer stage, their journey is far from over. They continue to evolve, engaging with their environments in the ever-changing dynamic landscape of the cosmos. Magnetic fields, though often overlooked, play a crucial and far-reaching role in shaping the universe's structures. From the formation of galaxies to the behavior of interstellar gas and dust, these fields influence a wide array of cosmic phenomena. Present on scales ranging from the tiny regions within stars to the vast stretches of intergalactic space, magnetic fields arise primarily from the motion of charged particles, such as electrons within conductive materials like plasma. This motion generates magnetic fields through a process called dynamo action, which then interacts with nearby matter, influencing its behavior. One of the most profound effects of magnetic fields lies in their ability to influence the dynamics of gas clouds in the early universe, clouds that are critical to star formation. As these clouds collapse under their own gravity, magnetic fields can exert a counteracting pressure, slowing down the collapse in certain regions while allowing it to proceed in others. This delicate balance can regulate the rate of star formation, playing a crucial role in determining where and how stars are born. Furthermore, magnetic fields contribute to the alignment of angular momentum in collapsing gas, aiding in the formation of rotating protoplanetary disks around young stars. In galaxy clusters, magnetic fields are instrumental in shaping the hot plasma that fills the space between galaxies, known as the intracluster medium. Observations of synchrotron radiation, emitted by relativistic electrons spiraling around magnetic field lines, have revealed the presence of powerful magnetic fields in these regions. These fields not only influence the behavior of cosmic rays, but also play a vital role in heating the intracluster medium, further impacting galaxy evolution and the overall large-scale structure of the universe. Magnetic fields, pervasive throughout the cosmos, exert a powerful influence on cosmic structures, particularly on a grand scale. As these fields interact with vast clusters of galaxies, they alter the motion of galaxies as they traverse cosmic filaments. Within these regions, the role of magnetic fields extends far beyond mere background forces, actively shaping the dynamics of galaxies. When galaxies encounter each other in these magnetic realms, the effects are profound. Magnetic fields can influence their rotational dynamics and regulate their gas supply, which in turn affects star formation processes. This interplay of forces demonstrates how magnetic fields are not just peripheral components, but essential elements in the mechanics driving the evolution and growth of galaxies and clusters. These interactions reveal the deep interconnections among the diverse forces that shape the universe. Magnetism, gravity, and other fundamental forces work in concert, demonstrating the complexity of cosmic evolution. Far from being isolated phenomena, magnetic fields in cosmic structures illuminate the intricate and dynamic nature of the universe itself. The influence of magnetism on the cosmos underscores how forces we often take for granted are crucial in sculpting the very fabric of existence. As galaxy clusters move through the cosmos, their interactions provide a fascinating glimpse into the ongoing evolution of the universe. These clusters, massive concentrations of galaxies and dark matter, exert immense gravitational pull on one another, and when they approach one another, their mutual attraction sets off a cascade of cosmic events. One of the most dramatic results of this gravitational interaction is the merging of clusters. When two or more clusters collide, they merge into a single, more massive entity, sparking a multitude of dynamic processes. Within these mergers, the galaxies themselves often pass through one another largely unhindered. The vast spaces between stars mean that the galaxies don't directly collide. However, the hot gas that fills these clusters, the intracluster medium, becomes highly dynamic during such events. As this gas collides, it produces shocks and triggers significant heating, increasing the gas's temperature by millions of degrees. This heating generates intense X-ray emissions, enabling astronomers to study these interactions in high-energy wavelengths, thus providing insight into the workings of these massive cosmic systems. Beyond mere merging, the effects of such interactions ripple through the universe, leading to the formation of large-scale structures. The collision of clusters can strip gas from one another, redistributing it in new and fascinating ways. This redistribution can have profound effects on the star formation rates within the galaxies, as the gas reservoirs that fuel these processes are altered. In some cases, mergers and interactions between clusters can lead to the birth of entirely new galaxies, or trigger bursts of intense star formation. These spectacular events radically change the dynamics of the participating clusters, influencing their structure and growth. Another fascinating aspect of galaxy cluster interactions is gravitational lensing. When the mass of a cluster bends the light from more distant galaxies, it creates a lensing effect. This phenomenon not only provides a unique way to map the distribution of dark matter within and around clusters, but also offers a tool for studying galaxies that lie far beyond the foreground cluster. Gravitational lensing illustrates how galaxy clusters are not isolated objects, but part of a vast, interconnected cosmic web. Each interaction leaves lasting consequences, helping to shape the evolution of individual galaxies and the broader structure of the universe itself. Intergalactic gas and dust, often invisible to the naked eye, are key players in the universe's ongoing evolution. These materials fill the immense voids between galaxies, playing a pivotal role in cosmic processes. Known collectively as the intergalactic medium, this gas is composed mainly of low-density hydrogen and helium, with trace amounts of heavier elements. The intergalactic gas serves as an essential resource, feeding galaxies and aiding in their star formation. Though less abundant than gas, intergalactic dust is equally important in shaping the universe's dynamics. It plays a crucial role in thermal and chemical processes across vast distances. The intergalactic gas exists in several distinct phases: hot, warm, and cold, each with its own set of characteristics. The hot phase, made up of ionized hydrogen, can reach temperatures of millions of degrees Celsius. It is found primarily in the filaments of the cosmic web, where it serves as a conduit for material transfer between galaxies. The cold phase, on the other hand, consists of neutral hydrogen and molecules, and is often dense enough to collapse, can form new stars. Dust particles, though sparse, are made up of solid elements like carbon, silicon, and iron. They form in the late stages of stellar evolution or during supernova explosions. Despite their low abundance compared to gas, intergalactic dust plays a vital role in the universe's processes. Dust can absorb and scatter light, affecting how we observe distant galaxies. It also facilitates the formation of molecular hydrogen, which is a key ingredient in the creation of new stars and planets. The interactions between intergalactic gas, dust, and galaxies are central to understanding the life cycle of cosmic matter. This material is often drawn into galaxies during their formation and evolution, feeding their ongoing star formation processes and contributing to their growth over time. In this way, the continuous exchange between the intergalactic medium and galaxies shapes the very structure of the universe. The study of the elusive intergalactic medium opens a window into the heart of the universe, helping astronomers piece together the complex web of connections that link galaxies to the broader structures that shape cosmic evolution. Among these structures, superclusters of galaxies stand out as some of the largest and most awe-inspiring formations in the cosmos. These vast conglomerates are not isolated entities. Rather, they are the product of an intricate interplay of gravitational forces and the dynamics of cosmic expansion. Superclusters can span millions of light years and may contain dozens of galaxy clusters, each cluster acting as a fundamental building block in the grand scheme of cosmic architecture. The formation of superclusters traces back to the early universe, when tiny fluctuations in density emerged just moments after the Big Bang. These minuscule variations, though seemingly insignificant, were the seeds from which vast structures would eventually grow. Matter began to accumulate through gravitational attraction, favoring regions where the density was higher. As these pockets of matter clumped together under their own gravity, individual galaxies started to take shape, often forming clusters of their own. Over time, these clusters drifted closer together as the universe expanded, drawn toward one another by the pull of gravity. As the universe continued to evolve, the mutual gravitational attraction between nearby galaxy clusters led to a process of merging and accumulation. Smaller structures gradually coalesced into larger superclusters, a process that unfolded over billions of years. This evolution was not linear or uniform. Rather, it was influenced by the surrounding cosmic web, a vast network of filaments and voids composed of dark matter and gas. These filaments serve as highways of matter, guiding the motion of galaxies and clusters toward denser regions. As matter flows along these cosmic threads, it falls toward gravitational wells, causing galaxies and clusters to interact in a constant dance of mergers and collisions. When galaxy clusters collide, the effects are profound. Not only do they merge into larger structures, but these interactions can also lead to dramatic transformations. Gas and mass are redistributed, sparking bursts of star formation and altering the galaxies within the cluster. These cosmic collisions are more than just physical events. They are transformative processes that reshape the very nature of the clusters and their constituent galaxies. Over time, this dynamic environment gives rise to a supercluster that is far from static. Instead, it is in a continual state of evolution, driven by gravitational forces, mergers, and even the mysterious influence of dark energy, which accelerates the expansion of the universe. Superclusters are not homogeneous. They exhibit a rich diversity in their structural characteristics. The galaxies within them vary widely in type, age, and stage of evolution. This diversity is a testament to the complex and ever-changing nature of the cosmos. The study of superclusters, therefore, offers valuable insights into the underlying structure of the universe. By examining the way galaxies interact within these massive superstructures, astronomers can better understand the forces that govern the universe on the grandest of scales. Superclusters reveal the intricate connections between galaxies and provide a glimpse into the vast architecture of the cosmos, an architecture that continues to evolve, shaped by forces both visible and invisible, from gravity to dark energy. Quantum entanglement stands as one of the most mind-bending phenomena in quantum mechanics, presenting an astonishing connection between particles that defies the traditional boundaries of space and time. In its essence, it involves the intertwining of two particles' quantum states, creating a relationship so deep that the state of one particle is inextricably linked to the state of the other, even when they are separated by vast distances. The defining characteristic of entanglement is that when one particle is measured, the other particle's state is immediately affected, regardless of how far apart they are. This instantaneous influence between particles is not due to any classical transmission of information, but rather a manifestation of the non-local nature of quantum physics. When these particles are separated by incredibly large distances, perhaps across galaxies, measuring one particle appears to instantly influence the state of the other, a phenomenon that Albert Einstein famously referred to as spooky action at a distance. Despite its mysterious nature, quantum entanglement does not violate the speed of light, as it does not involve the transmission of any useful information. Instead, it highlights the deep contrasts between the classical understanding of the universe and the strange principles of quantum mechanics. In fact, entanglement challenges our perception of locality, suggesting that particles may be connected in ways that defy our usual understanding of physical space. One of the most intriguing aspects of quantum entanglement lies in its potential implications for our understanding of the cosmos. If two particles become entangled in a specific region of space and then one is transported across enormous intergalactic distances, their entangled state remains intact. This raises fascinating questions about the role entanglement could have played in the early universe. Long before the cosmos expanded to its current scale, particles would have likely interacted, entangled, and then dispersed across the universe as it evolved. This primordial entanglement could have persisted for billions of years, affecting quantum states in distant regions. Such ideas challenge our current cosmological models and suggest that entanglement may influence the larger structures of the universe, from galaxies to dark matter. Although entangled particles do not appear to communicate across vast distances in any traditional sense, recent advancements in quantum information theory show that entanglement could have significant practical applications in the future. Technologies like quantum computing and quantum communication are exploring ways to harness the strange properties of entanglement to create faster, more secure systems. Whether these technologies are deployed here on Earth or applied in the farthest reaches of space, the potential applications of quantum entanglement could revolutionize the way we understand and manipulate the quantum world. Ongoing research into quantum entanglement not only continues to push the boundaries of science, but also challenges our very understanding of reality. It forces us to reconsider what is possible within the universe, straddling the gap between the infinitesimally small scales of quantum mechanics and the colossal expanse of the cosmos. Similarly, another foundational concept in quantum mechanics, quantum superposition, opens the door to an even more puzzling reality. Superposition describes a state where a quantum system can exist in multiple states at the same time, until it is measured. This is in stark contrast to the classical world we experience daily, where objects exist in defined states. In the quantum realm, a single particle like an electron can occupy multiple positions, energies, or spins simultaneously. It is only when the particle is observed that it collapses into one of its possible states. The mind-bending nature of superposition is perhaps most famously illustrated through Schrödinger's cat thought experiment. In this scenario, a cat sealed inside a box is both alive and dead at the same time, thanks to the unpredictable decay of a radioactive atom. The cat's fate is linked to the atom's state, and until an observer opens the box, the cat exists in a superposition of both outcomes. This paradox exposes the strangeness of quantum mechanics and raises profound questions about the nature of reality and the role of the observer. Mathematically, superposition is described through wave functions, which provide a complete description of a quantum system. These wave functions can be combined in different ways, and the resulting forms represent all the potential states the system could collapse into upon measurement. The likelihood of observing a particular state is determined by the square of the wave function's amplitude. For example, a particle might be described by a wave function that places it in multiple locations, with the probability of finding it in one place or another, determined by the amplitude of the wave function at those positions. However, the delicate nature of superposition is not easy to observe in the macroscopic world. As quantum systems interact with their environment, superpositions tend to decay, a process known as decoherence. This phenomenon helps to explain why we don't see objects in multiple states at once in our everyday lives, despite the fact that quantum particles can. The loss of quantum coherence and the collapse of the wave function into a single state are what allow us to perceive the classical world in which objects appear to occupy definite positions and properties. Understanding quantum superposition has profound implications not only for the field of quantum physics, but also for emerging technologies such as quantum computing and quantum cryptography. These technologies aim to exploit the ability of particles to exist in multiple states simultaneously, paving the way for groundbreaking advancements in computing power and secure communication. By leveraging the bizarre and counterintuitive properties of quantum mechanics, researchers are working toward creating systems that could far exceed the capabilities of today's classical technologies. Together, quantum entanglement and quantum superposition form the bedrock of a new era in science, one that is transforming our view of the universe, from the smallest subatomic particles to the farthest reaches of space. These phenomena continue to shape the future of technology and challenge our fundamental understanding of reality, opening up a new frontier in the exploration of the cosmos. Reconciling quantum mechanics with general relativity stands as one of the greatest challenges of modern physics. These two pillars of our understanding describe vastly different realms of the universe. Quantum mechanics governs the behavior of the incredibly small, while general relativity explains the dynamics of the vast cosmos. At their core, These theories describe the world in fundamentally different ways, which creates a profound gap in our understanding. Quantum mechanics is a framework for understanding the microcosm, from particles to their interactions. It describes forces through quantum fields and particles, where gravity is notably weaker than the other fundamental forces. The behavior of particles under quantum principles is probabilistic, with phenomena such as wave-particle duality and quantum entanglement challenging our classical intuitions. Yet, when attempting to apply these principles to the fabric of spacetime itself, particularly these curved spacetime described by general relativity, we encounter significant hurdles. General relativity, on the other hand, treats gravity not as a force, but as the curvature of spacetime caused by mass and energy. In this framework, space and time are intertwined into a dynamic entity that warps in response to matter. However, this geometric view of gravity does not seamlessly accommodate the probabilistic nature of quantum particles. The result is a tension. General relativity describes a smooth and continuous universe, while quantum mechanics describes a universe that is inherently uncertain and discrete. Efforts to bridge this divide have led to theories like quantum field theory and curved spacetime. This approach seeks to apply quantum mechanics within the framework of general relativity, especially when describing fields and particles in a curved spacetime, such as near a black hole or during the early universe. While this represents progress, the theory still faces significant obstacles, especially in extreme environments where both quantum effects and intense gravitational forces come into play. Near singularities, such as those found at the centers of black holes or during the Big Bang, both quantum mechanics and general relativity seem to break down, revealing the limits of traditional physics. In light of these challenges, various alternative theories have emerged. Among the most discussed are string theory and loop quantum gravity. String theory posits that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. These strings may provide a unifying framework that can encompass both the microscopic world of quantum mechanics and the vast, curved spacetime of general relativity. On the other hand, loop quantum gravity proposes a radical approach by attempting to quantize spacetime itself, suggesting that spacetime has a granular structure at the smallest scales, comparable to the way matter is made up of discrete particles. Both string theory and loop quantum gravity are still in their infancy, and each faces significant theoretical and experimental challenges. Yet, these ideas provide tantalizing glimpses into a potential unified theory, one that could offer a comprehensive explanation of the universe's workings across all scales. The ongoing search for such a theory remains one of the most exciting frontiers of modern theoretical physics, promising not only to deepen our understanding of the universe, but also to unlock new realms of discovery, from the nature of black holes to very origins of the cosmos. Central to this quest is the concept of quantum fluctuations, temporary variations in the energy at a specific point in space, a phenomenon intrinsic to the uncertainty principle in quantum mechanics. The uncertainty principle tells us that certain pairs of properties, such as position and momentum, cannot be precisely measured simultaneously. This leads to the idea that energy levels can fluctuate, causing virtual particles to appear and disappear out of the quantum vacuum. These fleeting phenomena might seem like minor details, but they have profound implications for our understanding of the universe. Quantum fluctuations played a critical role in the early moments of the universe, particularly during the inflationary period, shortly after the Big Bang. During this rapid expansion, the universe grew exponentially in a fraction of a second, smoothing out irregularities and setting the stage for the large-scale structure we observe today. The fluctuations in energy density during this phase were crucial, serving as the seeds for the formation of galaxies and galaxy clusters. Over time, slight variations in gravitational attraction, seeded by these fluctuations, grew to form the vast cosmic structures we see now. In the end, these tiny quantum fluctuations may hold the key to unlocking the mysteries of the universe, as we continue our search for a theory that bridges the microscopic and the cosmological. While the path to unification remains long and uncertain, each step forward brings us closer to understanding the universe in its most fundamental form. Quantum fluctuations weave through the very fabric of the universe, affecting everything from the tiniest subatomic particles to the vast, mysterious realms of black holes. At the heart of these fluctuations lies a process that underpins some of the most intriguing phenomena in physics, one of the most notable being Hawking radiation. This process occurs at the event horizon of black holes, where intense gravitational forces create conditions for quantum effects to emerge. In this environment, particle-antiparticle pairs spontaneously appear. If one particle is drawn into the black hole while the other escapes, it results in the gradual loss of energy and mass from the black hole over time. This intriguing interaction hints at a startling possibility. Black holes, once thought to be eternal and inescapable, could eventually evaporate entirely, their mass slowly radiating away into space. The influence of quantum fluctuations, however, is not limited to the cosmic scale. They also manifest in the microscopic world, playing a crucial role in phenomena like the zero-point energy of vacuum states and the behavior of superconductors. These fluctuations reflect the underlying quantum nature of the universe, which continues to challenge our understanding of reality. As we delve deeper into the fundamental structure of matter and the forces that govern it, quantum fluctuations remain a key piece in the puzzle of how the universe evolved from its earliest moments to its current state. They bridge the gap between the microscopic quantum world and the macroscopic universe, emphasizing the profound connections that tie all levels of existence together. Another fascinating quantum phenomenon is tunneling, which defies classical expectations. In the quantum realm, particles can pass through energy barriers that classical physics would deem impassable. This occurs because at quantum scales, particles are not confined to specific locations. Instead, they exist as probabilities, and there is a non-zero chance that they might be found on the other side of an energy barrier, even if they don't possess enough energy to overcome it in the traditional sense. This is not just a quirky feature of quantum mechanics. It plays a central role in many cosmic processes. A striking example is in the core of stars, where quantum tunneling allows hydrogen nuclei to overcome their mutual electrostatic repulsion and fuse into helium. In the extreme conditions of stellar cores, this tunneling process accelerates fusion, allowing stars to produce vast amounts of energy. Without quantum tunneling, stellar fusion would occur at a much slower rate, which would have profound effects on the evolution and lifespans of stars. On a grander scale, quantum tunneling might even have played a role in the very birth of the universe itself. Some theories suggest that the Big Bang could have been a quantum event, a transition from a higher dimensional space or false vacuum state into the observable universe we now inhabit. This tunneling from one quantum state to another may have set the initial conditions for the universe's formation, laying the foundation for everything we see today. The idea that quantum processes could have shaped the universe on its largest scale is mind-boggling, yet it highlights the importance of quantum mechanics in the grand cosmic narrative. In black holes, tunneling once again comes into play through the phenomenon of Hawking radiation. As quantum fluctuations cause virtual particle pairs to emerge near the event horizon, one particle can fall into the black hole while the other escapes. This process leads to a slow loss of mass for the black hole over time, hinting at a dynamic rather than static nature for these enigmatic objects. The interplay between quantum mechanics and general relativity raises intriguing questions, especially about the ultimate fate of black holes. While classical theories hold that black holes consume everything that crosses their event horizon, quantum mechanics suggests that they are far more dynamic, capable of emitting radiation and even potentially shrinking over time. The concept of Hawking radiation challenges long-standing assumptions about black holes. Historically, they were thought to be regions where nothing, not even light, could escape. Yet quantum fluctuations allow for the creation of particles at the event horizon, permitting radiation to escape and leading to a slow but steady loss of mass. This process not only gives us a glimpse into the quantum underpinnings of black holes, but also opens up new avenues of thought about the ultimate fate of these mysterious objects. This phenomenon also touches on another profound issue, the black hole information paradox. According to classical theories, when matter falls into a black hole, all the information it contains is lost, disappearing beyond the event horizon. However, quantum mechanics insists that information cannot be destroyed. This fundamental tension between quantum theory and general relativity has yet to be resolved, but it highlights the need for a deeper understanding of how these two theories can coexist. The ultimate resolution of the black hole information paradox may require a new framework that unifies quantum mechanics and gravity, an endeavor that could unlock some of the most profound mysteries of the universe. Thus, quantum fluctuations, tunneling, and the concept of Hawking radiation all serve as windows into the deep, intricate workings of the cosmos. From the birth of stars to the evolution of black holes, and even the origins of the universe itself, these quantum processes play an essential role in shaping the universe. As we continue to explore the quantum world, the mysteries of space and time will unfold in ways we are only beginning to understand, reminding us that the universe is far more complex and far more interconnected than we could ever have imagined. However, quantum mechanics posits that information cannot be obliterated, a concept that has sparked intense debate in theoretical physics. This paradox lies at the heart of ongoing discussions as scientists strive to reconcile the fundamental principles of quantum mechanics with the behavior of black holes, two seemingly contradictory pillars of our understanding of the universe. The research exploring black holes through the lens of quantum mechanics not only enriches our knowledge of these enigmatic cosmic objects, but also pushes the very boundaries of physics itself. As scientists continue their quest to understand how these concepts intersect, they may uncover new revelations that challenge our most basic understanding of space and time. These insights could ultimately provide a more complete picture of the formation, evolution, and ultimate fate of black holes in the universe. Quantum effects almost certainly played a crucial role in shaping the early universe, particularly in the first moments following the Big Bang. At this time, the universe was in an extraordinarily hot and dense state, dominated by quantum mechanics rather than classical physics. In this primordial environment, particle-antiparticle pairs formed spontaneously, only to annihilate each other due to the intense energy levels present. The fluctuating quantum fields at this early stage may have been instrumental in shaping the distribution of matter and energy throughout the cosmos, setting the foundation for the large-scale structures that populate our universe today. One of the most significant outcomes of these quantum effects is seen in the process known as cosmic inflation. This theory suggests that in the universe's earliest moments, a period of rapid exponential expansion took place, smoothing out irregularities and ensuring a nearly uniform distribution of energy. During this inflationary period, quantum fluctuations were stretched to cosmic scales, creating slight variations in density. These tiny variations ultimately seeded the formation of galaxies and other structures as the universe continued to expand and cool. Furthermore, quantum mechanics may have fundamentally altered our understanding of time and space itself. The relationship between quantum field theory and general relativity hints that spacetime might exhibit quantum characteristics at extremely small scales. This idea challenges the classical notions of causality and the continuity of space and time, transforming the early universe into an arena for exploring the deep, unknown interactions between these fundamental forces. As we explore the implications of quantum mechanics in the infancy of the universe, we are confronted with profound questions about the nature of time itself. How did reality emerge from a quantum state? What governing principles shaped the universe when it was incomprehensibly small and nascent? These questions not only expand our understanding of the universe's early moments, but they also open the door to new physics that might bridge the gap between the quantum realm and the vast cosmological landscape. One such pursuit is quantum gravity. Quantum gravity is an ambitious theoretical framework that attempts to reconcile two pillars of modern physics: general relativity, which describes gravity on a cosmic scale, and quantum mechanics, which governs the interactions of particles at the smallest levels. The challenge lies in the fact that while general relativity explains how gravity affects the curvature of spacetime, quantum mechanics deals with discrete particles and their interactions, leading to vastly different predictions and models. This disparity represents one of the most critical unresolved problems in contemporary physics: how to create a unified theory that merges both the very large and the very small forces of nature. Several theoretical avenues are currently being pursued to develop a theory of quantum gravity. One prominent candidate is string theory, which suggests that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. These strings can exist in multiple dimensions, and their vibrational states give rise to various particles and forces. If string theory holds true, it could provide a unifying framework that links gravity with the other fundamental forces, such as electromagnetism and the strong and weak nuclear forces. Another leading theory is loop quantum gravity, which seeks to quantize space-time itself. According to this theory, space is composed of discrete units called loops, thereby introducing a granular structure at the smallest scales. This theory strives to maintain the principles of general relativity while incorporating quantum mechanics, which could potentially lead to a deeper understanding of gravitational phenomena, including black holes and the Big Bang. The convergence of these theories could dramatically reshape our perception of the universe. Gravity, as we know it, may not be a force in the traditional sense, but rather a manifestation of the geometric properties of space-time, influenced by quantum mechanics. Such an understanding could help resolve long-standing mysteries, particularly those related to black holes and the singularities often associated with them. Ultimately, the search for quantum gravity is not just about synthesizing different theories, but about unlocking a deeper understanding of the universe's fundamental fabric and the interplay between its most basic constituents. Among the most energetic phenomena observed in the universe are ultra-high energy cosmic rays. These particles, whose energies exceed 1 billion trillion electron volts, are primarily protons, though they may also consist of heavier atomic nuclei. The origins of these cosmic rays remain an intriguing mystery, the subject of ongoing research. One prevailing theory attributes their creation to extreme astrophysical events, such as supernova explosions, active galactic nuclei, and gamma-ray bursts. Supernovae are stellar explosions that occur when massive stars run out of nuclear fuel and collapse under their own gravity. These events create shock waves that accelerate particles to extraordinary energies. The remnants of these explosive events provide environments where cosmic rays can be accelerated and subsequently detected on Earth. Active galactic nuclei, regions around supermassive black holes at the centers of galaxies, are another key source of these energetic particles. Intense gravitational forces in these regions, along with the accretion of matter, release vast amounts of energy. As matter spirals into the black hole, it may emit powerful jets of particles that accelerate protons and heavier nuclei to ultra-high energies. Observational evidence suggests a correlation between some of the most energetic cosmic rays and specific active galaxies, supporting this connection. Moreover, gamma-ray bursts, among the most powerful explosions in the universe, could be key contributors to the energetic landscape of the cosmos. These bursts release staggering amounts of energy, predominantly in the form of gamma rays, and are thought to be the result of processes that unfold in some of the universe's most extreme environments. These environments accelerate particles to unimaginable speeds, pushing the limits of physics as we understand it. By studying ultra-high energy cosmic rays, scientists can not only trace their origins, but also gain profound insights into the most violent and energetic processes that shape our universe. These cosmic rays offer a rare window into the extreme physics that governs celestial phenomena beyond our comprehension. Cosmic rays and their constant bombardment of Earth's atmosphere exert a notable influence on planetary environments and even life itself. Composed mainly of protons and heavier atomic nuclei from distant regions of space, these particles relentlessly collide with atmospheric gases, initiating a cascade of secondary particles, including muons and neutrinos. Though most of these high-energy particles are either absorbed or deflected by the Earth's magnetic fields and atmosphere, their interactions can trigger complex processes that have far-reaching implications for both our planet's atmosphere and the life forms that inhabit it. Within the atmosphere, cosmic rays play a critical role in the production of certain isotopes, including carbon-14, through nuclear reactions. This isotope is vital in radiocarbon dating, the technique that allows scientists to determine the age of organic materials. Without the influence of cosmic rays, understanding the passage of time in archaeology, geology, and other fields would be far less precise. However, their influence doesn't stop there. Cosmic ray interactions also impact atmospheric chemistry, particularly in the formation of clouds. By ionizing molecules in the air, cosmic rays can initiate reactions that lead to cloud formation, which in turn affects weather patterns and, ultimately, the Earth's climate. The impact of cosmic rays on life is complex and multifaceted. While the Earth's atmosphere offers a protective barrier against most cosmic rays, some of their radiation still reaches the surface, where it can pose risks to living organisms. High levels of exposure to these energetic particles can lead to an increase in mutation rates in both plants and animals. The damage to cellular structures and DNA raises concerns about evolutionary adaptations, as organisms must contend with the long-term effects of this radiation. This ongoing interaction between cosmic rays and life on Earth reveals a profound connection between the cosmos and the delicate balance of life on our planet. However, some researchers propose that the perpetual presence of cosmic rays might also contribute to the generation of genetic diversity, potentially offering an advantage for evolution in an ever-changing environment. This idea extends beyond their direct impact on life, as cosmic rays are believed to play a significant role in broader biological phenomena, including cloud seeding and climate variability. These interactions remind us of the deep interconnectedness between cosmic events and life on Earth, illustrating how forces from beyond our planet can ripple through our environment and influence the biological processes that sustain life. As we learn more about cosmic rays and their influence on our planet, we develop a greater understanding of the complexities of life within the vast and interconnected universe. Among the most energetic and powerful phenomena in the cosmos are gamma-ray bursts, events that release extraordinary amounts of energy in mere seconds. These bursts can briefly outshine entire galaxies, sending gamma rays across vast distances through space. The leading causes of these bursts are often linked to cataclysmic events involving massive stars and the violent dynamics of supernova explosions. One of the primary triggers of gamma-ray bursts is the collapse of massive stars into black holes. When a star of enormous mass runs out of nuclear fuel, it can no longer withstand the forces of gravity, causing its core to collapse. As this happens, the outer layers of the star explode outward in a spectacular supernova. During this collapse, jets of highly energetic particles are formed and focused along the star's rotational axis. When these jets pierce the outer layers of the star, they emit intense gamma radiation, creating the gamma-ray bursts we observe from Earth. Another significant cause of gamma-ray bursts is the merger of binary neutron stars. Neutron stars, which are the incredibly dense remnants of supernova explosions, can spiral toward each other in a pair. As they draw closer, they eventually collide and merge, producing an intense gamma-ray burst. These events can also give rise to kilonovae, in which material ejected during the merger leads to the creation of heavy elements such as gold and platinum. The study of gamma-ray bursts offers profound insights into the universe, shedding light not only on the dramatic end-of-life stages for massive stars, but also on the distribution of heavy elements and the processes that govern star formation and death. These violent phenomena serve as cosmic beacons, allowing scientists to better understand the complex and often chaotic mechanisms that shape the cosmos. With every new discovery, we uncover more about the intricate interactions between matter and energy at the most extreme scales. Cosmic rays, which are primarily composed of protons and other atomic nuclei, travel at nearly the speed of light, reaching remarkable energies through various acceleration processes within astrophysical environments. The mechanisms behind this acceleration are multifaceted and often involve phenomena associated with incredibly energetic events in the universe. Some of the most important processes responsible for cosmic ray acceleration include shock waves from supernova explosions, interactions within active galactic nuclei, and the dynamics of stellar processes. One of the key accelerators of cosmic rays is the shock wave produced by supernova explosions. When a massive star explodes as a supernova, it sends out powerful shockwaves that rapidly expand into the surrounding space. As these shockwaves interact with particles in the interstellar medium, they push those particles back and forth, repeatedly crossing the shock front. With each crossing, the particles gain more energy. This process, known as diffusive shock acceleration, can propel particles to energies thousands of times greater than those achievable by Earth-based particle accelerators. Active galactic nuclei, the regions surrounding supermassive black holes at the centers of galaxies, also act as potent accelerators of cosmic rays. As matter falls into these black holes, it forms an accretion disk and emits intense energy in the form of jets that shoot outward from the black hole. These jets, composed of high-energy particles, are capable of accelerating particles to relativistic speeds, sending them on journeys across vast distances into space. These cosmic jets are a critical source of cosmic rays, propelling particles to near-light speeds as they travel outward into the galaxy. Through these phenomena, whether the violent end of a massive star or the energetic jets of a black hole, we are witnessing the mechanisms that create the cosmic rays that fill our universe. Each discovery unravels another layer of complexity in the processes that drive the universe's most powerful and energetic events. Cosmic rays, the high-energy particles that originate from deep space, are not just a curiosity, they are the key to unlocking some of the most profound mysteries of the universe. These particles, which travel at nearly the speed of light, are accelerated by some of the most extreme and violent astrophysical events in the cosmos. Events such as gamma-ray bursts and pulsar winds, each driven by forces we can scarcely imagine, play pivotal roles in these accelerated journeys. Gamma-ray bursts, GRBs, some of the most powerful explosions in the universe, occur when stars collapse in catastrophic supernovae or when neutron stars merge. These events an unfathomable amount of energy. The sheer force of such explosions can send particles speeding across vast distances, accelerating them to extraordinary speeds. Similarly, pulsars, rotating neutron stars that emit beams of radiation, create an environment where particles are subjected to intense magnetic fields. These fields can rapidly accelerate particles to speeds that defy our understanding of physics. In both cases, cosmic rays are born, becoming some of the fastest particles known to humanity. Understanding how these cosmic rays achieve such speeds not only enriches our knowledge of high-energy astrophysics, but also deepens our understanding of how the universe's most violent phenomena influence life on Earth, from atmospheric chemistry to the very conditions that allow life to flourish. However, cosmic rays are just one facet of this high-energy puzzle. Alongside them, neutrinos, nearly massless particles that interact only weakly with matter, play a crucial role. Neutrinos, which travel through space with little to no resistance, can be generated in some of the most extreme processes in the universe. While they are incredibly difficult to detect due to their elusive nature, the search for them has revealed some of the most energetic events in the cosmos. The highest energy neutrinos detected on Earth are thought to originate from supernovae, active galactic nuclei, and gamma-ray bursts. During a supernova, massive stars explode in a brilliant display of energy, releasing vast quantities of neutrinos as byproducts of nuclear reactions. These neutrinos stream outward, and if a supernova occurs close enough to Earth, its neutrino emissions might even be detectable. Active galactic nuclei, driven by supermassive black holes at the centers of galaxies, also generate high-energy neutrinos. As matter is pulled into these black holes, it accelerates to near light speed, producing intense jets that can generate neutrinos through complex interactions. In a similar vein, gamma-ray bursts, linked to stellar collapses or neutron star mergers, are thought to also produce vast quantities of high-energy neutrinos. The bursts themselves, some of the most explosive phenomena observed, create conditions that can accelerate particles and generate neutrinos, adding another layer to the cosmic energy puzzle. The detection and study of these elusive particles have revealed correlations between gamma-ray bursts and high-energy neutrinos, offering new insights into the most energetic processes in the universe. As detection technologies improve, scientists are able to delve deeper into the nature of these particles and the cataclysmic events that give rise to them, shedding light on the extreme environments that shape the very fabric of the cosmos. Yet, cosmic rays and neutrinos are not the only cosmic travelers affected by the universe's magnetic forces. As cosmic rays traverse vast expanses of space, they interact with magnetic fields, both interstellar and intergalactic, resulting in complex phenomena. When cosmic rays move through interstellar magnetic fields, they experience a process called magnetic deflection. Charged particles, such as protons or atomic nuclei, spiral around these magnetic field lines, altering their straight-line trajectories. This deflection complicates efforts to trace the original source of cosmic rays, especially since the fields themselves are highly variable. Low-energy cosmic rays are particularly vulnerable to deflection, while higher-energy particles tend to retain more of their momentum, causing them to be less affected by these magnetic forces. Alongside deflection, cosmic rays can induce secondary interactions when they collide with the magnetic field lines or other particles. For instance, when a cosmic ray interacts with an atom of hydrogen or helium, the collision may create a cascade of secondary particles, including muons, neutrinos, and gamma rays. These interactions are critical for researchers as they help to unravel the complex relationships between cosmic rays and the environments through which they travel. As cosmic rays continue their journey, they encounter increasingly weaker magnetic fields, such as those found in the vast spaces between galaxies, known as intergalactic space. In these regions, cosmic rays interact less frequently with matter, but the influence of magnetic fields remains, albeit on a less significant scale. Ultimately, the interplay between cosmic rays, neutrinos, and magnetic fields offers researchers a unique window into the universe's most extreme phenomena. Every detection of a high-energy particle or observation of a cosmic burst brings us closer to understanding the mechanisms that drive the cosmos. By studying these high-energy particles, scientists continue to peel back the layers of cosmic mystery, revealing a universe far more dynamic, interconnected, and awe-inspiring than we ever imagined. However, across the vast stretches of space, even the faintest of magnetic fields can deflect cosmic rays, causing even minor deviations to become significant over such immense distances. This complicates the effort to trace the origins of ultra-high-energy cosmic rays back to their sources. The interaction between these cosmic rays and magnetic fields offers a deeper understanding of these energetic particles and, by extension, the intricate structure and behavior of the universe, both at the interstellar and intergalactic scales. As scientists continue to decode these complex dynamics, they uncover ever more profound insights into the fundamental processes that shape our cosmic environment. Cosmic rays are more than just particles. They are messengers carrying invaluable information about distant galaxies. These high-energy particles, born from various astrophysical phenomena, travel through the vastness of space, offering us a window into their origins and the environments from which they emerged. By analyzing cosmic rays detected here on Earth, researchers can piece together details about the elemental and isotopic composition of far-off galaxies. One of the most revealing aspects of cosmic rays is their elemental composition. When these particles interact with Earth's atmosphere, they produce secondary particles that advanced detection instruments can measure. By studying the ratios of elements such as carbon, iron, and helium, scientists can gain insights into the nucleosynthesis processes at work in their distant sources. These processes, which occur in stars and their explosive deaths, offer clues about the formation of elements in previous generations of stars, shedding light on the chemical evolution of their host galaxies. Furthermore, cosmic rays provide a unique glimpse into the environments where they were accelerated. Extreme environments like those found in supernova remnants and active galactic nuclei are known to generate high-energy cosmic rays. The acceleration mechanisms that create these particles are closely tied to the physical conditions of their surroundings. By analyzing the energies and distributions of cosmic rays, scientists can infer critical information about conditions such as temperature, density, and magnetic field strength in these regions. This information helps scientists understand the intricate interplay between cosmic rays and the matter around them. Cosmic rays also offer valuable data about the propagation of particles through the interstellar and intergalactic mediums. As these particles journey across vast cosmic distances, they interact with the ambient matter and radiation, which can alter both their composition and energy. By studying how cosmic rays lose energy and what changes occur during their journey, scientists can refine their models of cosmic ray sources and improve the accuracy of their conclusions about distant galaxies. All of this points to a broader truth. Cosmic rays are indispensable tools for astrophysicists seeking to understand the universe. They help scientists piece together the composition and characteristics of distant galaxies, enhancing our grasp of cosmic evolution, stellar life cycles, and the larger dynamics of galaxies in the universe. The ongoing research into cosmic rays continues to unravel the complex story of the formation and evolution of cosmic structures, revealing the inner workings of the cosmos. Cosmic rays also play a critical role in star formation and galactic evolution, influencing processes both locally and across galaxies. These high-energy particles, primarily composed of protons and heavier nuclei, interact with the gas and dust scattered throughout interstellar space, playing a pivotal role in the dynamics of the interstellar medium. Their interactions can significantly alter the properties of molecular clouds, as well as the conditions under which new stars are born. One of the most profound effects of cosmic rays is their ability to ionize the gas within molecular clouds. As cosmic rays penetrate these dense regions, they ionize atoms and molecules, which in turn influences the chemical makeup of the cloud. This ionization process promotes the formation of certain molecules, including molecular hydrogen, an essential building block for star formation. Through this process, cosmic rays help shape the very conditions that lead to the birth of new stars, further illustrating their central role in the ongoing evolution of galaxies. Cosmic rays, high-energy particles streaming across the universe, play a pivotal role in shaping the very fabric of galaxies and star formation. When these particles collide with the interstellar gas, the resulting energy causes a rise in temperature, which can stir the gas into turbulent motion. This turbulence, in turn, affects how gas clouds collapse to form new stars. Without the influence of cosmic rays, the behavior of molecular clouds would likely differ, potentially altering the rate at which stars are born within galaxies. Their impact goes far beyond mere heating. Cosmic rays also serve as a dynamic force in the regulation of galactic mechanics. The pressure exerted by cosmic rays can balance out the intense gravitational pull within the interstellar medium, preventing the gas from collapsing too quickly into new stars. In this way, cosmic rays do more than just contribute to star formation. They act as modulators of the efficiency and pace at which stars come into being across different regions of a galaxy. This process helps explain the diversity seen in stellar populations across galaxies. On a larger scale, cosmic rays are integral to the evolution of galaxies themselves. Their energy injects into the interstellar medium, generating gas outflows that can impact a galaxy's ability to form new stars. This cycle of feedback, driven by cosmic rays, alters the gas content of galaxies, influencing not only the star formation rate, but also the chemical makeup of the galaxy, contributing to its overall development. As scientists continue to probe these interactions, they uncover ever more complexities in the relationship between cosmic rays, star formation, and galactic evolution. These discoveries add new layers to our understanding of how the universe evolves, highlighting the intricate and dynamic forces that govern the life cycles of both stars and galaxies. The case of Tabby's star, formerly designated K8462852, has captured the attention of astronomers worldwide. Known for its irregular and significant fluctuations in brightness, this star has become an enigma. While the cause behind these mysterious dimming events remains unclear, a variety of hypotheses have emerged. One popular theory suggests that a cloud of dust or debris orbiting the star might periodically block its light, creating the observed dips in brightness. If the circumstellar disks surrounding the star were to contain irregularities, it could obstruct the light as the dust clouds pass in front, leading to a reduction in the star's apparent brightness. Another theory points to the possibility of a comet swarm. If a group of comets were pushed into orbits that bring them too close to Tabby's star, their passage might partially obscure its light. As these comets move in and out of alignment with our line of sight, they could cause random darkening patterns that align with the observed fluctuations. A more speculative and far more intriguing explanation suggests the involvement of an advanced civilization. The theory proposes that a megastructure, such as a Dyson sphere, a hypothetical construct designed to capture the energy output of a star, might be responsible for the dimming. Though this idea excites the imagination, it remains highly speculative, and there is little supporting evidence to suggest that such a structure exists. Despite the uncertainty surrounding Tabby's star, scientists continue to gather data using advanced telescopes, seeking to unravel the mystery of its dimming behavior. The ongoing investigation of this star serves as a reminder of the complexities and vast unknowns that persist in our understanding of stellar phenomena. Each new discovery brings us a step closer to understanding the mechanisms behind these unusual fluctuations, and by extension, contributes to our broader knowledge of the universe. Magnetars, a type of neutron star, present another fascinating aspect of stellar evolution. These objects are renowned for their extraordinarily powerful magnetic fields, which can reach strengths up to 1 trillion Gauss, about 1,000 times more intense than those found in ordinary neutron stars. The origins of these powerful magnetic fields are deeply rooted in the extreme conditions found within neutron stars and the processes that unfold during a supernova explosion. When a massive star exhausts its nuclear fuel, it undergoes a dramatic gravitational collapse, resulting in the formation of a neutron star. As the core collapses, the star's rotation rate speeds up due to the conservation of angular momentum. This rapid rotation, combined with the high density of the collapsing matter, facilitates the creation of magnetic fields through a process called the dynamo effect. For magnetars, this process operates under the unique conditions that exist within neutron stars. Superfluid and superconducting matter at incredibly high densities amplify magnetic fields in ways that are impossible to replicate in less extreme environments. As the neutron star spins, charged particles within its interior also move, generating electric currents that further strengthen and organize the magnetic field lines. Over time, magnetars can experience rapid shifts in both their rotation and magnetic field configuration. These dynamic changes contribute to the creation of the star's incredibly strong magnetic fields, making magnetars some of the most extreme and intriguing objects in the universe. Magnetars are among the most extraordinary and enigmatic objects in the universe. These neutron stars, known for their extreme magnetic fields, offer a fascinating glimpse into the fundamental workings of nature under conditions that cannot be replicated anywhere on Earth. The origin of these intense magnetic fields is still a subject of ongoing study. One of the key theories posits that the magnetic fields of magnetars result from the continuous evolution of a neutron star's magnetic structure after its formation. As the star cools and contracts over time, its magnetic field lines can become compressed, leading to an increase in their strength. In this environment, the complex interactions within the star's core can cause the magnetic field to shift and reorganize, creating stronger, localized concentrations of magnetic energy. These changes in the magnetic field structure not only help us understand the extreme conditions that give rise to magnetars, but also provide insights into the behavior of matter and energy in environments of immense pressure and density. The study of magnetars offers more than just an understanding of these celestial objects. It also serves as a laboratory for testing fundamental physics. The unique properties of magnetars challenge our current understanding of magnetic phenomena in the cosmos, pushing the boundaries of what we know about the forces that govern the universe. As such, they serve as invaluable tools for scientists seeking to unravel the mysteries of the universe, providing clues to how matter behaves under conditions far beyond anything we can simulate on Earth. Supernovae, those brilliant and awe-inspiring explosions, mark the dramatic end of a massive star's life cycle. These cosmic events are triggered by the intricate dance of nuclear processes that unfold in a star's core as it runs out of fuel. For massive stars, typically those with a mass at least 8 times that of the Sun, nuclear fusion occurs in successive layers as the core contracts and heats up. Initially, hydrogen in the core fuses into helium. As hydrogen is depleted, helium fusion begins, followed by the fusion of heavier elements, carbon into oxygen, oxygen into silicon, and so on. This process continues until iron accumulates at the core. However, iron fusion does not release energy. Instead, it consumes energy, leading to a buildup of non-fusible material. Once the mass of a star's iron core reaches a critical point, the core can no longer support itself against the immense pull of gravity. At this moment, a catastrophic collapse occurs, causing the core to implode in a matter of seconds. This collapse generates immense temperatures and pressures, leading to the formation of a shock wave that radiates outward through the star's outer layers. As the shock wave reaches the surface, it rebounds, violently ejecting the star's outer material and triggering a supernova explosion. This explosion is not just a spectacular visual phenomenon, it also has profound implications for the universe. Supernovae are responsible for dispersing heavy elements into space, enriching the cosmic environment and providing the raw materials needed for the formation of new stars and planets. In addition to the typical process of supernova, there are other mechanisms that can trigger such explosive events in massive stars. For instance, if a massive star is part of a binary system, it may siphon material from its companion star, increasing its mass. This accumulation of mass can lead to a collapse, triggering a supernova even before the star has exhausted its own nuclear fuel. The dynamics of this material transfer can destabilize the star and initiate the process of collapse. As such, binary systems provide an interesting avenue of study, as they can cause stars to meet their end in ways that differ from the traditional core collapse supernova model. The explosion of a supernova marks the end of a star's life, but it also represents a critical moment in the life cycle of matter in the universe. The heavy elements produced and dispersed in these explosions are crucial for the formation of new stars, planets, and even life. Through the study of supernova, astronomers gain essential insights into the process of stellar evolution, shedding light on the life cycles of stars and the materials that make up the cosmos. Not all stars, however, meet such a cataclysmic end. While most massive stars end their lives in supernova explosions, a select few survive this dramatic event. The key to their survival lies in their mass and the specific circumstances surrounding the explosion. For stars in binary systems, the interaction between the two stars can play a significant role in determining whether one of them will survive. In some cases, a massive star can transfer a portion of its mass to its companion before undergoing a supernova. This transfer can prevent the star from undergoing the catastrophic collapse that typically leads to the explosion, allowing it to avoid total destruction. Supernovae come in two primary types, Type 1 and Type 2. Type 1 supernovae occur in binary systems when a white dwarf star accretes enough material from its companion to reach a critical mass, triggering a violent explosion. The companion star, if sufficiently distant, may survive the explosion, avoiding the direct impact of the blast. On the other hand, Type 2 supernovae result from the collapse of the core of a massive star. Depending on the star's mass and internal structure, the explosion can leave behind either a neutron star or a black hole, while the outer layers of the star are scattered into space. These stellar explosions, whether they end in destruction or survival, play a crucial role in shaping the universe. They contribute to the ongoing cycle of star formation and death, enriching the cosmos with the elements needed for new stars, planets, and perhaps even life itself. Through the study of these processes, astronomers continue to unlock the secrets of the universe, gaining deeper insights into the forces that govern the cosmos and the evolution of matter throughout the vast expanse of space. In the vast expanse of the cosmos, stars face an array of extraordinary and complex evolutionary paths. While many stars culminate their existence in a fiery supernova explosion, some take a far more subtle route, transitioning into processes that do not result in any explosive display. This dimension of stellar evolution unveils the intricate and often mysterious nature of the universe, where a star's fate is shaped not just by its mass, but by the interplay of cosmic forces beyond our comprehension. Survival in this realm is a delicate dance, where mass, fate, and cosmic interactions converge to determine the final destiny of these celestial giants. Among the most perplexing phenomena in modern astrophysics are fast radio bursts, or FRBs. These bursts of radio waves, lasting only a fraction of a second, unleash unimaginable energy, equivalent to the energy produced by the sun over several days. Despite their brief duration, the mystery surrounding FRBs only deepens as scientists continue to probe their origins. Several theories exist, with one of the leading hypotheses suggesting that they arise from cataclysmic astrophysical events, such as the merger of compact objects like neutron stars or black holes. These violent collisions release massive amounts of energy, creating the ideal conditions for the sudden bursts of radio waves that we detect across vast stretches of space. Another possible source for FRBs lies in the activity of magnetars, neutron stars endowed with magnetic fields of extraordinary strength. Some scientists propose that the intense magnetic fluctuations within these magnetars could be behind the powerful radio emissions. What makes FRBs especially intriguing is their elusiveness. Though these signals are detected across great distances, only a handful of them have been traced back to specific galaxies, with some pinpointed in star-forming regions. This raises further questions about the possible connections between these cosmic bursts and the life cycles of stars themselves. The unpredictable and transient nature of FRBs adds another layer of complexity to their study. Since their discovery in 2007, hundreds of these bursts have been recorded, deepening our understanding of their enigmatic origins. As technology advances and more observations are made, the curtain may slowly lift on these cosmic puzzles, revealing the forces at work in the universe's most distant corners. Binary star systems, where two stars orbit around a common center of mass, undergo a captivating evolutionary journey of their own. These systems come in various forms, influenced by factors such as the star's mass, separation distance, and their initial formation conditions. Over time, the gravitational pull between the stars dictates their evolution, often leading to dramatic transformations. In binary systems, where the stars are widely separated, they tend to evolve largely independently, each following its own life cycle. The more massive star exhausts its nuclear fuel faster than its smaller companion, advancing through different phases, becoming a red giant, or perhaps ending its life as a white dwarf, neutron star, or black hole. In contrast, the stars in closer binary systems exert gravitational forces on one another that significantly alter their evolutionary paths. When one star becomes a red giant, it may transfer material to its companion through a process known as mass transfer. This exchange can drastically change the life cycle of both stars. The smaller star might even be rejuvenated, while the larger star's evolution is similarly impacted. In some cases, this interaction can lead to spectacular events such as novas or even type 1a supernovae, if one of the stars becomes a white dwarf and accretes enough mass. The ultimate fate of a binary system can be highly dramatic, ranging from the creation of two white dwarfs to one star consuming its companion entirely, resulting in a single massive object. If the stars remain close enough, their gravitational dance could also lead to the eventual merger of the two, resulting in the production of gravitational waves, ripples in space-time that offer a glimpse into these extraordinary processes. The intricate dynamics of binary star systems not only yield breathtaking cosmic events, but also provide valuable insights into the forces that govern stellar evolution and the cosmos as a whole. Among the most fascinating and exotic theoretical entities in the universe are strange quark stars, stars composed primarily of strange quarks. To grasp the significance of these potential stellar objects, we must first explore the building blocks of matter. Ordinary matter consists of protons and neutrons, which in turn are made up of three types of quarks: up, down, and strange. Strange quarks, heavier than their up and down counterparts, are crucial in the formation of these unique stellar phenomena. The concept of strange quark stars originates from the extreme conditions found in neutron stars, dense remnants of massive stars after a supernova explosion. Neutron stars are primarily composed of neutrons, tightly packed together by gravity. However, under certain conditions of immense density, the up and down quarks in the neutrons may convert into strange quarks, leading to the formation of strange quark matter. Strange quark stars are theorized to have remarkable properties due to the unique equation of state governing strange quark matter. These stars would be denser than ordinary neutron stars, potentially more compact despite having a lower mass. This could lead to extraordinary gravitational effects, and some researchers propose that strange quark stars might even be able to spin rapidly without becoming unstable, distinguishing them from other types of compact stars. However, despite the fascinating potential of strange quark stars, they remain entirely hypothetical. No observational evidence has yet been found to confirm their existence, and they remain a tantalizing enigma in the field of astrophysics. These mysterious phenomena, fast radio bursts, binary star systems, and strange quark stars, are but a few of the countless wonders of the universe that continue to challenge and captivate astronomers. Each discovery, each observation brings us one step closer to uncovering the forces that govern the cosmos, unlocking secrets that have remained hidden for eons. The universe, in all its complexity, is a place where even the most improbable events may occur, and every new revelation only deepens our awe and curiosity about the endless mysteries of the stars. However, astrophysical phenomena linked to neutron stars, such as certain types of pulsars and gravitational waves from neutron star mergers, have sparked growing interest in the study of strange quark stars. Understanding these enigmatic objects could significantly deepen our comprehension of the fundamental forces and behaviors governing matter under extreme conditions, offering profound insights into the universe's most compact and mysterious entities. The formation of stars in extreme environments, particularly within the chaotic and densely packed centers of galaxies, is governed by conditions vastly different from those in quieter regions of space. At the core of many galaxies resides a supermassive black hole, surrounded by a dense cloud of gas, dust, and intense radiation. The gravitational forces at play in these environments are immense, shaping the star formation process in ways that are still not fully understood. In these galactic centers, the volume of gas and dust is staggering. Interactions between particles lead to complex dynamics, with high temperatures initially hindering star formation by keeping the gas in a heated state. However, shock waves and interactions triggered by the black hole's gravitational influence can compress nearby gas clouds, creating regions where conditions become favorable for star formation. As these clouds collapse under their own gravity, they fragment into smaller pieces, ultimately giving birth to new stars. A key factor in this process is the influence of stellar feedback from existing stars. In such extreme settings, the massive stars that form evolve rapidly and can eventually go supernova. The energy and material released during a supernova explosion are injected back into the surrounding medium, compressing gas and triggering additional bursts of star formation in a continuous cycle of creation and destruction. This intricate interplay between the intense gravitational forces and the energy released by stellar evolution fosters the rapid formation of star clusters. Additionally, the presence of strong magnetic fields and turbulent motions within these dense environments can also influence star formation. These factors contribute to varying star formation rates, allowing for the formation of a diverse range of stars, from massive, short-lived behemoths to smaller, long-lived ones. The study of star formation in such extreme environments not only deepens our understanding of stellar evolution, but also reveals important insights into the dynamics of galaxies themselves, showcasing the extraordinary conditions in which stars can emerge despite the challenges posed by their surroundings. The cosmic microwave background radiation, CMB, often regarded as a remnant of the early universe, provides a snapshot of conditions roughly 380,000 years after the Big Bang. One of the most striking features of the CMB is its remarkable uniformity, showing only slight temperature variations across the sky. This near uniformity raises fascinating questions about the history and structure of the universe. The uniformity of the CMB traces back to the state of the universe shortly after the Big Bang. In this hot, dense phase, the universe was filled with a nearly uniform sea of particles interacting through radiation. As the universe expanded, it cooled, allowing protons and electrons to combine into hydrogen atoms, a key event known as the epoch of recombination. At this point, photons could travel freely, no longer scattered by charged particles. These photons released at that moment created the CMB, which has since redshifted into the microwave range as the universe continued to expand. However, the CMB is not perfectly uniform. It contains slight temperature fluctuations, or anisotropies. These variations are of great significance because they provide insights into the density fluctuations that existed in the early universe, fluctuations that eventually evolved into the large-scale structures we see today, such as galaxies and clusters of galaxies. The uniformity of the CMB can be understood through the theory of inflation, which suggests that the universe underwent a rapid expansion in its earliest moments. This inflationary phase smoothed out any pre-existing inhomogeneities, leading to the relatively even distribution of matter and radiation that characterizes the CMB. The statistical properties of the CMB, including its uniformity, support the theory that the universe is isotropic and homogeneous on large scales, meaning it appears the same in all directions and at vast distances. These characteristics align with the cosmological principle, a foundational assumption in cosmology. The CMB is not just a relic from the early universe. It serves as a vital tool for understanding the cosmos's evolution, offering a glimpse into the conditions that laid the foundation for the formation of galaxies and the large-scale structures we observe today. The shape of the universe is a profound topic that delves into the fundamental concepts of cosmology. To understand its true shape, one must consider the universe's large-scale structure and its geometric properties. Researchers explore various models, typically categorizing the universe as either flat, open, or closed. The shape of the universe is closely tied to its overall density and the influence of gravity. Current observations, especially those derived from the cosmic microwave background radiation, suggest that the universe is nearly flat on a large scale. In a flat universe, geometry follows the rules of Euclidean space. Parallel lines never meet, and the angles in a triangle always sum to 180 degrees. This flatness indicates that the total density of the universe is close to a critical value, where the gravitational pull of all matter and energy exactly balances the rate of cosmic expansion. However, the universe could also be curved, either positively or negatively, depending on its total density. A positively curved universe resembles the surface of a sphere, where parallel lines may eventually converge. In contrast, a negatively curved universe takes on the shape of a saddle, where parallel lines diverge. The true curvature of the universe is determined by its density of matter and energy, and current evidence suggests that the majority of the universe's mass is made up of dark energy, which drives its accelerated expansion. This brings us to some of the most fascinating and speculative theories about the universe's structure. Some scientists propose that the universe could be multidimensional, or even shaped in a more complex way, like a torus or even higher dimensional manifolds. While these ideas are still far from proven, they represent humanity's persistent desire to understand the deeper, perhaps hidden nature of the cosmos. The shape of the universe, in all its potential complexity, remains a fundamental mystery, one that continues to challenge our perceptions and propel the ongoing search for answers. This leads us to another equally captivating question. Could there be regions of the universe where different physical laws apply? Our current understanding of the universe is grounded in the principles of physics we have tested extensively here on Earth and in the observable universe. Laws such as gravity, electromagnetism, and nuclear physics appear to operate uniformly across vast distances. But there are some theories that suggest this might not be true everywhere. One such theory is the concept of a multiverse, a collection of parallel universes, each possibly governed by its own unique set of physical laws or constants. In the multiverse model, different universes could exist side by side, with each having its own specific conditions. Imagine variations in fundamental constants, such as the strength of gravity or electromagnetic interactions, leading to entirely different physical realities. These variations could produce universes so different from our own that their existence might never be observable. The very idea of a multiverse, while intriguing, remains speculative, as we currently lack the tools to directly observe these other realms. Additionally, there are extreme, uncharted areas at the very edges of our current knowledge, such as near black holes or during the universe's formative moments. In these intense environments, the laws of physics as we know them could break down or behave in unexpected ways. Under such extreme conditions, where energy densities soar to unimaginable levels, phenomena may arise that challenge existing theories. Quantum mechanics, with its principles of uncertainty and probability, also adds another layer of complexity, allowing for behaviors that defy straightforward explanation. Even within regions of the universe that seem to follow known physical laws, quantum effects can produce strange outcomes. Despite this, most physicists agree that the basic laws of physics are universal. However, theoretical physics continually pushes the boundaries of our understanding, suggesting that there may be more to reality than meets the eye. As ongoing research deepens our knowledge, new insights could reshape our understanding of the very nature of existence itself. The formation of the first stars and galaxies marks a pivotal chapter in the unfolding story of the universe. This era, known as the Cosmic Dawn, occurred roughly 300 to 500 million years after the Big Bang. It was during this time that the universe had cooled enough to allow hydrogen and helium gas to condense and collapse under the force of gravity. At first, the universe was a vast, hot expanse of gas, primarily hydrogen and helium. As it expanded, it gradually cooled, and temperature drops allowed small fluctuations in density to occur. These density variations sparked the formation of gas clouds, which began to clump together. The force of gravity caused these clouds to collapse, and as they did, they grew hotter and denser. Eventually, the temperatures reached levels high enough to ignite nuclear fusion, giving birth to the first stars. These stars, known as population 3 stars, were vastly different from the stars we see today. They were likely more massive, hotter, and brighter, and they contained little to no heavy elements, as these had not yet been formed. The energy produced by these first stars triggered a process known as stellar nucleosynthesis, wherein lighter elements like hydrogen and helium fused to form heavier ones. As these stars neared the end of their life cycles, they exploded in supernovae, releasing heavy elements such as carbon, oxygen, and iron into the surrounding gas. These explosions enriched the cosmos with the building blocks for future generations of stars, planets, and even life itself. As the remnants of these supernovae spread through space, they seeded the formation of the first galaxies. These early galaxies were the first building blocks of the complex cosmic web we observe today. Over billions of years, they merged and evolved, forming the galaxies, clusters, and structures that make up our current universe. The legacy of these primordial stars continues to shape the universe, from the very composition of the stars we see today to the vast, intricate patterns that define the cosmic landscape. The vast, intricate structures of galaxy clusters and superclusters that stretch across the cosmos represent the foundational elements of the universe. At the heart of astronomical inquiry lies the study of the first stars and galaxies, these ancient and luminous objects that marked the universe's early years. In recent decades, scientists have turned to powerful telescopes and sophisticated simulations, tools that allow them to peer deeper into the past and explore the origins of these celestial bodies. Understanding how these early structures took shape holds the key to unlocking the secrets of the cosmos's evolution. The processes that led to their formation are crucial in explaining the diverse array of galaxies we observe today, providing a deeper appreciation of how the universe has evolved into its current state. Cosmic inflation, a groundbreaking theory, proposes that in the fraction of a second after the Big Bang, the universe underwent an incredibly rapid expansion. Specifically, this inflationary phase is thought to have occurred from approximately 10 to the power of negative 35 seconds to 10 to the power of negative 32 seconds following the Big Bang. The theory suggests that a tiny, homogeneous region of space expanded exponentially, increasing the universe's size by unimaginable scales in mere moments. This sudden inflation addresses several puzzling properties of the universe, such as its large-scale uniformity and flatness. Without inflation, the cosmos would have been far more irregular, shaped by quantum fluctuations in the early universe. Inflation offers an elegant solution by stretching these irregularities, smoothing out the cosmos, and creating the homogeneous, this isotropic universe we observe today. Moreover, inflation theory predicts that tiny variations in density, born from quantum fluctuations during this rapid expansion, would later evolve into the massive structures of galaxies and clusters. Evidence from the cosmic microwave background radiation, the faint echo of the Big Bang, provides strong support for the inflationary model. The radiation's slight temperature variations mirror the density fluctuations predicted by inflation, confirming that these early irregularities played a pivotal role in shaping the large-scale structures of the universe. Further investigations, such as the detection of primordial gravitational waves, continue to hint at the truth of inflation. Yet, despite its strong theoretical backing, many aspects of inflation remain uncertain. The exact cause and mechanism of this early cosmic expansion are still subjects of ongoing research, with various models attempting to fill in the gaps. Instruments like the Planck satellite have already provided valuable data, and future missions are poised to refine our understanding. These continued observations are crucial for confirming the validity of inflation and unraveling the specifics of how the universe began its journey. Equally intriguing is the Hubble tension, a conundrum in modern cosmology. This discrepancy arises from differing measurements of the universe's expansion rate, known as the Hubble constant. Essentially, the Hubble constant tells us how quickly galaxies are moving away from us as the universe expands. Two primary methods have produced conflicting values, casting doubt on our understanding of the cosmos's expansion. One method derives the Hubble constant from observations of the cosmic microwave background radiation, specifically through data gathered by satellites like the Planck Observatory. This technique relies on the standard model of cosmology, which includes certain assumptions about the contents and behavior of the universe. According to this approach, the Hubble constant is estimated to be around 68 kilometers per second per megaparsec. To put that into perspective, this means that for every megaparsec, roughly 3.26 million light years, a galaxy is from us, it is receding at a speed of 68 kilometers per second. On the other hand, another method measures the Hubble constant by using nearby supernovae as standard candles. These supernovae act as markers of known brightness, allowing astronomers to calculate distances more accurately. This approach has produced a higher value, around 73 kilometers per second per megaparsec. This discrepancy between the two measurements is significant, raising important questions about our understanding of cosmic expansion and the fundamental properties of the universe. To resolve this Hubble tension, researchers are investigating several possible avenues. One approach involves re-examining the systematic uncertainties inherent in both measurement techniques. Differences in distance measurements, calibration errors, or the underlying assumptions of both methods could be contributing to the conflicting results. Ongoing research will be essential in narrowing down these uncertainties and ultimately improving our understanding of how the universe is expanding and evolving. In the search for answers, the mysteries of cosmic inflation and the Hubble tension hold the potential to reshape our understanding of the cosmos. By refining our knowledge of these phenomena, we may soon unlock new insights into the origins and future of the universe itself. Research into the mysteries of the universe often takes scientists beyond the boundaries of established models. Some investigations are now focused on understanding the potential physics that could lie beyond the standard model of cosmology. This includes exploring modifications to gravity, dark energy, or even the possibility of undiscovered particles that could affect the rate at which the universe is expanding. One such approach is to refine our measurements and gather more precise data using the latest observational technology, like the James Webb Space Telescope and other advanced facilities. By closely studying distant supernovae and calculating more accurate distances to various cosmic objects, scientists aim to gain deeper insights into the Hubble constant and ultimately resolve the ongoing tension that exists around it. The Hubble tension, the mismatch between measurements of the rate of expansion of the universe, remains one of the most significant challenges in cosmology. However, this discrepancy presents an exciting opportunity for discovery, one that could shed light on the fundamental nature of the universe, its structure, and its expansion. This pursuit might lead to groundbreaking revelations that challenge and potentially reshape our understanding of the cosmos. The largest structures in the cosmic web, which include galaxies, galaxy clusters, and superclusters, have formed through a combination of gravitational attraction, dark matter, and the complex processes of cosmic evolution. The story of these formations begins at the very dawn of the universe, starting with the Big Bang. Initially, the universe was nearly uniform, composed of a hot, dense plasma. However, quantum fluctuations during this early period caused slight density variations, which led to regions where matter began to clump together under the influence of gravity. Dark matter, which constitutes a significant portion of the universe's mass, played a crucial role in this process. Unlike ordinary matter, dark matter does not interact electromagnetically and cannot be seen directly. Yet, its gravitational effects are undeniable. Over time, these clumps of dark matter acted as scaffolding for baryonic matter, ordinary matter such as gas and dust. This allowed the latter to collapse into denser regions, ultimately giving birth to stars and galaxies. As galaxies formed, they began to group together under the pull of gravity, creating larger structures like galaxy clusters. These clusters, some containing hundreds of galaxies, are bound together by their mutual gravity. Over time, they evolve into even more massive structures known as superclusters. The interactions between galaxies within these clusters, including mergers and gravitational passes, contribute to the ongoing evolution of the cosmic landscape. The cosmic web, a vast and intricate structure, is defined by enormous filaments of dark matter connecting galaxies and clusters, interspersed with vast voids, regions where galaxies are sparse. This filamentary arrangement is a result of gravitational forces and reflects the large-scale structure of the universe. As the universe expanded, the interplay of dark matter, baryonic matter, and gravity shaped the network of galaxies, clusters, and superclusters that we observe today. Understanding the cosmic web, with its vast network of filaments and voids, offers more than just a map of matter's distribution. It provides profound insights into the underlying physics driving cosmic evolution. The study of these colossal structures continues to evolve, with deep field surveys and advancements in cosmological simulations helping scientists refine their understanding of the universe's architecture. These ongoing efforts not only enhance our comprehension of the cosmos, but also underscore the significance of these structures in the broader context of cosmic history. Another long-standing enigma in cosmology is the missing baryon problem. Theories predict that the universe should contain a certain amount of ordinary or baryonic matter, composed of protons, neutrons, and electrons. This matter is the building block of stars, gas, and galaxies. However, observational evidence reveals that much of this baryonic matter remains undetected, creating a puzzling discrepancy between theory and observation. Theoretical models based on the cosmic microwave background radiation and the large-scale structure of the universe suggest that baryons should make up approximately 15 to 20% of the universe's total mass energy content. Yet, observations reveal only about half of that expected amount. This gap has sparked a search for possible explanations. One leading hypothesis posits that a significant portion of the missing baryons may exist in a warm, diffuse state, making them difficult to detect with current methods. These baryons could reside in vast, nearly invisible filaments of gas that stretch across the cosmic web, connecting galaxies and clusters. This intergalactic medium is challenging to detect, particularly at optical wavelengths, but observations in X-ray and ultraviolet spectra have hinted at the presence of this warm, diffuse gas. Such findings suggest that a substantial fraction of the missing baryons could be hidden in these faint regions. Another possibility is that baryons might be located in smaller scale structures, such as star-forming regions, which might not be adequately resolved by current observational techniques. These smaller regions could contain large quantities of baryonic matter, but their size and nature make them difficult to detect, further complicating our understanding of the universe's composition. The missing baryon problem is a reminder of how much we still have to learn about the universe. It points to gaps in our observational capabilities, the limitations of current technology, and the mysteries that lie just beyond the reach of our instruments. As our tools improve, the discovery of these missing baryons could provide new insights into the very fabric of the cosmos and lead to a deeper understanding of the forces shaping the universe. In the pursuit of unraveling the universe's deepest secrets, astrophysicists face an increasingly complex set of challenges. Stellar feedback, a phenomenon where massive stars expel gas back into the intergalactic medium, adds another layer of difficulty to understanding the distribution of bionic matter. This process, along with other cosmic dynamics, complicates the inventory of the universe's essential building blocks, often leading to more questions than answers. The missing baryon problem, which remains one of the most perplexing mysteries in astrophysics, is tackled with an ever-evolving arsenal of observational techniques and simulations. Researchers continue to refine their models and gather invaluable data as advanced telescopes and sophisticated instruments become more widely available. With each passing year, these efforts inch closer to resolving this elusive question. As scientists expand their understanding of bionic matter, they're also delving deeper into the fabric of space itself. One area of intense research involves the concept of quantizing space-time, an endeavor that stems from the challenge of reconciling two fundamental pillars of physics, general relativity and quantum mechanics. While general relativity beautifully describes gravity as the curvature of space-time, quantum mechanics governs the behavior of particles at the smallest scales. To bridge these two realms, physicists aim to construct a unified framework, one that can describe all of nature's fundamental forces within a single coherent model. The idea that space-time could be quantized challenges our traditional view of it as a continuous fabric. Instead, researchers propose that space-time might be composed of discrete units, or quanta. One of the most promising approaches to achieving this is loop quantum gravity, a theory that suggests space is made up of tiny interconnected loops. These loops create a granular structure to space-time at the Planck scale, an unimaginably small scale of about 10 to the power of negative 35 meters. This quantum nature of space might hold the key to resolving some of the paradoxes that arise in classical general relativity, such as the mysteries surrounding black holes and singularities. In parallel, string theory offers another tantalizing possibility. Instead of point-like particles, string theory proposes that the fundamental constituents of nature are one-dimensional strings. These strings vibrate at different frequencies, and the vibrations determine the properties of the particles they represent. String theory naturally leads to the notion of a multidimensional space in which additional dimensions are compactified. Though string theory does not directly quantize space-time, it offers a framework that could allow quantum mechanics and gravity to coexist, suggesting that the very nature of space-time might emerge from the dynamics of these fundamental strings. Despite these fascinating theoretical advancements, proving the quantization of space-time remains an elusive goal. The experimental verification of these ideas is fraught with difficulties, largely due to the scales at which quantum gravitational effects would become apparent, scales far beyond the reach of current technology. Yet scientists are not without hope. They are exploring a variety of approaches, including high-energy particle collisions and astrophysical phenomena such as black holes, which could provide the key to observing the effects of a quantized space-time. As these investigations progress, the question of whether space-time is quantized remains one of the most profound open problems in modern physics. If successful, a theory of quantum gravity could radically transform our understanding of the universe, offering new insights into the very nature of reality and the relationship between gravity and the other fundamental forces governing the behavior of particles. At the heart of this grand puzzle lies the challenge of understanding gravity at the quantum level. While general relativity provides a macroscopic description of gravity, showing it as the curvature of space-time caused by mass, this view does not mesh neatly with the principles of quantum mechanics, which govern the behavior of particles on the smallest scales. To develop a coherent framework that unites these two domains, physicists are exploring the possibility of a hypothetical particle, the graviton, which might mediate gravitational interactions, much like the photon mediates electromagnetic interactions. Gravitons, if they exist, would be massless and travel at the speed of light, fitting within the framework of quantum field theory. However, despite extensive theoretical work, no direct evidence for gravitons has yet been found. Current theories also investigate the potential effects of quantum mechanics on gravitational phenomena. One intriguing concept is that quantum entanglement, an essential feature of quantum mechanics, could suggest that space-time itself is a manifestation of fundamental information and entanglement. In this view, gravity might not be a classical force, but an emergent property arising from more basic quantum states. This challenges the traditional notion of gravity as a force mediated by a particle, proposing instead that gravitational interactions could emerge from the quantum fabric of reality itself. Loop quantum gravity offers a different perspective, suggesting that space-time is made up of discrete loops that form the underlying geometry of the universe. In this framework, gravity is an emergent property of the structure of space-time itself, and phenomena like black hole entropy and singularities might be explained by a finite quantized space-time. This approach provides a potential solution to the problems that arise in classical general relativity, yet, like other theories, it faces significant empirical hurdles. The energy scales at which quantum gravitational effects would become observable are simply beyond the capabilities of current experimental tools. As these groundbreaking theories continue to evolve, the search for a unified theory of quantum gravity remains one of the most exciting and challenging quests in modern physics. Whether through the exploration of string dynamics, the study of black holes, or the investigation of quantum entanglement, physicists are pushing the boundaries of our understanding of the universe, hoping to uncover the ultimate nature of space, time, and gravity itself. However, advancements in observational astronomy, such as the study of gravitational waves and high-energy cosmic events, are pushing the boundaries of what we know about the universe. These breakthroughs offer the potential to provide direct evidence that could reshape our understanding of gravity at the quantum level. Achieving a complete theory of quantum gravity would be nothing short of revolutionary. It could open the door to insights that not only challenge but potentially redefine our view of the universe's fundamental structure. More crucially, it would illuminate the intricate relationship between gravity and quantum mechanics, a relationship that has long been elusive. The journey towards a unified theory of gravity is ongoing, with physicists exploring an array of theories and methodologies, all in the pursuit of unlocking the true nature of gravity on the quantum scale. One concept that has garnered increasing interest is the possibility of additional spatial dimensions beyond the three that define our everyday reality. This idea, largely driven by string theory, proposes that the fundamental building blocks of the universe are not particles but one-dimensional strings. These strings could vibrate in multiple ways, and based on this theory, there may be as many as 10 or 11 dimensions, far beyond the length, width, and height that we experience. What makes these dimensions so intriguing is that they are likely not observable in the traditional sense. Instead, they might be compactified, existing in tiny curled-up spaces that are far too small for current technology to detect. To understand this, imagine a garden hose. From a distance, it appears to be a one-dimensional object, just a straight line. But when you get closer, you realize it has a circular cross-section, an additional dimension, invisible from afar. Similarly, while our universe seems to consist of three large spatial dimensions, these additional dimensions might be similarly hidden from view, too compact to notice, or so tightly curled that they remain beyond the grasp of our instruments. Despite being imperceptible, these extra dimensions could deeply influence the laws that govern the universe. They offer a potential avenue for theories attempting to unify gravity with the other fundamental forces of nature, something that has eluded physicists for centuries. The dynamics of these higher dimensions could reveal much about how particles interact and how forces like gravity manifest at the quantum level. Exploring higher dimensions is a challenge to our fundamental understanding of reality. It invites us to reconsider long-held assumptions about the nature of space, time, and the universe itself. What lies beyond the familiar dimensions we experience daily? What role do these hidden dimensions play in the forces that govern everything around us? As scientists continue to probe these profound questions, we may begin to uncover more about the underlying structure of the universe, about the layers of reality that lie just beyond the reach of our senses. In the most extreme environments of the universe, like near black holes or neutron stars, gravity behaves in ways that stretch the limits of our understanding. According to Albert Einstein's theory of general relativity, gravity is not merely a force, but a curvature of space-time itself. When a massive object is present, it warps the fabric of space-time, affecting the way that other objects move through that region. Near a black hole, the gravitational field is so intense that it creates a point of no return, called the event horizon. Once an object crosses this boundary, it is pulled in with such force that not even light can escape. This strange phenomenon leads to exotic effects, such as time dilation, where time appears to pass more slowly for an object near the black hole compared to one far away. While this effect has been confirmed in less extreme conditions, it becomes vastly more pronounced near black holes, offering an astonishing glimpse into how gravity can influence the very passage of time. Nearby neutron stars, the dense remnants of collapsed supernovae, are another place where gravity reveals its strange and powerful properties. These stars are so massive and compact that they can create gravitational waves, ripples in spacetime caused by the acceleration of massive objects. When two neutron stars spiral toward each other, their intense gravitational pull generates waves that travel across the cosmos, providing us with a unique window into the most violent and energetic processes in the universe. When these stars collide, the resulting gravitational waves carry enormous energy, helping us probe the furthest reaches of space in ways that were once thought impossible. The detection of gravitational waves has opened an entirely new chapter in astrophysics. It allows scientists to observe cosmic events that were previously undetectable with traditional methods, expanding our capacity to study the universe. By analyzing these waves, we can begin to piece together the behavior of matter under extreme conditions and refine our understanding of the universe's fundamental physics. Each new discovery offers a glimpse into the deep relationship between mass, space, and time, further expanding our understanding of the cosmos. Gravitational waves are generated by the acceleration of massive objects in dynamic and extreme astrophysical settings. When massive bodies such as black holes or neutron stars orbit one another, their motion disturbs space-time, creating ripples that spread outward at the speed of light. These ripples are akin to the waves formed when a stone is thrown into a pond. The more massive the objects involved, the more intense the waves. When black holes merge, for instance, the energy released can be equivalent to several solar masses being converted entirely into energy, producing powerful gravitational waves that travel across space. These waves not only reveal information about distant cosmic events, but also bring a wealth of new data for astronomers to study. In particular, gravitational waves allow scientists to observe phenomena that are invisible in regular light. For example, when two black holes merge, the event can be detected purely by the gravitational waves it produces, with no accompanying electromagnetic signature. This ability to hear the universe through gravitational waves has revolutionized the way we study the cosmos. It offers fresh insights into the formation of compact objects, the behavior of matter under extreme conditions, and even the expansion of the universe itself. By continuing to explore and understand these ripples in space-time, we may uncover answers to some of the most profound questions about the universe: how it was formed, how it continues to evolve, and the underlying laws that govern it. Gravitational waves provide us with a unique perspective on the cosmos, one that could reshape our understanding of the universe in ways that we are just beginning to comprehend. Gravitational waves hold the potential to unveil some of the universe's deepest secrets. By analyzing the distinct characteristics of these waves, scientists can glean vital information about their origins, shedding light on the masses and spins of their sources. As gravitational wave astronomy continues to evolve, it promises to answer some of the most fundamental questions in physics: the nature of gravity, the formation of black holes, and the mysterious environments in which these cosmic giants reside. This growing field exemplifies how innovative scientific techniques can expand our understanding of the fundamental workings of the universe, often revealing phenomena that were once thought to be beyond our reach. Equally captivating are the theoretical constructs of wormholes, which represent fascinating potential pathways through the fabric of space-time. These hypothetical structures, often envisioned as shortcuts between distant points in the cosmos, suggest that the universe may be far more connected than we can currently imagine. According to the theory of general relativity, wormholes might exist because extreme gravitational fields warp space-time, creating these tunnels through which one could, in theory, travel vast distances instantaneously. Though this concept was first introduced in the early 20th century, wormholes remain primarily a theoretical construct, yet their implications are vast, both for scientific inquiry and for the realms of science fiction. There are various types of wormholes, but the most famous is the Einstein-Rosen bridge. This model suggests a tunnel-like structure that could potentially connect two separate regions of space-time. However, for such a wormhole to form and remain stable, an immense amount of mass energy would be required to stabilize its throat, ensuring that it remains open for travel. This brings us to the concept of exotic matter, hypothetical substances that possess negative energy density. Exotic matter, if it could be created, would counteract the gravitational forces trying to collapse the wormhole, making it stable enough to traverse. While the idea of wormholes and exotic matter is tantalizing, the possibility of natural wormholes remains speculative at this point. Despite numerous theoretical explorations of the equations that govern wormholes, no empirical evidence has been found to suggest they could form naturally in the universe. Much of the discussion surrounding wormholes centers on extreme astrophysical phenomena, such as black holes, which may provide the perfect conditions for wormholes to emerge. However, even these theories remain purely speculative. If wormholes do exist, they could have profound implications for our understanding of time and space, possibly offering shortcuts through the universe or even enabling time travel. Yet, the technical challenges and consequences of traversing such a structure, if it were possible at all, are still grounded in the realm of theoretical physics. Nevertheless, the pursuit of wormhole research continues to be a captivating subject, bridging the gap between our current knowledge and the vast, unexplored possibilities of the cosmos. White holes, often proposed as theoretical counterparts to black holes, present another intriguing wrinkle in our understanding of the universe. While black holes are regions of space-time where nothing can escape due to their immense gravitational pull, white holes, in theory, do the opposite. They expel matter and energy rather than absorbing it. Essentially, a white hole could be seen as the reverse of a black hole, releasing all the matter and radiation that a black hole has accumulated over time. The concept of a white hole arises from the same equations of general relativity that describe black holes, particularly in the context of wormholes. In this framework, matter that falls into a black hole could, theoretically, emerge from a white hole elsewhere in the universe, or even in a completely different universe altogether. This idea suggests that black and white holes might be connected by a wormhole, creating a pathway that links distinct regions of spacetime. This speculative theory adds a layer of complexity to our understanding of the cosmos, hinting at an interconnectedness that transcends traditional notions of time and space. Though the existence of white holes remains purely theoretical, the potential they hold for reshaping our comprehension of the universe is enormous. If they were to exist, they could offer revolutionary insights into the behavior of matter and energy at the most fundamental levels. Yet, much like wormholes, white holes remain an enigma, one that continues to spark the curiosity of scientists and the imagination of thinkers across the world. As we push further into the unknown, the theoretical study of white holes could one day reveal new dimensions to our understanding of space-time and the interconnectedness of the universe. However, despite the fascinating theoretical nature of white holes, there is currently no observational evidence to support their existence. The physical properties required for a stable white hole present significant challenges. For instance, if a white hole were to exist, it would need to be surrounded by an event horizon, much like a black hole. But unlike its dark counterpart, a white hole would constantly eject matter in a highly controlled manner, presenting questions about how such an object could remain stable or persist over time in the universe. While the idea of white holes is captivating, sparking speculation about the boundaries of our universe, they remain firmly in the realm of theoretical physics. The search for understanding continues. as scientists remain eager to uncover the fundamental nature of black holes, space-time, and the cosmos. But as of now, white holes exist only within the confines of mathematical theories, not as observable entities. At the singularity of a black hole, space-time exhibits some of the most extreme and perplexing behaviors in the universe. The singularity is the point at the heart of a black hole, where gravitational forces compress matter to an infinitely dense state, and the laws of physics, as we know them, break down. It represents the culmination of matter and energy, concentrated beyond the limits of our current scientific understanding. As you approach the singularity, general relativity predicts that space-time curvature becomes infinite. This means that traditional concepts of time and space lose their usual meaning. As an object nears the singularity, the gravitational pull intensifies, causing time itself to stretch significantly. To an outside observer, time would seem to almost come to a halt for anything moving closer to the singularity. However, from the perspective of the object falling in, it would experience the passage of time normally, until it reaches the singular point. Inside a black hole, the nature of space-time changes dramatically. The geometric properties determined by general relativity no longer apply in the expected way, leading to paradoxes and divergent predictions. For instance, classical physics suggests that once an object crosses the event horizon, the boundary around a black hole, it is irrevocably pulled toward the singularity, where current physics fails to predict what happens next. This breakdown of physics raises profound questions about the very nature of reality itself. To fully understand the behavior of space-time at the singularity, scientists are in pursuit of a theory of quantum gravity, which would merge general relativity with quantum mechanics. This would potentially provide a clearer picture of what happens under these extreme conditions. As research progresses, the singularity remains one of the most profound mysteries of the universe, not only highlighting the limitations of our current knowledge, but also pointing to the potential for groundbreaking discoveries in the future of cosmology. The origin of Earth's water has long been a subject of intense research and debate within the scientific community. The leading theories suggest that water on our planet has two main sources: outgassing from volcanic activity and contributions from extraterrestrial bodies, such as comets and asteroids. Outgassing refers to the release of water vapor from the Earth's interior, primarily through volcanic eruptions. During Earth's early formation, the planet was molten and volcanic activity was rampant. As the surface cooled, water vapor released from the mantle during volcanic eruptions condensed to form surface water, pooling in the planet's basins. This process could have contributed a significant portion of the water we see on Earth today. The second theory suggests that Earth's water could have been delivered from external sources, primarily through impacts by icy celestial bodies. Comets, which are known for their high water content, stand out as prime candidates for this delivery. Similarly, certain types of asteroids, which contain hydrated minerals, might have contributed to Earth's water inventory as well. It's believed that these celestial impacts were particularly frequent during the early solar system, a period known as the Late Heavy Bombardment. During this time, the planet may have received substantial amounts of water, laying the foundation for the oceans and life we know today. Recent research delves deeper into the isotopic compositions of water found in different celestial bodies. By comparing the ratios in these bodies with those of Earth's water, scientists aim to piece together the specific contributions of these external sources. Although the exact proportions remain uncertain, the prevailing theory that a combination of volcanic outgassing and celestial impacts shaped Earth's watery status is compelling. Understanding the origins of water on Earth not only sheds light on our planet's history, but also plays a critical role in the ongoing search for water elsewhere in the universe, which could point to habitable conditions on distant exoplanets. Venus, often dubbed Earth's twin due to its similar size and composition, stands as a stark contrast in terms of its environment. While both planets may have shared similar characteristics in their early history, billions of years of divergent evolution have led them down drastically different paths. One of the most significant distinctions between Venus and Earth lies in their atmospheres. Venus is shrouded in a thick, toxic blanket of carbon dioxide, with clouds of sulfuric acid that dominate the skies. This dense atmosphere creates a runaway greenhouse effect, trapping heat and causing surface temperatures to soar to a blistering 800 degrees Fahrenheit. In contrast, Earth maintains a delicate balance with its greenhouse effect, resulting in temperatures conducive to sustaining life. Venus's unregulated climate has made it incredibly hostile, with atmospheric pressures on its surface reaching over 90 times that of Earth's. Geologically, Venus also diverges from Earth. While both planets have volcanic activity, Venus shows evidence of far more intense and widespread eruptions. The surface of Venus is relatively young, suggesting it has undergone significant resurfacing, possibly driven by extensive volcanic activity. On the other hand, Earth's geology is shaped by plate tectonics, a process that recycles the planet's crust and supports a diverse range of geological features. The planet's dynamic climate is also linked to these tectonic processes, offering a more stable environment. Furthermore, the proximity of Venus to the Sun plays a key role in its extreme conditions. Being closer to the Sun, Venus experiences higher solar radiation, which exacerbates its intense climate and accelerates chemical reactions in its atmosphere. In studying Venus, scientists gain valuable insights into planetary evolution and the range of conditions that can determine whether a planet may host life. Understanding how Venus and Earth have evolved differently enhances our ability to investigate exoplanets, especially those in distant solar systems, and the potential for life beyond our own world. Mars, once a planet that harbored a robust magnetic field and a thicker atmosphere, presents an entirely different narrative. In its early history, Mars may have had conditions that were potentially favorable for life. However, a series of events led to the loss of its magnetic field and atmosphere, leaving Mars the cold, arid world we observe today. The transformation from a more Earth-like planet to its present state has sparked the curiosity of scientists who seek to understand the forces behind planetary evolution. One of the main reasons Mars lost its magnetic field lies in its core structure. Unlike Earth, which has a liquid outer core that generates a strong magnetic field through the dynamo effect, Mars has a smaller and less active core. Studies suggest that Mars might have had a magnetic field early in its history, likely generated by convective motions in its molten core. However, over time, this internal dynamo ceased, weakening the planet's magnetic field and leaving it vulnerable to the harsh conditions of space. As a result, Mars experienced the gradual stripping away of its atmosphere, making it incapable of supporting life as we know it. Through the study of these planetary differences, Earth's watery origins, Venus's hostile atmosphere, and Mars's geological transformation, scientists are piecing together the broader puzzle of planetary evolution, which may eventually inform our understanding of life's potential on exoplanets in far-flung corners of the universe. However, as Mars cooled over millions of years, the planet's core may have solidified, shutting down the crucial dynamo effect responsible for generating its magnetic field. Without this protective shield, Mars became increasingly vulnerable to the intense solar wind, a stream of charged particles emitted by the Sun. This unrelenting bombardment gradually eroded the planet's atmosphere. The solar wind, with its high-energy particles, stripped away essential gases and molecules, leaving Mars with an atmosphere much thinner than it once had. In stark contrast, Earth's magnetic field shields it from such solar activity, protecting its atmosphere from similar erosion. But Mars, devoid of this crucial defense, had no such protection. Over hundreds of millions of years, the combined forces of a weak magnetic field and continuous solar wind exposed Mars' atmosphere to the vacuum of space, carrying away most of its once thicker atmosphere. This slow but relentless loss transformed the Martian environment from a warmer, wetter world into the arid, cold landscape we observe today. This dramatic shift has profound implications for the possibility of life on Mars. Once a planet that may have had a more hospitable environment, Mars now serves as a cautionary tale of how a planet's internal processes and protective features can alter its habitability. With each new space mission to Mars, scientists aim to uncover more about the planet's history, seeking clues about the factors that shaped its evolution. The answers might not only illuminate Mars's past, but also offer vital insights into the fragility of planetary environments and the complex forces that influence their development. On the other hand, the gas giants in our solar system, like Jupiter and Saturn, are entirely different from terrestrial planets such as Earth. These massive worlds are composed mainly of hydrogen and helium, with only trace amounts of other elements and compounds. This composition is a result of their formation in the outer reaches of the solar system, where lighter gases were abundant. Understanding the makeup of these gas giants gives us valuable insights into their structure, their atmospheres, and even their magnetic fields. A gas giant's structure is divided into several distinct layers. The outermost layer is the atmosphere, dominated by hydrogen and helium, but also containing clouds of ammonia, water vapor, and various other compounds. Beneath this, at extreme depths, lies a thick layer of metallic hydrogen. At incredibly high pressures, hydrogen is compressed into a metallic form that behaves like a metal, and this metallic hydrogen layer plays a critical role in generating the powerful magnetic fields that these giants are known for. Beneath the metallic hydrogen, gas giants are believed to have a core composed of rocky or icy materials. This core is likely to contain heavier elements such as silicon, sulfur, and oxygen, along with water ice and other compounds. The core can be vast, with a mass that may be several times greater than that of Earth. Understanding these internal layers not only helps explain the gas giants' magnetic properties, but also reveals the complexity of their formation and evolution, further deepening our knowledge of the diverse worlds in our solar system. However, due to the immense pressure and the overwhelming temperatures, the exact nature of the core of gas giants remains one of the most puzzling subjects in planetary science. The interactions between their core, mantle, and atmosphere give rise to the awe-inspiring phenomena observed on these colossal worlds. On Jupiter, for example, the Great Red Spot is a storm that has raged for centuries, while Saturn's atmosphere is home to intricate and shifting cloud patterns. These extraordinary weather systems are shaped by the extreme conditions within the gas giants, with each layer playing a key role in their formation and behavior. Scientists continue to study these planets to gain deeper insights into planet formation, the behavior of materials under extreme conditions, and the potential for discovering exoplanets that mirror the characteristics of these majestic giants. Their exploration is not only about understanding the gas giants themselves, but also about unraveling the larger mysteries of the universe, such as the processes that govern the birth of planets and the forces that shape them over time. Beyond these gas giants, two distinct regions of our solar system, the Kuiper Belt and the Oort cloud, serve as relics from the solar system's formative years. These icy bodies and remnants provide a snapshot of a time when the solar system was in its early stages of development, around 4.6 billion years ago. The Kuiper Belt, located just beyond Neptune's orbit, is a region populated by countless small icy objects, including dwarf planets like Pluto. It is believed to have formed from the protoplanetary disk that once surrounded the young sun. As material in this disk began to coalesce, some of it formed the gas giants. The debris that remained, situated beyond the giant planets, eventually became the Kuiper Belt. Over billions of years, these icy bodies have collided and merged, creating a diverse collection of objects that have remained largely unchanged since the solar system's early days. Gravitational interactions with Neptune have played a pivotal role in shaping the dynamics of the Kuiper Belt, preventing its icy bodies from coming together to form a planet. In contrast, the Oort cloud is a distant, spherical shell that extends far beyond the Kuiper Belt, potentially reaching up to a light year away. It is thought to have formed from material ejected from the inner solar system during the turbulent early years of planetary formation. The migration of the gas giants, especially Jupiter and Saturn, scattered many smaller icy bodies outward, and some of these objects were flung into distant orbits, creating the Oort cloud. This region is thought to be a reservoir for long-period comets, which occasionally enter the inner solar system when perturbed by gravitational interactions. The differences in structure, location, and origin between the Kuiper Belt and the Oort cloud provide crucial insights into the forces and processes that shaped the solar system. As scientists continue to explore these distant realms, they uncover more details about the early solar system, offering a better understanding of how our planetary neighborhood evolved and how similar structures might exist in other star systems. In 2017, astronomers made a groundbreaking discovery, Oumuamua, the first known interstellar object to pass through our solar system. Its name, derived from the Hawaiian word for scout or messenger, reflects its origin from beyond our solar neighborhood. This mysterious object captured the attention of the scientific community because it exhibited several peculiar characteristics that set it apart from typical asteroids or comets. One of the most striking features of Oumuamua was its lack of a comet-like tail. Despite its comet-like trajectory, there was no sign of the typical outgassing that usually accompanies such objects as they approach the sun. Some researchers speculated that Oumuamua could be a fragment of a larger body ejected from its home star system, while others proposed more exotic theories about its origins. Its high speed and unusual trajectory suggested that the object had traveled for millions of years, potentially originating from another star system before entering ours. This raised intriguing questions about the conditions and materials present in distant star systems, suggesting that Oumuamua might offer a rare glimpse into the nature of these far-flung cosmic neighborhoods. Despite extensive observations and studies, many aspects of Oumuamua remain shrouded in mystery. The exact composition of the object, its shape, and the cause of its unexplained acceleration are still the subject of intense debate. Nevertheless, the discovery of Oumuamua has sparked new excitement in the field of astronomy as it pushes the boundaries of our understanding of interstellar space and the objects that populate it. In the future, as we continue to study this extraordinary visitor, we may uncover not only the secrets of Oumuamua itself, but also gain valuable insights into the nature of countless other objects that may be lurking in the vast expanse of the cosmos. Uranus, the ice giant, stands apart from the other planets in our solar system due to its extreme axial tilt. Unlike most planets, which rotate more or less upright, Uranus spins on its side at an angle of about 98 degrees. This unusual orientation suggests a violent history, one that may have involved significant collisions or gravitational interactions that altered the planet's rotational dynamics. One widely accepted theory is that Uranus was struck by massive protoplanetary bodies during its early years. These colossal impacts likely occurred at oblique angles, which could have caused Uranus to shift its axis drastically. This theory suggests that, over time, Uranus's axial tilt became the extreme position we observe today, a remarkable testament to the chaotic processes that governed the early solar system. Uranus's peculiar tilt has fascinated scientists, not only because it challenges our understanding of planetary dynamics, but also because it offers a clue about the kinds of violent events that could have shaped other planets and their moons across the universe. Studying Uranus's tilt and its origins helps us learn more about the unpredictable forces that have shaped the solar system and may continue to shape distant star systems in the future. Such a scenario is entirely plausible when considering the chaotic and turbulent environment of the early solar system. At that time, planetary bodies were still colliding, forming, and being shaped by cosmic forces. It was a period marked by intense activity where even the most unlikely events could occur. One such possibility is that the extreme tilt of Uranus was not solely the result of a catastrophic collision, but also influenced by the gravitational forces of its own extensive system of moons and rings. Over time, these interactions could have contributed to Uranus's dramatic sideways rotation. The gravitational pull exerted by the moons and rings on the planet's atmosphere likely played a role in maintaining or even enhancing its axial tilt after the initial impact. This process would have been slow, unfolding over millions of years, but the result is one of the most unusual and striking characteristics in our solar system: Uranus's sideways rotation. Each of its poles is subjected to 21 Earth years of continuous sunlight, followed by an equal period of darkness as the planet orbits the sun. This unique tilt gives rise to extreme seasonal cycles that have profound effects on Uranus's climate and weather patterns. The planet experiences varying atmospheric phenomena with a climate that remains largely enigmatic, but consistently unpredictable. The planet's sideways spin, however, provides more than just intrigue for astronomers. It also acts as a key to understanding the violent processes that shaped the early solar system. By studying how Uranus came to be in such an extreme orientation, scientists gain deeper insight into the mechanisms of planetary formation and evolution. Much like Uranus's tilt, another extraordinary feature within our solar system has captivated the attention of researchers: Saturn's hexagonal storm at the planet's north pole. This storm, which spans around 15,000 miles across, has been a subject of fascination ever since it was first observed by NASA's Voyager missions in 1980. The peculiar six-sided shape of the storm, which persists in the upper atmosphere of Saturn, offers clues about the complex dynamics of gas giants and their unique atmospheric behavior. The hexagon is a direct result of differential rotation, where the winds at various latitudes on Saturn move at different speeds. The interplay between these fast and slow-moving air currents creates a standing wave pattern which stabilizes the hexagonal shape. The pattern is further reinforced by the presence of a powerful jet stream, flowing eastward at about 125 miles per hour, that encircles the hexagon. This jet stream maintains the storm's unique formation, organizing the atmospheric flow into a consistent six-sided shape. Curiously, the hexagonal structure has shown remarkable stability over long periods. Despite fluctuations in the surrounding atmospheric conditions, the hexagon endures. Its immense scale likely contributes to this durability, allowing it to persist while other storms come and go. Observations from the Cassini spacecraft, which studied Saturn from 2004 to 2017, provided crucial data that has deepened our understanding of this phenomenon. The hexagonal storm serves as a stunning example of the intricate forces at play in the atmospheres of gas giants, offering a glimpse into the fluid dynamics that govern these distant worlds. Turning to a completely different realm of inquiry, the idea that life on Earth may have had multiple origins is a compelling concept that challenges traditional ideas about the emergence of life. Current scientific theories generally point to complex chemical processes as the foundation for life's beginnings, leading to the emergence of simple biological systems. Given the right conditions, it seems plausible that these processes could have occurred independently in different locations on Earth, leading to the possibility of multiple, distinct origins of life. Some researchers propose that life may have originated in several diverse habitats: hydrothermal vents on the ocean floor, shallow pools of water, or even icy environments on the surface of the planet could each have provided the ideal conditions for the formation of the first organic compounds, setting the stage for the development of primitive life forms. Early Earth, with its variety of environments, may have supported different pathways for life to emerge, potentially giving rise to multiple independent events of biogenesis. This idea aligns with the concept of extremophiles, organisms that thrive in the most extreme environments known on Earth. These life forms demonstrate the remarkable versatility of biochemical processes, suggesting that life could have emerged in a wider array of habitats than previously imagined. If simple life forms were able to develop in such diverse environments, it opens the intriguing possibility that different life forms may have evolved in parallel, only to later merge through competition or interaction. According to the principle of competitive exclusion, one group of organisms might have outcompeted others for resources, ultimately leading to the predominance of a single lineage that dominated the evolutionary landscape over time. In this light, the origins of life on Earth could have been more complex and varied than we once thought, pointing to a broader, more multifaceted picture of life's emergence on our planet. However, despite the theoretical allure of multiple origins of life, there is, at present, no direct evidence to support this idea. Most of the evidence we have consistently points to a single origin, a common ancestor from which all current life on Earth has descended. The field of astrobiology, however, continues to explore the fascinating question of how life could emerge and evolve in a variety of environments. Understanding how life might arise in conditions far beyond Earth offers a mirror into our own origins, providing new perspectives on the processes that shaped us. As we search for life beyond our planet, each new discovery about early microbial life on Earth refines our hypotheses on the origins and evolution of life. These findings fuel an ongoing quest to answer one of the most profound questions humanity faces. Where did life come from? One of the most intriguing ideas in astrobiology is panspermia, the hypothesis suggesting that life, or at least the essential building blocks for life, might be spread throughout the universe by comets, asteroids, or meteoroids. This concept opens up tantalizing possibilities. Could life have traveled between celestial bodies, perhaps seeding planets like Earth with the necessary ingredients for life? Over the years, scientists have carefully examined the plausibility of this idea, evaluating the conditions under which life could transfer between planets and what this means for the existence of life beyond our world. A key argument in favor of panspermia lies in the resilience of microbial life. Certain extremophiles, organisms capable of surviving extreme conditions, can endure intense radiation, extreme temperatures, and even the vacuum of space. Their extraordinary adaptability suggests that microorganisms could survive the journey through space, perhaps embedded within meteorites, traveling vast distances across the cosmos. Some studies even propose that these organisms could remain dormant for extended periods, only to reactivate upon reaching a more hospitable environment, such as a planet with the right conditions for life. Furthermore, there is evidence that celestial bodies can exchange material. For example, asteroid impacts can eject debris into space, which might later collide with another planet. On rare occasions, material from Earth might be transported to Mars, or vice versa. This process of cross-planar contamination lends support to the notion that life could potentially transfer between planetary bodies within our solar system, and even beyond it. Nevertheless, while panspermia offers an intriguing mechanism for how life might spread across space, it does not answer the fundamental question of how life began in the first place. If life did arrive on Earth from elsewhere, it still raises the critical question: where and how did life originate? The panspermia hypothesis primarily emphasizes the potential for life to spread, not its initial creation. While the idea of life traveling vast distances through space is fascinating, the actual likelihood of such a journey and the success of life in establishing itself on another planet remains uncertain. Current research continues to probe the resilience of microorganisms in space-like conditions, investigating the mechanisms that would allow life to travel through the vacuum of space and survive the extreme conditions it might encounter. As we push further into the cosmos, exploring planets, moons, and distant stars, the search for signs of life, whether indigenous or transported, deepens our understanding of life's origins. The exploration of panspermia may yet yield the key to unlocking the mystery of life's spread across the universe. The boundaries of life are continually being tested and redefined by scientific research, with each new discovery expanding our understanding of what life can endure. Earth itself is a testament to life's remarkable adaptability, with organisms thriving in environments once thought to be uninhabitable. These extreme environments, which include searing heat, crushing pressure, high acidity, saline concentrations, and intense radiation, provide a fascinating lens through which we examine the limits of life as we know it. Among the most extreme environments on Earth are hydrothermal vents deep beneath the ocean. Here, organisms tap into chemical energy from sulfur compounds, thriving in temperatures that can exceed 300 degrees Fahrenheit. These thermophiles and hyperthermophiles challenge our notions of life, revealing its ability to survive and flourish in high heat where most life forms would perish. Similarly, psychrophiles, organisms that endure freezing temperatures as low as 38 degrees Fahrenheit, showcase the resilience of life in frigid, inhospitable conditions. Acidic environments, such as those found at acid mine drainage sites, are home to acidophiles, organisms that thrive in highly acidic conditions with pH levels as low as 0. In contrast, halophiles, salt-loving organisms, exist in highly saline environments, including salt flats and salt lakes, demonstrating life's ability to adapt to extreme concentrations of salt. These adaptations are not just passive survival tactics. They involve intricate biochemical and structural modifications that enable these organisms to maintain cellular functions and stabilize their proteins and membranes under such extreme conditions. Each of these extraordinary life forms adds another piece to the puzzle of life's origins and its potential to thrive in environments beyond our planet. Studying extremophiles not only challenges our understanding of what life is, but also deepens our exploration of how life might survive, and perhaps even thrive, in the most extreme conditions the universe has to offer. However, there are limits to these adaptations. Beyond certain thresholds of pressure, temperature, or radiation, the fundamental biological processes that sustain life, such as DNA replication, protein synthesis, and cellular metabolism, can break down. The boundaries of life, as we understand it, are often defined by the fragility of complex biological molecules and the delicate balance of biochemical reactions that are necessary for survival. Extreme radiation, for example, poses another formidable challenge. It can damage DNA and other cellular structures, leading to catastrophic consequences for life as we know it. This vulnerability underscores the inherent limitations of life within certain environments. But within these constraints lies an opportunity for discovery. By studying extremophiles, organisms that thrive in environments previously thought to be inhospitable, we expand our understanding of life's resilience and adaptability. These remarkable organisms push the boundaries of what we consider possible for life, not only deepening our understanding of Earth's biological limits, but also informing the search for life beyond our planet. If life can thrive in environments such as the icy moons of Jupiter and Saturn, where temperatures plunge far below freezing and radiation levels are intense, then the potential for discovering life in similarly extreme conditions elsewhere in the universe becomes ever more plausible. The discovery of life forms in these seemingly harsh environments would drastically alter our understanding of life's resilience and redefine the conditions under which life can exist. As our research continues to explore these frontiers, the concept of life's boundaries evolves. It reshapes our understanding of what it means to be alive in a universe so vast and diverse. Defining life, especially in a cosmic context, involves considering a broad range of characteristics that capture the essence of living organisms, while accounting for the incredibly diverse environments that may exist beyond Earth. Traditionally, life is characterized by several fundamental properties, including organization, metabolism, growth, reproduction, response to stimuli, and adaptation through evolution. But as we search for extraterrestrial life, the challenge becomes one of adaptation. How do these criteria translate to environments completely different from those found on Earth? And more importantly, how might these traits manifest in forms that are vastly different from anything we know? At its core, life is defined by its ability to maintain homeostasis, a stable internal environment despite fluctuations in its external surroundings. This concept encompasses a range of physiological processes that, on Earth, are carried out by biochemical pathways. These pathways convert energy from the environment, allow for growth and reproduction, and use genetic systems to pass on information to future generations. But what if alien life does not follow the same biochemical blueprints? Could life, for example, rely on alternative biochemistries, perhaps even non-carbon-based compounds? These are the questions that researchers are beginning to address as we push the boundaries of our understanding. In the search for extraterrestrial life, scientists focus on environments where these life-sustaining processes might be possible. They examine subsurface oceans on icy moons, the atmospheres of exoplanets, and other far-flung places, seeking evidence of metabolic processes or organic molecules that could suggest the presence of life. This evolving field, known as astrobiology, seeks not only to define the conditions necessary for life, but also to provide new methods for detecting life elsewhere in the universe. Through astrobiology, we hope to expand the scope of what we consider to be life, embracing the possibility that life forms may exist in forms so radically different from our own that they challenge our very definitions. As we continue to explore the vast expanse of the cosmos, we find ourselves redefining the boundaries of life, shaping a new, broader understanding of what it truly means to be alive. Additionally, the concept of life as we know it may be far too limited when we consider the immense diversity of life forms that could exist across the universe. If we are to expand our understanding, we must account for the possibility that life might emerge based on chemistries entirely different from what we are familiar with, such as silicon rather than carbon, or even thrive in environments that we currently deem uninhabitable. In this context, the definition of life becomes a fluid and evolving idea, one that stretches beyond Earth's narrow framework to embrace the infinite potential for varied forms of existence. While still acknowledging the fundamental principles that define living systems, the exploration of life's many possible forms continues to challenge and expand our understanding. As researchers delve deeper into the complexities of life beyond Earth, the question of what constitutes life itself remains an intriguing, dynamic subject. With every discovery, we are drawn closer to imagining the vast, untapped possibilities of life in the cosmos, and in turn, we are forced to reconsider the very essence of life in a universe that is much more expansive and varied than we once believed. Comets and asteroids, those ancient messengers from the early solar system, play crucial roles in the distribution of organic compounds not just within our solar system, but potentially throughout the universe. These celestial bodies are relics from the formation of our solar system, containing water, organic molecules, and other key ingredients that could be vital for the development of life. Their interactions with planets through impacts or close encounters could seed these planets with compounds necessary for life's emergence. Comets, made predominantly of ice and dust, are particularly fascinating. As they approach the sun, their icy exteriors vaporize, forming glowing comas and tails that are visible from Earth. In this process, comets release organic compounds such as amino acids, building blocks of life. When these comets collide with planets, they can deliver organic materials directly to their surfaces, essentially seeding them with the ingredients needed for life to take root. Asteroids, in contrast, are rocky bodies that also carry a wealth of organic materials. Some asteroids are particularly enriched with carbon-based compounds, making them rich sources of essential organic molecules. When these asteroids impact a planet, they transfer not only organic compounds, but also vital water, further contributing to the chemical complexity that supports life's origins. The study of meteorites, particularly carbonaceous chondrites, has shown that many of the amino acids and organic compounds found on Earth could also exist within these ancient space rocks. This discovery supports theories like panspermia, which suggests that life or its precursors may have been transported across the cosmos, seeding planets far beyond our own. The evidence of organic materials in comets, asteroids, and meteorites is not just an academic curiosity. It provides tangible insights into how life might have originated on Earth and how it might emerge elsewhere in the universe. As space missions continue to study these cosmic bodies, scientists hope to unravel the complex processes that govern the distribution of organic compounds and their role in life's origins. These ongoing discoveries are not only deepening our understanding of planetary chemistry, but also shedding light on the potential pathways life could take in the vastness of space. In exploring these ancient bodies, we are learning more about the building blocks of life and how they might spread across the cosmos, defying the limitations of our earthbound perspective. However, planetary habitability is not a fixed condition. It is a dynamic and evolving feature that changes over vast timescales. The ability of a planet to support life can be shaped by a myriad of factors, including geological activity, atmospheric changes, stellar evolution, and cosmic events. Understanding how these elements interact offers vital insights into the potential for life to flourish on a given planet throughout its history. One of the most important factors influencing a planet's habitability is its geological activity. On Earth, plate tectonics is a fundamental process that maintains a stable climate and recycles essential nutrients. Over millions of years, geological activity transforms a planet's surface, creating environments that may either support or hinder the development of life. In contrast, a planet that ceases to undergo geological processes may experience a decline in habitability, as its atmosphere degrades and its surface becomes increasingly inhospitable. Atmospheric conditions are equally pivotal in determining whether a planet remains habitable. For example, Earth's early atmosphere was largely composed of carbon dioxide and other gases that created a hostile environment for life. Over time, however, biological processes, volcanic activity, and extraterrestrial impacts gradually shifted Earth's atmosphere, enriching it with oxygen, a change that allowed complex life forms to thrive. As a planet's atmosphere evolves, so too do its prospects for supporting life. An atmosphere that becomes too thick or toxic could render a once habitable planet uninhabitable. Stellar evolution is another critical factor in a planet's long-term habitability. Over billions of years, stars undergo significant changes in their size, brightness, and energy output. As a star like our Sun ages, its increased brightness will gradually raise the surface temperature of nearby planets, eventually making them too hot to sustain life. This process will likely result in the loss of Earth's oceans and the collapse of its ecosystems, significantly altering the conditions that support life. These changes also shift the boundaries of the habitable zone, the region around a star where liquid water can exist, moving the area where life can thrive. Moreover, cosmic events such as asteroid impacts, supernovae, or even shifts in a planet's orbit can introduce sudden, catastrophic changes that affect habitability. For instance, an asteroid impact could cause mass extinctions, dramatically altering ecosystems and the evolutionary course of life. These cosmic disruptions emphasize that planetary habitability is a fluid, dynamic characteristic, shaped by both internal and external forces over time. By studying the history of Earth's habitability and the conditions on other celestial bodies, scientists aim to understand the complex processes that govern whether life can take root in the universe. As we continue to explore exoplanets and distant worlds, this knowledge will guide us in identifying environments that might support life, whether through the presence of liquid water, a stable atmosphere, or other indicators. In the search for life beyond Earth, scientists focus on detecting biosignatures, indicators of biological activity that may point to the presence of life on exoplanets. These biosignatures can take many forms, including chemical, physical, and biological signals that suggest the presence of life. By studying these potential biosignatures, we continue our quest to answer one of humanity's oldest questions: are we alone in the universe? One of the most significant biosignatures that researchers focus on when exploring the potential for life beyond Earth is the presence of specific gases in a planet's atmosphere. On Earth, certain gases like oxygen and methane exist in a delicate balance, a balance that is largely maintained by biological processes. The simultaneous presence of both oxygen and methane in an atmosphere can be a powerful indicator of biological activity. Oxygen typically depletes methane, meaning that if both gases are found together in detectable quantities, there must be a continual source replenishing methane, often linked to biological processes. However, these gases aren't the only atmospheric markers. Other gases, such as carbon dioxide, nitrous oxide, and ozone, also play a crucial role in revealing the potential for life. When found in particular concentrations and in certain relationships with each other, these gases can signal biological activity, providing yet another vital clue for astrobiologists searching for signs of life elsewhere in the universe. In addition to atmospheric signatures, the detection of specific organic molecules is another key biosignature. Organic compounds, such as amino acids, fatty acids, and hydrocarbons can be associated with biological processes, particularly when found in unusual or complex structures. While these compounds can be produced through geological or chemical processes, the presence of a wide variety of organic molecules, especially in large amounts, often points to biological origins. The discovery of such molecules may offer scientists valuable evidence of past or present life. Surface features and geological conditions are also important to understanding potential habitability. For example, formations similar to stromatolites, which are produced by microbial life on Earth, could suggest past biological activity. The presence of liquid water, whether it exists in the form of vast oceans, deep lakes, or even hidden subsurface aquifers, is considered one of the most fundamental biosignatures. Water is essential for life as we know it, making it a critical element in the search for extraterrestrial life. Equally important are isotopic ratios. The ratios of certain isotopes in a planet's atmosphere or surface materials can reveal signs of biological processes. For instance, organisms on Earth preferentially utilize particular isotopes during metabolic processes. The isotopic ratios of carbon found in organic matter can reveal biological activity, serving as a telltale sign of life. As technology continues to advance, scientists are developing ever more sophisticated instruments to analyze the chemical compositions of exoplanet atmospheres. By identifying and studying these biosignatures, researchers aim to uncover signs of life beyond our planet and deepen our understanding of the cosmos. The search for biosignatures doesn't just rely on one scientific discipline, but is a collaborative effort. Astrobiologists, chemists, physicists, and other experts work together, combining their knowledge to decipher the mysteries of life in the universe. This collaboration emphasizes the importance of a multidisciplinary approach in the search for extraterrestrial life. The study of astrobiology also delves into the fascinating potential for life to adapt in environments radically different from Earth. On our planet, extremophiles, organisms that thrive in extreme conditions, are prime examples of how life can adapt in ways we may not initially expect. These adaptations offer scientists a glimpse into the diverse forms life could take on other worlds. For instance, life on a planet with a harsh, high-radiation environment might evolve to develop robust DNA repair mechanisms or protective biofilms. On gas giants, where extreme pressures exist, life forms could evolve specialized structures to withstand these immense forces. When considering potential life beyond Earth, one of the most significant factors is the biochemical makeup of organisms. Earth-based life is primarily carbon-based, relying on water and amino acids. However, in environments where carbon is scarce, scientists speculate that life could evolve with alternative biochemistries. Silicon, for example, is one such candidate that could form the basis of life in low-carbon environments. Life might also use other solvents, such as ammonia or methane, instead of water, leading to biochemistries that are drastically different from anything we're familiar with. Extreme temperatures could also influence the way life evolves. In very hot environments, such as those found near hydrothermal vents, organisms might develop heat-resistant proteins and membranes to survive the intense heat. Conversely, in extremely cold environments, such as icy moons or planets, life could evolve antifreeze-like compounds that enable metabolic processes to continue despite the freezing temperatures. The potential for life to adapt to harsh conditions doesn't stop there. On planets with high radiation levels, life might evolve in ways that allow organisms to shield themselves from the radiation's damaging effects. In places where sunlight is scarce, organisms may rely on chemosynthesis, the process of deriving energy from chemical reactions rather than from the sun, as seen in Earth's deep-sea ecosystems. Scientists are investigating a wide range of celestial bodies to determine the conditions under which life might arise. Planets like Mars and moons like Europa and Titan all present unique environments that could potentially foster life. By studying the adaptability of life, scientists not only deepen our understanding of life on Earth, but also expand the possibilities for finding life beyond our planet. The search for life in the cosmos has led to the exploration of more than just planets that orbit stars. Rogue planets, those that wander through space unbound to any star, pose a unique challenge to astronomers. Despite the difficulties in detecting these elusive worlds, advancements in technology have opened new doors for identifying rogue planets and studying their characteristics. One of the primary methods used to detect rogue planets is gravitational microlensing. This phenomenon occurs when a rogue planet passes in front of a more distant star, temporarily magnifying the light of that star due to the planet's gravitational field. By studying the light curve of the distant star, astronomers can detect the signature of a rogue planet. Infrared observations also play a role in detecting these planets. Since rogue planets do not emit their own light, they are invisible in visible wavelengths. However, their heat signature can often be detected in the infrared spectrum, offering another way to identify these wandering worlds. By investigating these rogue planets and their potential for life, scientists are not only expanding our knowledge of the cosmos, but also learning more about the vast range of conditions in which life might exist. As technology improves and our understanding of the universe deepens, the search for biosignatures, extreme life forms, and rogue planets continues to drive exploration and discovery, pushing the boundaries of human knowledge. Rogue planets, drifting aimlessly through the void of space, continue to intrigue scientists. Although they may not have a star to call home, they can still emit thermal radiation, particularly if they are relatively warm or have recently experienced geological activity. Observatories equipped with advanced infrared telescopes, such as the James Webb Space Telescope, are capable of detecting the heat signatures of these mysterious worlds as they wander through the cosmos. By studying the emitted thermal radiation, astronomers can uncover valuable details about the rogue planets, including their temperatures, atmospheric compositions, and even the potential conditions on their surfaces. Direct imaging, though challenging, is another promising method for studying rogue planets, especially those in closer proximity. With the help of cutting-edge imaging techniques like adaptive optics, telescopes are able to correct for the blurring effects caused by Earth's atmosphere. This allows scientists to capture sharper images of these far-off planets, revealing more about their characteristics. While this method has shown limited success so far, its potential is undeniable, and as technology continues to evolve, it may become a vital tool in the study of rogue planets. Once these planets are detected, further investigation often focuses on their atmospheres and surface features. Spectroscopy plays a central role in this research. By examining the light that either passes through or reflects off a planet's atmosphere, scientists can identify chemical signatures that tell them about the planet's composition, temperature, and its potential to support life. This technique offers a window into the hidden details of rogue planets, from their chemical makeup to their possible habitability. Studying rogue planets also sheds light on the broader processes of planetary formation and evolution. Many of these planets are thought to have originally formed within the confines of their own solar systems, only to be ejected later due to gravitational interactions. This phenomenon provides valuable insights into the dynamics of planetary systems, offering a glimpse into the forces that shape these distant worlds. As research into rogue planets progresses, our understanding of these enigmatic objects and the environments that may exist on them will continue to deepen. Meanwhile, exploring gas giants like Jupiter and Saturn presents its own set of challenges. These massive planets, with their thick atmospheres and extreme conditions, require specialized technologies to study. Advanced spacecraft designed for long-duration missions are crucial in this endeavor. These vehicles must be capable of withstanding the harsh environments of gas giants, which include extreme temperatures, intense radiation, and powerful gravitational forces. Take, for example, the Juno spacecraft, which was launched in 2016 to study Jupiter. Equipped with advanced shielding and cutting-edge instruments, Juno is able to endure the planet's intense radiation while sending back critical data that expands our understanding of this giant world. Instruments for remote sensing play a pivotal role in studying the atmospheres of gas giants. Spectrometers, which measure the wavelengths of light emitted or reflected by a planet's atmosphere, offer detailed insights into its chemical composition and structure. These instruments are capable of identifying specific gases and determining their concentrations, which provides valuable information about atmospheric processes, cloud formations, and potential weather patterns. Together, these technologies create a comprehensive picture of the gas giants, allowing scientists to explore their mysteries from a distance. As research continues and technologies advance, our ability to detect, observe, and understand distant planets, whether rogue or part of a planetary system, will expand, revealing new layers of complexity and beauty in our universe. Radar and microwave instruments have been indispensable tools in the exploration of gas giants, probing the depths of their dense atmospheres. These sophisticated instruments, which can penetrate through thick cloud layers, offer invaluable data on atmospheric dynamics and temperature profiles. For example, Juno's microwave radiometer has provided groundbreaking insights into the structure of Jupiter's atmosphere, unveiling details beneath its swirling cloud tops. This data sheds light on the planet's atmospheric circulation and internal dynamics. Such instruments are pivotal in unlocking the mysteries of gas giants, laying the foundation for future research and exploration. Looking ahead, entry probes are emerging as a promising technology for missions to gas giants. These robotic explorers would be engineered to descend through thick atmospheres, collecting data at various altitudes. With the ability to directly measure temperature, pressure, winds, and chemical compositions in situ, these probes would provide a wealth of information about the lower layers of gas giants' atmospheres. By offering a more direct approach, these probes could unlock critical insights into the core properties of gas giants, enhancing our understanding of their complex atmospheric systems. In parallel, satellite communication and data transmission technologies are essential for relaying the vast amounts of data collected from space. Efficient communication systems ensure that findings from distant spacecraft reach Earth, allowing researchers to analyze the results and plan future missions. This is crucial for continuing our exploration of these distant worlds and their atmospheres. The study of gas giants represents a convergence of cutting-edge spacecraft design, advanced instrumentation, and data processing, all working in tandem to reveal the complex nature of these distant planets. As our knowledge of gas giants grows, the development of innovative technologies will further expand our capabilities to explore these enigmatic worlds. These advancements not only deepen our understanding of the planets themselves, but also offer potential clues about their formation and evolution within our solar system. Meanwhile, the exploration of icy moons such as Europa and Enceladus represents a different yet equally compelling frontier in planetary science. These moons, with their subsurface oceans, may harbor the conditions necessary for extraterrestrial life. Scientists use a variety of techniques to investigate these moons, including remote sensing, land emissions, and advanced modeling. The combination of these methods provides a comprehensive view of their internal structures and the possibility of life beneath their icy surfaces. Remote sensing is one of the primary tools used in exploring icy moons. Spacecraft equipped with advanced instruments observe these moons from orbit, gathering crucial data about their surfaces and atmospheres. For example, the Galileo spacecraft, which studied Europa in the late 1990s, identified surface features such as ridges and cracks in the ice, suggesting the presence of a subsurface ocean. Instruments like ice-penetrating radar can even measure the thickness of the icy shell, providing insight into the ocean's size and depth. Another valuable technique involves measuring the gravitational fields of these moons. As a spacecraft orbits a moon, its gravitational pull alters the spacecraft's trajectory. By analyzing these changes, scientists can infer details about the moon's internal structure, including variations in density and the presence of liquid water. This method has been successfully used in previous missions and continues to be a powerful tool in mapping out subsurface oceans and icy layers. Although no dedicated landers have yet been deployed to Europa or Enceladus, future missions hold great promise for exploring the surfaces of these moons. Robotic landers could be designed to directly sample the ice and any plumes of water vapor, particularly on Enceladus, where geysers have been observed releasing water vapor and organic molecules into space. Analyzing these samples would provide critical information about the subsurface ocean and its potential to support life. Computer models are also essential in interpreting data from icy moons. These models simulate the internal conditions of the moons, helping scientists predict how their interiors operate. By combining observational data with advanced simulations, researchers can gain a deeper understanding of the thermal evolution, ice dynamics, and potential chemical environments beneath the surface. As we continue to explore moons like Europa and Enceladus, the intersection of engineering, observational science, and astrobiology will yield new insights into the potential for life in the outer reaches of our solar system. Missions like NASA's Europa Clipper and the European Space Agency's Jupiter Icy Moons Explorer are preparing to launch in the coming years, bringing us closer to answering fundamental questions about these mysterious moons. Their findings could significantly enhance our understanding of the conditions necessary for life beyond Earth. On an even grander scale, the idea of sending probes to nearby stars has captivated both scientists and the public. Yet the challenges of interstellar travel are immense, covering technological, financial, and logistical hurdles. The sheer distances involved make such missions daunting. The closest star system to Earth, Alpha Centauri, lies over 4 light-years away. Even if we could travel at the speed of light, something far beyond our current capabilities, it would take more than 4 years to reach it. At present, spacecraft travel much slower. For instance, the Parker Solar Probe, one of the fastest human-made objects, can reach speeds of approximately 63 kilometers per second. At this speed, a journey to Alpha Centauri would take tens of thousands of years, an impractical timeframe for a meaningful mission. To make interstellar travel possible, the development of propulsion systems that can achieve a significant fraction of the speed of light is crucial. Research into concepts such as solar sails, nuclear propulsion, and even theoretical technologies like antimatter engines and fusion drives is already underway, offering a glimpse into the potential future of interstellar exploration. As these technologies evolve, the dream of reaching other star systems becomes ever more tantalizing. Though the challenges are formidable, the pursuit of interstellar travel is an endeavor that pushes the boundaries of human ingenuity and curiosity, driving us toward an unknown frontier in the vast expanse of space. The quest for advanced propulsion systems remains a tantalizing frontier in space exploration, yet these systems are still largely experimental. There are numerous engineering hurdles that must be overcome before they can be used effectively in crewed or uncrewed missions. One significant challenge is the communication delay inherent in interstellar travel. Once a probe is launched toward a distant star, the time it takes for signals to travel back to Earth is measured in years. This delay creates an obstacle to receiving real-time data or issuing instructions to the spacecraft. As a result, the effectiveness of remote operations is severely limited, and the spacecraft must rely on autonomous systems to conduct experiments and make decisions independently. In addition to the communication challenge, the hostile environment of space presents further obstacles to mission success. Probes will need to endure extreme conditions, including prolonged exposure to radiation, extreme temperature fluctuations, and the constant threat of micrometeoroid impacts. Traveling across vast distances will expose spacecraft to these dangers for many years, requiring the development of instruments and systems capable of withstanding these harsh conditions. Designing such durable technologies is essential for ensuring that data collection continues even as the probe travels toward distant star systems. Financial considerations also play a major role in the feasibility of interstellar missions. Sending probes to other star systems would require substantial investment, either from government agencies or private entities. However, funding for such projects is difficult to secure, especially when competing with other high-priority space initiatives. The enormous costs, coupled with the long timelines associated with these missions, make it hard to maintain continuous support for the necessary research and development. While technological advancements and human ingenuity are bringing the dream of interstellar exploration within reach, these substantial challenges must be addressed before we can send probes to neighboring stars. Moreover, the exploration of primordial black holes offers yet another complex challenge that demands creative and innovative solutions. Unlike stellar black holes, which form when massive stars collapse, primordial black holes are theorized to have emerged shortly after the Big Bang. These early black holes are thought to have formed due to density fluctuations in the rapidly expanding universe, and their sizes can vary widely, from extremely small to potentially large, depending on the conditions at the time of their formation. Detecting primordial black holes is especially difficult due to their elusive nature. They do not emit light or radiation like other celestial objects, making them invisible to conventional telescopes. However, one of the main ways to detect their presence is by observing their gravitational effects on nearby objects. In particular, gravitational lensing, the bending of light from background stars caused by the black hole's gravity, can reveal the existence of these mysterious objects. By carefully analyzing the distortions in light patterns caused by gravitational lensing, astronomers can estimate the mass and location of primordial black holes. Another method of detection involves searching for traces of primordial black holes in the cosmic microwave background (CMB) radiation, the faint glow that permeates the universe as a relic of the Big Bang. If primordial black holes exist, they could have influenced the large-scale structure of the universe and affected the distribution of matter in ways that are reflected in the CMB. Anomalies in the CMB, detectable through detailed maps created by missions such as the Planck satellite, might provide indirect evidence of primordial black holes' impact on cosmic evolution. Primordial black holes may also generate gravitational waves when they merge with other black holes or compact objects. These waves are ripples in space-time caused by violent cosmic events, and they can be detected by observatories like LIGO and Virgo. By studying the gravitational wave signals produced by the mergers of primordial black holes, scientists can gain valuable insights into their properties, including their masses, distances, and the dynamics of the collisions. These discoveries could offer profound revelations about the nature of the early universe and the fundamental forces that shaped it. Primordial black holes, if they exist, could hold the key to unlocking deeper mysteries about the universe. If these black holes have smaller masses, they might interact with dark matter in ways that leave detectable marks in the cosmos. Studying dark matter itself might indirectly reveal insights into the nature of primordial black holes, whether they exist and what their properties could be. However, this path is fraught with challenges. Detecting and studying primordial black holes requires overcoming significant technical hurdles. Yet, with each passing year, progress in observational technologies pushes the boundaries of what we know. New telescopes, gravitational wave detectors, and cosmic surveys offer a tantalizing glimpse into previously hidden parts of the universe, igniting hope that we might one day uncover concrete evidence of primordial black holes and better understand their role in the evolution of the cosmos. Exploring the heart of our galaxy, the Milky Way's galactic core, poses its own unique set of challenges. This region, which is dense with stars, gas, and dust, is a maelstrom of intense gravitational forces and high-energy radiation. Despite these obstacles, advancements in technology are enabling us to peer deeper into this enigmatic zone. Radio astronomy has emerged as one of the most effective ways to study this region. Radio telescopes, capable of observing non-visible emissions, can penetrate the thick clouds of gas and dust that obscure visible light. By analyzing radio frequency signals from various cosmic phenomena, such as supernova remnants, pulsars, and the supermassive black hole at the center known as Sagittarius A, Sagittarius A, astronomers can uncover vital information about the composition and dynamics of the galactic core. Infrared astronomy is another indispensable tool for observing the galactic center. The dense dust clouds that obscure optical wavelengths can be bypassed with infrared light, revealing the inner workings of this tumultuous region. Space-based observatories like the Hubble Space Telescope and the upcoming James Webb Space Telescope are equipped with infrared instruments that enable scientists to study stellar populations, gas movements, and star formation within the core. These technologies provide insights that would be impossible to gain using optical observations alone. X-ray and gamma-ray astronomy further complement these methods, revealing high-energy phenomena within the galactic core. Space observatories such as the Chandra X-ray Observatory and the Fermi Gamma-ray Space Telescope can detect emissions from X-ray binaries, supermassive black holes, and gamma-ray bursts, sources that are abundant in the dynamic and high-energy environment of the galactic center. These observations help us understand the energetic processes shaping the region, offering a glimpse into matter's behavior under extreme conditions. Another emerging technique, gravitational wave astronomy, holds the potential to revolutionize our understanding of the galactic core. When compact objects like black holes and neutron stars merge, they generate gravitational waves that travel across the universe. By detecting and analyzing these waves with observatories like LIGO and Virgo, researchers can gain a deeper understanding of the mass distributions and dynamic interactions at play in the galactic center. Gravitational waves provide a new way of probing the universe, especially in regions that are otherwise difficult to study using traditional methods. Simulations and computational modeling also play a crucial role in studying the galactic core. By running computer models that simulate the complex interactions between stars, gas, and the supermassive black hole at the center, scientists can test their hypotheses and refine our understanding of the forces at work in this region. Although studying the galactic core remains challenging due to the extreme density and radiation levels, combining techniques such as radio, infrared, X-ray, and gravitational wave astronomy with theoretical models equips scientists with powerful tools to explore this complex environment. As technology continues to evolve, our capacity to study the galactic center improves. offering profound insights into the workings of our galaxy and the fundamental processes that govern its evolution. In the search for Earth-like exoplanets, a new frontier in space exploration is unfolding. Detecting these planets, particularly those that could support life, requires a combination of advanced technologies, innovative observational techniques, and comprehensive data analysis. Scientists and engineers are continually refining the tools and methods needed to enhance the sensitivity and precision of exoplanet detection, particularly in identifying worlds with conditions conducive to life. One of the most promising avenues for exoplanet discovery is the deployment of next-generation space telescopes. The James Webb Space Telescope, having recently launched, is poised to revolutionize the field. Equipped with advanced infrared imaging and spectroscopy capabilities, it will allow scientists to analyze the atmospheres of distant exoplanets, looking for chemical signatures that could indicate habitability or even the presence of life. Future missions, such as ESA's Ariel and NASA's LUVOR, or HABEX, aim to refine this search, particularly focusing on Earth-like planets around Sun-like stars. The transit method remains one of the most effective techniques for detecting exoplanets. This method involves observing the periodic dimming of a star's light as a planet passes in front of it. By analyzing these dimming events, scientists can infer the size, orbit, and distance of the planet. To improve the sensitivity of this method, larger and more powerful telescopes are being developed, along with precise photometers capable of detecting even smaller transiting planets. This will enhance the chances of finding Earth-like planets in the habitable zone of their stars. Another key technology is direct imaging. By blocking out the overwhelming light from a star, astronomers can capture images of exoplanets, even those located close to bright stars. Adaptive optic systems and coronagraphs, which improve image clarity, play a critical role in this process. With continued advancements, these techniques will further improve our ability to detect and characterize exoplanets that could resemble Earth. Radial velocity measurements also continue to be vital for detecting exoplanets. By measuring the slight wobble of a star caused by the gravitational pull of an orbiting planet, astronomers can infer the planet's mass and orbit. The development of enhanced spectrographs and high-precision instruments has significantly improved the sensitivity of this method, allowing scientists to detect smaller Earth-sized planets orbiting distant stars. With these advancements in technology and observational techniques, the quest to uncover Earth-like exoplanets has entered an exciting new phase. As we continue to refine our tools and methods, the possibility of discovering planets capable of supporting life grows ever more tangible, pushing the frontiers of science and exploration. By leveraging the power of machine learning and artificial intelligence, we can greatly enhance the way we analyze vast data sets. These advanced technologies can sift through massive volumes of observational data, detecting subtle patterns and identifying potential exoplanet candidates far more efficiently than traditional methods. By automating parts of the analysis process, machine learning algorithms streamline the detection process, making it easier to spot Earth-like exoplanets hidden among a sea of other signals. This integration of AI and machine learning into the search for exoplanets not only improves observational strategies, but also expands our ability to process data, driving the effectiveness of our search for distant worlds that could harbor life. As our analytical capabilities continue to evolve, the ongoing quest to detect and characterize exoplanets brings us closer to answering one of humanity's oldest questions. Are we alone in the universe? Could there be other Earth-like planets with the potential for life as we know it? Meanwhile, the concept of harnessing antimatter for space propulsion has become an exciting prospect for the future of space exploration. This revolutionary technology could pave the way for propulsion systems far more efficient than anything we have today. Antimatter, the opposite of ordinary matter, has a fascinating property. When it comes into contact with its matter counterpart, both annihilate, releasing enormous amounts of energy. According to Einstein's famous equation, E equals mc squared, this annihilation reaction yields energy at levels that are incomprehensibly high compared to conventional chemical propellants. This makes antimatter a compelling candidate for advanced propulsion technologies. One of the key advantages of antimatter propulsion lies in its potential for high thrust-to-weight ratios. This means spacecraft could achieve speeds far beyond what current propulsion systems allow. A spacecraft powered by antimatter engines could potentially reach a significant fraction of the speed of light, drastically reducing travel times to distant stars. This holds the tantalizing possibility of making interstellar exploration feasible in the not-so-distant future. However, before antimatter can be used in practical propulsion systems, several significant challenges must be overcome. At present, the production of antimatter is both inefficient and prohibitively expensive. While antimatter is generated in particle accelerators like CERN, the quantities produced are minuscule. Current estimates suggest that producing even a gram of antimatter could cost trillions of dollars, making it economically unfeasible in its current form. For antimatter propulsion to become a reality, we would need to develop methods for mass production or discover more cost-effective ways of creating and capturing antimatter. In addition to production hurdles, safely storing and handling antimatter presents another significant challenge. Since antimatter annihilates when it comes into contact with regular matter, it must be kept in a vacuum, suspended within strong magnetic or electromagnetic fields. Without such containment, antimatter would immediately react, releasing vast amounts of energy. Engineering systems capable of maintaining antimatter in stable conditions for extended periods of time remains a substantial hurdle. Furthermore, any spacecraft designed to utilize antimatter propulsion would require careful mission planning. This includes optimizing the spacecraft's trajectory, integrating antimatter systems with existing technologies, and ensuring the safety of the crew during deep space missions. While antimatter propulsion may seem like science fiction, the continued advancement of research in antimatter physics offers hope that it could become a reality one day. As new production technologies and containment solutions are developed, we may slowly bridge the gap between theoretical possibilities and practical applications. This ongoing research could not only transform space exploration, but also expand our understanding of the fundamental forces that govern our universe. If a magnetar, an incredibly magnetized and rapidly rotating neutron star, were to pass close to our solar system, the consequences could be both severe and catastrophic. Magnetars are known for their extraordinarily powerful magnetic fields, which are thousands of times stronger than the magnetic fields of regular neutron stars and trillions of times stronger than Earth's magnetic field. These extreme magnetic fields, combined with the intense energy emissions from the magnetar's surface, could pose serious threats to our planet. One of the most immediate effects would be the disruption of Earth's magnetic field. If a magnetar passed within just a few light years, its magnetic field could distort and destabilize Earth's own magnetic field, leading to geomagnetic storms. These storms could have far-reaching consequences for our technological infrastructure, including power grids and satellite communications. In the worst-case scenario, the induced electrical currents could overwhelm transformers and other critical systems, causing blackouts and prolonged electrical outages that could last for weeks or even months. But the dangers wouldn't end there. Magnetars also emit bursts of high-energy radiation, particularly in the form of X-rays and gamma rays, which are among the most intense observed in the universe. If a magnetar came within a few hundred light-years of Earth, the resulting radiation could bombard our planet, potentially causing severe biological effects. Exposure to such intense radiation could lead to an increase in cancer rates and other health issues, particularly for those who are directly exposed to these elevated levels of radiation. While the likelihood of a magnetar passing near our solar system is extremely low, the potential consequences of such an event are significant enough to warrant further study. Understanding these cosmic phenomena and their impact on Earth is crucial as we continue to explore the mysteries of the universe. The intense radiation emitted by cosmic events like gamma-ray bursts could have profound and devastating effects on Earth's atmosphere. These high-energy gamma rays, capable of penetrating vast distances across space, can increase ionization within Earth's atmosphere. This disruption may lead to the depletion of the ozone layer, a shield that protects life on our planet from harmful ultraviolet UV radiation. A weakened ozone layer would allow more UV radiation to reach Earth's surface, with potentially catastrophic consequences for both ecosystems and human health. But that's not all. The gravitational influence of a magnetar, a neutron star with an incredibly dense core, would also come into play. If a magnetar were to come close enough, it could alter the gravitational dynamics of our solar system. This could affect the orbits of planets, asteroids, and comets, resulting in changes to their trajectories. However, such an event would require the magnetar to be exceptionally close, much closer than any known object in our immediate vicinity. In most cases, this would only happen if the magnetar was within a few astronomical units, a scenario so unlikely that it hardly bears concern. Though the odds of a magnetar approaching our solar system are remote, its potential impact on Earth would be immense. It underscores just how finely balanced the conditions are that make life on our planet possible. Understanding these phenomena gives us valuable insight into the cosmic forces that shape our universe and emphasizes the fragile nature of life on Earth. Gamma-ray bursts, GRBs, stand as one of the most energetic and destructive phenomena observed in the cosmos. These bursts, often associated with the death of massive stars or the merger of neutron stars, release enormous amounts of gamma radiation that can devastate entire star systems. The immediate consequences of such an event are severe, particularly if a gamma-ray burst is directed toward a planet. The high-energy gamma radiation can penetrate atmospheres with ease, causing widespread biological damage. The result would be a significant increase in the ionization of atmospheric particles, leading to conditions akin to a massive solar flare, but on a far more catastrophic scale. This surge in radiation could disrupt cellular processes, causing higher mutation rates and an increased risk of cancer and other health issues for any life forms exposed to it. But the effects don't stop there. A gamma-ray burst could have wide-reaching consequences for the life potential within its host galaxy. While bursts occurring at vast distances from Earth would likely have reduced effects due to the dispersion of energy, their impact could still be profound for any life-bearing planet within range. However, there is a more complex interaction at play. Some scientists believe that the shockwaves created by a gamma-ray burst might also play a role in star formation. These intense waves of energy can compress nearby gas and dust, triggering the formation of new stars. In some cases, this could even lead to the creation of new planetary systems. While the destruction caused by a GRB would likely overshadow any potential for creation in the short term, the long-term effects could lead to new environments where life might emerge. Despite this, the rarity of gamma-ray bursts and their specific conditions of occurrence suggest that Earth has largely escaped their direct effects, though their implications for life elsewhere in the universe remain a subject of great interest. Galactic collisions, where two galaxies merge, represent one of the most dramatic events in cosmic history. These monumental events not only reshape the star systems within the galaxies involved, but also trigger profound changes in their structure over vast periods of time. The gravitational forces at play during such collisions have a remarkable impact on star formation, stellar dynamics, and the overall architecture of the merging galaxies. One of the most notable consequences of galactic collisions is the dramatic increase in star formation. When two galaxies collide, the gas and dust within them are compressed by the gravitational forces, leading to an intense burst of star formation, commonly referred to as a starburst. In these regions, stars are born at a rate far greater than in non-colliding galaxies, sometimes at several times the normal rate. Many of these newly formed stars will eventually end their lives in supernova, contributing to the cycle of creation and destruction that defines the universe. The gravitational disruptions caused by galactic mergers also alter the orbits of existing stars and gas clouds. Some stars may be ejected from their parent galaxies, becoming free-floating objects in intergalactic space. Others may be pulled into denser regions, participating in the formation of new star clusters, or even merging with other stars to form binary or multiple star systems. These interactions can lead to a dramatic reshaping of the stellar landscape within the galaxies involved. Furthermore, galactic mergers often result in the creation of entirely new structures. For instance, when two spiral galaxies collide, the resulting galaxy may take on a more elliptical shape. The collision can distort or even diminish the spiral arms, leading to a redistribution of stars and gas that significantly alters the dynamics of the entire galaxy. Over time, this restructuring can lead to a new era of evolution for the galaxy, one shaped by the forces unleashed during the merger. Through these cosmic events, we gain deeper insight into the processes that govern the universe. While they may seem distant and detached from our daily lives, understanding the far-reaching effects of such phenomena enhances our knowledge of the universe's intricate workings. It serves as a reminder of the dynamic and ever-changing nature of the cosmos, where creation and destruction are inextricably intertwined, shaping the future of galaxies, stars, and possibly even life itself. When galaxies collide, their supermassive black holes, located at their centers, undergo dramatic interactions. During such cosmic collisions, these black holes may draw closer to one another, setting the stage for the formation of binary black holes. Over time, the merger of these black holes generates gravitational waves, which not only provide a glimpse into their collision, but also offer insights into the broader history of the galaxies involved. These ripples in space-time echo across vast distances, revealing hidden truths about the universe's most massive objects. But the effects of galactic collisions extend far beyond the realms of black holes. They shape the very fabric of star systems, with the forces at play influencing everything from the creation of new stars to the conditions that make a planet habitable. Increased stellar activity during a collision, especially in the form of intense starbursts, can alter radiation levels dramatically. This surge in stellar radiation has the potential to impact the atmospheres of surrounding planets, perhaps even rendering them inhospitable, or conversely, fostering new conditions for life to thrive. Over time, the gravitational chaos and resulting dynamic changes that arise from galactic mergers can lead to complex environments that transform entire star systems. Enhanced star formation, disruptions in stellar dynamics, and the reordering of galactic structures are just a few of the cascading consequences. These phenomena not only impact existing stars, but also determine the future of planetary systems, constantly reshaping the evolutionary path of galaxies and the stars within them. In exploring these processes, we deepen our understanding of cosmic evolution. We begin to unravel the forces that have shaped and continue to shape the universe's most intricate structures. One of the most dramatic and violent events in the universe is the supernova, the explosive death of a massive star. Supernovae release an extraordinary amount of energy, and although devastating to their immediate surroundings, they can have surprising effects on neighboring planetary systems. While the intensity of a supernova's radiation and shockwaves can be catastrophic, the survival of planets within the affected system depends heavily on their distance from the explosion. A supernova emits a sudden burst of gamma rays, X-rays, and other forms of radiation. If a planetary system is far enough from the explosion, often tens of light years away, the radiation's impact diminishes to a level that may allow the planets to retain their atmospheres and continue to support life. On the other hand, the closer a system is to the explosion, the greater the risk to its habitability. But there's more. Supernovae also generate shockwaves that propagate outward, compressing interstellar gas and dust. This shockwave can trigger star formation in nearby molecular clouds, potentially creating new stars or contributing to the material available for planet formation. Even planetary systems situated further away from the explosion can be impacted, as the shockwave might deliver additional material that could feed into existing protoplanetary disks. This interaction could enhance the formation of new planets or help existing ones grow. In certain cases, if the supernova occurs within a binary star system, the surviving companion star can help stabilize the remnants of a planetary system. Should a planet continue to orbit the remnant, whether a neutron star or black hole, the system can survive. In fact, these remnants exert strong gravitational influence, potentially holding on to nearby planets that might have otherwise been lost. Moreover, supernovae can enrich the interstellar medium with elements heavier than helium, known as metals. This enriches the raw materials available for the creation of new stars and planets in the future, playing an essential role in the ongoing evolution of galaxies. These elemental aftershocks are a crucial part of how galaxies evolve and how new planetary systems come into being. In short, the long-term effects of supernovae on planetary systems are highly context-dependent, influenced by factors like distance from the explosion, the surrounding environment, and the evolutionary history of the host star. Understanding these dynamics offers invaluable insights into the broader processes that shape galaxies and illuminates the ongoing possibilities for life in the cosmos. But the supernova is not the most extreme of stellar explosions. That distinction belongs to the hypernova, a truly extraordinary event associated with the collapse of a massive star far beyond the scale of a typical supernova. A hypernova can release up to 100 times the energy of a regular supernova, making its consequences far more severe. If a hypernova were to occur relatively close to Earth, within a range of several tens of light years, the impact could be catastrophic. The most immediate and dramatic effect of a nearby hypernova would be the intense burst of gamma radiation. If this radiation were directed towards Earth, it could wreak havoc on our atmosphere. The gamma rays would increase ionization in the atmosphere, leading to the depletion of the ozone layer, which protects life from harmful solar radiation. With a compromised ozone layer, Earth would become vulnerable to higher levels of ultraviolet radiation. The consequences would be profound, with potential spikes in skin cancer rates, damage to plant life, and widespread disruption to ecosystems. Beyond radiation, the shockwave from a hypernova would also travel outward, compressing interstellar gas and dust. This shockwave could potentially affect the Earth's atmosphere, inducing severe weather phenomena and altering our planet's climatic conditions. The shockwave's reach extends far beyond Earth, potentially accelerating atmospheric changes and disturbing the geological balance of nearby planetary bodies. In summary, a hypernova occurring within proximity to Earth would not only disrupt life on our planet, but could also destabilize the very forces that shape the solar system. The resulting radiation, shockwaves, and atmospheric disruptions would leave an indelible mark on both our world and the cosmos. It serves as a stark reminder of the volatile and unpredictable forces at play in the universe, where even the smallest disturbances can ripple across the vast expanse of space, altering the fate of entire planetary systems. If a hypernova occurs close enough to our solar system, it could unleash a barrage of cosmic rays and high-energy particles that would inundate Earth with radiation. This increase in radiation could have serious consequences. It could disrupt satellite operations, damage technology, and pose a significant threat to human health. Individuals in high-altitude flights or on space missions would be especially vulnerable to elevated radiation levels. Over time, the accumulation of radiation might affect not only our immediate environment, but also long-term health, with potential genetic mutations or increased cancer risks for those exposed. Beyond these immediate dangers, a hypernova would have profound effects on the interstellar medium. The energetic output from such an event would enrich the space around it with heavy elements like iron and nickel, which could, over millions of years, lead to the formation of new stars and planetary systems. While this might contribute to the broader evolution of the galaxy, it's the immediate threats from the hypernova, such as radiation and its impact on existing life, that would be far more urgent. Another layer of complexity comes from the gravitational ripple effect a nearby hypernova could have on other star systems. The blast would scatter material and shift gravitational forces, potentially altering the orbits of nearby planets. This could destabilize the orbits of planets in other systems, creating chaos across vast distances. Even though the likelihood of such an event occurring in our corner of the galaxy is low, understanding the physics behind hypernovae helps us gauge the possible impacts on Earth and other planets. Similarly, our own sun, while not capable of triggering a hypernova, does produce immense bursts of energy in the form of solar flares. These flares can have far-reaching effects on space weather and the Earth's atmosphere. When a solar flare erupts, it releases an intense wave of electromagnetic radiation across a wide range of the spectrum, including visible light, ultraviolet rays, X-rays, and gamma rays. Along with this radiation, energetic particles are hurled into space, creating a storm of solar particles that travel outward, some of which eventually reach Earth. These solar particles interact with Earth's magnetic field, which can lead to geomagnetic storms. These storms disrupt the planet's magnetosphere, causing changes in the ionosphere that can interfere with radio communications, satellite operations, and GPS systems. Technology reliant on electromagnetic signals is particularly vulnerable to these storms. In more extreme cases, the influx of energetic particles can affect the very composition of a planet's atmosphere. For Earth, an increase in ultraviolet radiation could trigger chemical reactions that break down the ozone layer, which protects life from harmful radiation. For planets with thinner atmospheres, like Mars, the effects of solar flares are even more pronounced. Mars lacks a global magnetic field, leaving it defenseless against the solar wind and radiation. Over time, these intense solar flares can strip away the Martian atmosphere, contributing to its current thin and uninhabitable state. This process may provide insight into how solar flares could erode the atmosphere of a planet, potentially hindering its ability to sustain life. The threat from solar flares also extends beyond Earth, affecting space missions. Astronauts and spacecraft in space are at risk of severe radiation exposure during intense flare events, which could lead to acute health problems for those in orbit. Space agencies around the world carefully monitor solar activity to protect both astronauts and technology, preparing satellites and other equipment for potential flare-induced disruptions, whether it's the catastrophic potential of a hypernova or the more frequent but still significant impact of solar flares. Understanding these celestial phenomena is crucial. Solar flares shape space weather, triggering disruptions in communication, satellite operations, and even altering planetary atmospheres. Likewise, the possible consequences of a nearby hypernova emphasize the need to study and comprehend these cosmic events. In the end, monitoring such occurrences not only safeguards life on Earth, but also aids in our exploration of the vast and dynamic space beyond our home planet.